Close your eyes. Imagine looking up at the night sky. The stars stretch out before you, scattered like diamonds on black velvet, distant and cold and beautiful. And somewhere out there, somewhere beyond the furthest star you can see, beyond the edge of the Milky Way, beyond the billions of galaxies that fill the observable universe, lies a boundary. Not a wall, not an edge you could touch, but a horizon beyond which light has not had time to reach us. A cosmic border created not by space itself, but by the finite age of the universe and the finite speed of light. Beyond that horizon, approximately 46.5 billion light-years away in every direction, lies the rest of the universe, perhaps infinite. Perhaps filled with galaxies we will never see, stars that will never shine in our sky, worlds that will remain forever beyond our reach. We live in a universe so vast that the human mind cannot truly comprehend its scale. A universe so old that all of recorded human history represents less than 1/10,000,000th of its age. A universe governed by physical laws so strange that they defy common sense, where time can slow down, where space itself can bend, where something can come from nothing, and where the very fabric of reality is woven from mathematics we are only beginning to understand. This is 100 facts about the universe. Over 100 extraordinary facts, we are going to explore everything that exists, from the smallest quantum fluctuations to the largest cosmic structures, from the first moments after the Big Bang to the ultimate fate that awaits all things, from the nature of space and time themselves to the deepest mysteries that science has discovered but cannot yet explain. Along the way, we will encounter black holes where time stops, galaxies colliding in slow motion across billions of years, stars exploding with the energy of a billion suns, and cosmic voids so empty that they contain almost nothing for hundreds of millions of light years. We will explore the invisible universe, the dark matter that holds galaxies together, the dark energy that is tearing the universe apart, the quantum foam that bubbles at the smallest scales of reality. And we will confront the ultimate questions. How did the universe begin? How will it end? Are we alone? And is our universe the only one? Lie down, close your eyes, and let's explore everything that has ever existed, everything that exists now, and everything that ever will exist. Let's explore the universe. Fact 1. The universe is 13.8 billion years old. Begin with time. Before we can understand what the universe is, we need to understand when it began. And the answer, confirmed by multiple independent lines of evidence, measured with extraordinary precision, and representing one of the most important discoveries in the history of science, is that the universe is approximately 13.8 billion years old. This number, 13.8 billion years, or more precisely 13.787 billion years, with an uncertainty of only about 20 million years, was determined by the Planck Space Telescope, which measured the cosmic microwave background radiation with unprecedented accuracy. The cosmic microwave background is the afterglow of the Big Bang, the faint radiation left over from the moment when the universe first became transparent to light, approximately 380,000 years after the beginning of time. By analyzing the tiny temperature fluctuations in this ancient light, scientists can reconstruct the history of the universe with extraordinary precision. 13.8 billion years. To put this in perspective, if you compress the entire age of the universe into a single calendar year, with the Big Bang occurring at the stroke of midnight on January 1st, then the Sun and Earth would not form until September 2nd. The first complex life on Earth would not appear until mid-December. Dinosaurs would roam the Earth from December 25th to December 30th. And all of recorded human history, from the construction of the Egyptian pyramids to the present day, would occur in the last 14 seconds before midnight on December 31st. The universe is old, incomprehensibly old, old enough that stars have been born, burned for billions of years, and died, old enough that galaxies have formed, collided, merged, and formed again, old enough that the light from the most distant objects we can see has been traveling toward us for over 13 billion years, showing us the universe as it was when it was young. And yet, for all its age, the universe is still young compared to its future. If current understanding is correct, the universe will continue to exist for trillions upon trillions of years into the future, long after the last star has burned out, long after the last galaxy has faded to darkness, long after everything we know has succumbed to the relentless increase of entropy. 13.8 billion years is not the end of the story, it is barely the beginning. Fact 2. The observable universe is 93 billion light-years across. Here is a number that breaks the brain. The observable universe, the region of space from which light has had time to reach us since the Big Bang, is approximately 93 billion light-years in diameter. This number seems impossible. If the universe is only 13.8 billion years old, and light travels at a finite speed, then shouldn't the most distant objects we can see be only 13.8 billion light-years away? How can the observable universe be 93 billion light-years across? The answer is expansion. The universe is not static, it is expanding, and it has been expanding since the moment of the Big Bang. When we look at a galaxy that is, say, 13 billion light-years away, we are seeing it as it was 13 billion years ago, when the light we are now receiving first began its journey toward us. But in the 13 billion years it took that light to reach us, the universe has continued to expand, carrying that galaxy farther and farther away. Today, right now, at this very moment, that same galaxy is not 13 billion light-years away. It is approximately 46 billion light-years away, and the light we are currently seeing left it when it was much closer. The observable universe has a radius of approximately 46.5 billion light-years in every direction from Earth, giving it a total diameter of approximately 93 billion light-years. This is the cosmic horizon, the boundary beyond which objects are receding from us so quickly, due to the expansion of space itself, that their light will never reach us. Beyond this horizon lies the rest of the universe, perhaps infinite, perhaps not, which we can never observe because its light has not had time, and never will have time to reach us. The observable universe contains approximately 2 trillion galaxies. Each galaxy contains, on average, 100 to 400 billion stars. The total number of stars in the observable universe is estimated at 1024, 1 trillion trillion, or 1 septillion, or more stars than grains of sand on all the beaches on Earth. And every one of those stars, every one of those galaxies, every particle of matter, and every photon of light exists within a sphere 93 billion light-years across, embedded in a larger universe whose true size we may never know. Fact 3. The universe began with the Big Bang. 13.8 billion years ago, everything that exists, all of space, all of matter, all of energy, time itself, emerged from a state of unimaginable density and temperature in an event we call the Big Bang. The Big Bang was not an explosion in space, it was an explosion of space. Before the Big Bang there was no before, time itself did not exist. There was no space for an explosion to occur in. The Big Bang was the beginning of space and time, the moment when the universe came into existence, not as an expansion into a pre-existing void, but as the creation of the void itself. In the first fraction of a second after the Big Bang, the first 10 seconds, a period called Planck time, which is the smallest unit of time that has any physical meaning, the universe was unimaginably hot and dense. The temperature was approximately 1032 Kelvin, 100 million trillion degrees, hot enough that the fundamental forces of nature that govern the universe today were unified into a single force. Matter as we know it could not exist. Even atoms could not exist. The universe was a seething soup of fundamental particles and energy, expanding and cooling at an inconceivable rate. Then, in a process called cosmic inflation, the universe underwent a period of exponential expansion. In less than 1032 seconds, the universe expanded by a factor of at least 1026, growing from smaller than an atom to larger than a galaxy in a timespan trillions of times shorter than a blink of an eye. This inflation smoothed out the universe, making it remarkably uniform and flat, and it set the stage for everything that came after. As the universe continued to expand and cool, fundamental particles began to form, first quarks and electrons, then protons and neutrons. Within the first few minutes, nuclear fusion in the hot, dense early universe created the first atomic nuclei, primarily hydrogen and helium with trace amounts of lithium. For 380,000 years, the universe remained opaque, filled with a hot plasma of particles and radiation. Then, as the temperature dropped below about 3000 Kelvin, electrons combined with nuclei to form the first neutral atoms, a moment called recombination, and the universe became transparent. The cosmic microwave background radiation we observe today is the light from that moment, stretched and redshifted by 13.8 billion years of cosmic expansion. The Big Bang was not a theory invented to explain the universe. It is a conclusion forced upon us by the evidence. The expansion of the universe, the cosmic microwave background, the abundance of light elements, the large-scale structure of galaxies, every observation we make confirms that the universe had a beginning, and that beginning was the Big Bang. Fact 4. The universe is expanding, and the expansion is accelerating. In 1929, astronomer Edwin Hubble made one of the most important discoveries in the history of science. By measuring the light from distant galaxies, he found that nearly all of them were moving away from us, and the farther away a galaxy was, the faster it was receding. The universe was not static, it was expanding. This expansion is not galaxies moving through space like ships sailing across an ocean. It is space itself that is expanding, carrying the galaxies with it like raisins in a rising loaf of bread. The fabric of the universe is stretching, and the distances between galaxy clusters are increasing with time. For decades, astronomers assumed that the expansion of the universe must be slowing down, gradually decelerated by the gravitational attraction of all the matter pulling back on itself. The question was not whether the expansion was slowing, it was whether it was slowing enough to eventually stop and reverse, causing the universe to collapse back in on itself in a big crunch, or whether it would continue expanding forever, gradually cooling and darkening into a frozen, empty void. Then in 1998, two independent teams of astronomers studying distant supernovae made a discovery that shocked the scientific world. The expansion of the universe was not slowing down, it was speeding up. The universe was expanding faster now than it was billions of years ago, and the rate of expansion was accelerating. This discovery, which earned the 2011 Nobel Prize in Physics, revealed the existence of a mysterious force called dark energy, which makes up approximately 68% of the total energy content of the universe, and which is pushing the universe apart, overcoming the attractive force of gravity and driving an ever faster expansion. We do not know what dark energy is. We do not know why it exists. But its effects are undeniable. The universe is expanding, and it is expanding faster and faster, and galaxies that are not gravitationally bound to our own are accelerating away from us, disappearing beyond the cosmic horizon, never to be seen again. The ultimate fate of the universe depends on the nature of dark energy. If dark energy remains constant, the universe will continue expanding forever, cooling and darkening until the last stars burn out and the universe enters a state of maximum entropy called the heat death. If dark energy increases with time, the expansion could accelerate so rapidly that it tears apart galaxies, stars, planets, atoms, and even the fabric of space itself in an event called the Big Rip. The universe's fate is not yet written, but its expansion is the pen writing that fate across the cosmic page. Fact 5. There are at least 2 trillion galaxies in the observable universe. Look up at the night sky. Every point of light you see, with the exception of a few planets, is a star in our own galaxy, the Milky Way. But the Milky Way is just one galaxy among a vast multitude. Astronomers estimate that there are at least 2 trillion galaxies in the observable universe, and possibly many more. 2 trillion galaxies, each one a collection of millions, billions, or even trillions of stars. Each one a vast island of matter separated from other galaxies by distances so immense that light takes millions or billions of years to cross the space between them. Each one potentially home to planets, moons, asteroids, comets, and possibly to life. The estimate of 2 trillion galaxies comes from deep field observations made by the Hubble Space Telescope and other instruments. By pointing telescopes at apparently empty patches of sky and collecting light for days or weeks, astronomers have discovered that what appears to be darkness is actually filled with galaxies, thousands of galaxies in a region of sky no larger than a grain of sand held at arm's length. Extrapolating from these observations to the entire sky suggests a staggering number of galaxies, far more than the 200 billion previously estimated. Galaxies come in many shapes and sizes. Spiral galaxies like the Milky Way have rotating disks of stars with spiral arms winding outward from a central bulge. Elliptical galaxies are roughly spherical or football-shaped collections of stars with little gas and dust and little ongoing star formation. Irregular galaxies have no clear structure, often the result of gravitational interactions or collisions with other galaxies. And dwarf galaxies, small galaxies containing only millions to billions of stars, are the most common type, outnumbering large galaxies by a vast margin. But even 2 trillion galaxies is likely an underestimate. The observable universe has a horizon, a boundary beyond which we cannot see because light from those regions has not had time to reach us. Beyond that horizon lie more galaxies, more stars, more worlds, an unknown, perhaps infinite, expanse of universe that we can never observe. The galaxies we can see may be only a tiny fraction of all the galaxies that exist. The universe may be far, far larger than the small sphere of space we call the observable universe. 2 trillion galaxies, and we live in just one of them, on a planet orbiting an ordinary star in an ordinary region of an ordinary spiral galaxy. We are not at the center of the universe. We are nowhere special. And that fact, that overwhelming, humbling, awe-inspiring fact, is one of the greatest revelations of astronomy. Fact 6. The Milky Way contains 100 to 400 billion stars. Our home galaxy, the Milky Way, is a barred spiral galaxy approximately 100,000 light-years in diameter and containing between 100 and 400 billion stars. It is one galaxy among trillions, but it is our galaxy, the cosmic island we inhabit, the collection of stars we call home. The Milky Way is structured like a disk with spiral arms. At its center lies a dense bulge of stars and a supermassive black hole called Sagittarius A, pronounced Sagittarius A star, which has a mass approximately 4 million times that of the Sun. Surrounding the disk is a roughly spherical halo of old stars and globular clusters, dense balls of hundreds of thousands of stars, some of which are nearly as old as the universe itself. The Sun orbits the center of the Milky Way at a distance of approximately 26,000 light-years from the galactic center, moving at a speed of about 220 kilometers per second. At this speed, it takes the Sun approximately 225 to 250 million years to complete one orbit around the galaxy, a period of time called a galactic year. The Sun has completed approximately 20 to 25 orbits since it formed 4.6 billion years ago. The last time the Sun was at its current position in the galaxy, dinosaurs had not yet evolved. The continents were in different positions. Life on Earth looked completely different. And the next time the Sun completes a full orbit, 225 million years from now, Earth and everything on it will have changed beyond recognition. The Milky Way is not alone. It is part of a collection of galaxies called the Local Group, which contains approximately 54 galaxies, most of them small dwarf galaxies. The largest galaxy in the Local Group is the Andromeda Galaxy, a spiral galaxy slightly larger than the Milky Way, located approximately 2.5 million light-years away. Andromeda and the Milky Way are approaching each other at approximately 110 kilometers per second, and they are expected to collide in approximately 4.5 billion years, merging to form a single giant elliptical galaxy that astronomers have nicknamed Milkomeda. The Milky Way is beautiful when viewed from Earth, a faint band of light stretching across the night sky, visible from dark locations far from city lights. That band is the combined light of billions of stars in the galactic disk. So distant and so numerous that they blur into a continuous glow. When we look at the Milky Way, we are looking at our galaxy from inside it, seeing the edge of the disk from our position within it, gazing out at the vast collection of stars that share our cosmic home. Fact 7. Light from the most distant galaxies has been traveling for over 13 billion years. The most distant galaxies we have observed are so far away that their light has been traveling toward us for over 13 billion years. When we observe these galaxies, we are not seeing them as they are today. We are seeing them as they were more than 13 billion years ago, when the universe was less than 700 million years old, a cosmic infant compared to its current age of 13.8 billion years. This is one of the most profound implications of the finite speed of light. Light travels at approximately 300,000 kilometers per second, extremely fast by human standards, but not infinitely fast. When we look at distant objects in space, we are looking backward in time. The light from the Sun takes approximately 8 minutes to reach Earth, so we see the Sun as it was 8 minutes ago. The light from the nearest star system, Alpha Centauri, takes about 4.3 years to reach us, so we see it as it was 4.3 years ago. The light from the Andromeda Galaxy takes 2.5 million years to reach us, so we see Andromeda as it was 2.5 million years ago, before humans existed, when our ancestors were small ape-like creatures roaming the African savanna. And the light from the most distant galaxies, galaxies like GNZ11, located approximately 13.4 billion light-years away, has been traveling toward us for 13.4 billion years. When we observe GNZ11, we are seeing it as it was only 400 million years after the Big Bang, when the first galaxies were just forming, when the universe was still filled with the hydrogen and helium created in the first minutes after the beginning of time, before the heavier elements that make up planets and people had been forged in the nuclear furnaces of stars. These distant galaxies appear to us not as they are today, but as they were in the deep past, ancient light from a universe that no longer exists in the form we see it. Those galaxies have evolved, changed, aged over the billions of years their light has been traveling toward us. Some may have merged with other galaxies. Some may have been transformed by collisions or close encounters. Some may still exist, vastly changed from their ancient appearance. And some may have ceased to exist entirely, their stars exhausted, their light dimmed, their matter scattered across space. We will never know their current state, because the light showing us their present will not reach us for billions of years, and by the time it does, we will have long since ceased to exist. The universe is a time machine. Every observation we make is an observation of the past. And the deeper we look into space, the farther back in time we see, until we approach the cosmic horizon, the edge of the observable universe, beyond which lies a past so distant that its light has not yet had time to reach us. Fact 8. Most of the universe is made of dark matter and dark energy. Here is one of the most shocking revelations of modern cosmology. The atoms that make up stars, planets, gas clouds, and living beings, the ordinary matter we can see and touch, represents only about 5% of the total mass-energy content of the universe. The remaining 95% is something else entirely, mysterious substances called dark matter and dark energy that we cannot see, cannot touch, and do not fully understand. Dark matter makes up approximately 27% of the universe. It does not emit, absorb, or reflect light, making it completely invisible. We know it exists only through its gravitational effects. Dark matter holds galaxies together, bends the path of light from distant objects, and shapes the large-scale structure of the universe. Without dark matter, galaxies would fly apart, unable to hold together against the centrifugal force of their rotation. The stars in the outer regions of galaxies orbit too quickly for the visible matter alone to hold them in place. There must be additional mass, invisible mass, providing the gravitational pull needed to keep those stars bound to the galaxy. What is dark matter? We do not know. The leading hypothesis is that dark matter consists of exotic particles that interact with ordinary matter only through gravity and possibly through the weak nuclear force, particles that pass through ordinary matter like ghosts, detectable only by their gravitational influence. Experiments deep underground and in space are searching for these particles, attempting to detect the rare interactions that might occur when a dark matter particle collides with an atomic nucleus. So far, dark matter particles have not been directly detected, but their gravitational fingerprints are everywhere we look. Dark energy makes up approximately 68% of the universe. Unlike dark matter, which clumps together and exerts gravitational attraction, dark energy is uniformly spread throughout space and has a repulsive effect. It pushes things apart rather than pulling them together. Dark energy is the force driving the accelerated expansion of the universe, the reason that distant galaxies are receding from us at ever-increasing speeds. We do not know what dark energy is. It may be a property of space itself, a cosmological constant, as Einstein once proposed and then abandoned. It may be a dynamic field that changes with time, or it may be something else entirely, a phenomenon that will require new physics to explain. 5% visible matter, 27% dark matter, 68% dark energy. This is the universe we inhabit, a universe where almost everything is invisible, where the familiar stars and galaxies are a tiny minority, where the dominant constituents of reality are things we have never seen and do not understand. We live in a universe that is, in the most fundamental sense, mysterious, and that mystery is one of the greatest challenges facing science today. Fact 9. A black hole is a region of spacetime where gravity is so strong that nothing can escape. Black holes are among the most extreme and most fascinating objects in the universe. They are regions of spacetime where gravity is so strong that nothing, not matter, not light, not even information, can escape once it crosses a boundary called the event horizon. A black hole forms when a massive star, typically at least 20 to 25 times the mass of the Sun, reaches the end of its life and undergoes a catastrophic collapse. For most of a star's life, it is held up against the inward pull of gravity by the outward pressure of nuclear fusion in its core. But when the star exhausts its nuclear fuel, fusion stops, the outward pressure disappears, and gravity wins. The core of the star collapses inward with nothing to stop it, compressing matter to unimaginable densities. If the collapsing core has enough mass, the collapse does not stop. It continues until all the mass is compressed into a point of infinite density called a singularity, surrounded by an event horizon from which nothing can escape. The event horizon is not a physical surface. It is a boundary in spacetime, the point of no return, the distance from the singularity within which the escape velocity exceeds the speed of light. Outside the event horizon, it is possible, at least in principle, to escape the black hole's gravitational pull. Inside the event horizon, escape is impossible. Space itself is falling inward faster than the speed of light, carrying everything with it toward the singularity. Time and space swap roles inside the event horizon. Just as it is impossible to avoid moving forward in time outside the event horizon, it is impossible to avoid moving toward the singularity inside it. The future inside a black hole is always the singularity. Black holes come in different sizes. Stellar mass black holes, formed from the collapse of massive stars, have masses ranging from a few times to a few dozen times the mass of the Sun. Supermassive black holes, found at the centers of most large galaxies, have masses ranging from millions to billions of times the mass of the Sun. The supermassive black hole at the center of the Milky Way, Sagittarius A, has a mass approximately 4 million times that of the Sun. The supermassive black hole at the center of the galaxy, M87, famously photographed by the Event Horizon Telescope in 2019, has a mass approximately 6.5 billion times that of the Sun. Black holes are not cosmic vacuum cleaners, sucking in everything around them. Far from a black hole, gravity behaves normally. If the Sun were replaced by a black hole of the same mass, Earth's orbit would not change. But close to a black hole, gravity becomes extreme. Objects falling toward a black hole experience tidal forces so strong that they are stretched and compressed, a process called spaghettification, until they are torn apart into streams of atoms. Time slows down near a black hole. as predicted by Einstein's theory of general relativity. An observer watching something fall into a black hole would see it slow down as it approaches the event horizon, appearing to freeze at the boundary, its light redshifted to invisibility. But for the falling observer, nothing special happens at the event horizon. They cross it in a finite time, and then have only moments before reaching the singularity, where the known laws of physics break down and our understanding ends. Fact 10. Time slows down near massive objects. One of the strangest predictions of Einstein's theory of general relativity is that time is not absolute. Time passes at different rates depending on how strong the gravitational field is. Near a massive object, time slows down relative to a distant observer, a phenomenon called gravitational time dilation. This is not an illusion or a trick of perception. Time genuinely passes more slowly near a massive object. A clock placed near a black hole will tick more slowly than an identical clock far from the black hole. An astronaut orbiting close to a black hole will age more slowly than someone far away in empty space. If the astronaut spent a year orbiting near the event horizon of a supermassive black hole and then returned to a distant space station, they might find that decades or even centuries had passed for the people on the station. Gravitational time dilation is not just a theoretical curiosity, it has real, measurable effects that are important for modern technology. The Global Positioning System, GPS, relies on a network of satellites orbiting Earth, each carrying extremely precise atomic clocks. These satellites orbit at an altitude of about 20,000 kilometers, where the gravitational field is weaker than at Earth's surface. According to general relativity, the clocks on the satellites should run faster than identical clocks on the ground, and they do, by about 45 microseconds per day. If this effect were not corrected, GPS systems would accumulate errors of several kilometers per day, rendering them useless for navigation. The extreme case of gravitational time dilation occurs near black holes. Close to the event horizon, time slows down dramatically. At a distance of about 1.5 times the Schwarzschild radius, the radius of the event horizon, time runs at half the rate it does far from the black hole. At the event horizon itself, time from the perspective of a distant observer appears to stop entirely. Objects falling into a black hole appear to slow down as they approach the event horizon, their light redshifted and dimmed, until they seem to freeze at the boundary, never quite crossing it. But for the falling object, time passes normally. It crosses the event horizon in a finite time, and then falls inexorably toward the singularity. Time is not a universal, absolute flow. It is flexible, malleable, dependent on the gravitational field in which it is measured. Near massive objects, time bends just as space bends, and in the presence of extreme gravity, time can slow to a crawl or even, from an external perspective, stop entirely. Fact 11. The cosmic microwave background is the oldest light in the universe. The cosmic microwave background radiation, often abbreviated as CMB, is the oldest light in the universe, a faint afterglow of the Big Bang that fills all of space and provides a snapshot of the universe as it was approximately 380,000 years after its birth. In the first few 100,000 years after the Big Bang, the universe was too hot for neutral atoms to exist. Electrons and atomic nuclei were ionized, separated, and the universe was filled with a hot plasma that scattered photons like a thick fog scatters light. The universe was opaque. Light could not travel far before being absorbed and re-emitted by the plasma. Then, approximately 380,000 years after the Big Bang, the temperature of the universe dropped below about 3000 Kelvin, cool enough for electrons to combine with protons and helium nuclei to form the first neutral atoms, primarily hydrogen and helium. This moment is called recombination, a slightly misleading term, since the electrons and nuclei were combining for the first time, not recombining. When recombination occurred, the universe became transparent. Photons were no longer scattered by free electrons, they could travel freely through space. The light that was released at the moment of recombination has been traveling through the universe ever since, stretched and redshifted by the expansion of space, until today it reaches us as microwave radiation with a temperature of approximately 2.7 Kelvin, just a few degrees above absolute zero. The cosmic microwave background is remarkably uniform. Its temperature is the same in all directions to within 1 part in 100,000. This uniformity tells us that the early universe was extraordinarily smooth and homogeneous, consistent with the predictions of cosmic inflation, but the CMB is not perfectly uniform. Tiny temperature fluctuations, variations of only a few millionths of a degree, are imprinted on the CMB, the result of quantum fluctuations in the early universe that were stretched to cosmic scales by inflation. These fluctuations represent the seeds of all the structure we see in the universe today, the galaxies, galaxy clusters, and vast cosmic voids that fill space. Regions that were slightly denser than average in the early universe gravitationally attracted more matter, growing denser over time, eventually collapsing to form the first stars and galaxies. The cosmic microwave background has been mapped with extraordinary precision by satellites including COBE, WMAP, and Planck. These observations have allowed scientists to determine the age of the universe, the geometry of space, the density of matter and dark energy, and many other fundamental properties of the cosmos with remarkable accuracy. The CMB is the most important source of information we have about the early universe, a baby picture of the cosmos, taken when the universe was only 380,000 years old, preserved in the sky for 13.8 billion years, waiting for us to discover it. Fact 12: the universe is flat. One of the most surprising discoveries about the universe is that it appears to be flat. Not flat in the sense of being two-dimensional. The universe has 3 dimensions of space plus 1 of time, but flat in the sense that the geometry of space follows the rules of Euclidean geometry, the familiar geometry taught in high school where parallel lines never meet and the angles of a triangle add up to 180 degrees. This might seem obvious, of course space is flat, what else would it be? But according to general relativity, space can be curved. The geometry of space depends on the density of matter and energy it contains. If the density is greater than a critical value, space is positively curved, like the surface of a sphere. In a positively curved universe, parallel lines eventually converge. The angles of a triangle add up to more than 180 degrees, and the universe is finite in size. If the density is less than the critical value, space is negatively curved, like the surface of a saddle. In a negatively curved universe, parallel lines diverge. The angles of a triangle add up to less than 180 degrees, and the universe is infinite. If the density is exactly equal to the critical value, space is flat, and observations of the cosmic microwave background indicate that this is indeed the case. The critical density is approximately 5 atoms of hydrogen per cubic meter, an astonishingly low density, equivalent to about 5 protons spread across a space the size of a refrigerator. Measurements of the CMB indicate that the total density of the universe, including ordinary matter, and dark energy, is extremely close to this critical value, to within less than 1% uncertainty. The universe is flat, or so close to flat that we cannot measure the difference. Why is the universe flat? This is one of the great questions of cosmology. According to cosmic inflation, the theory that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, any initial curvature of space would have been smoothed out, making the universe extremely flat. Inflation predicts that the universe should be flat to within an extraordinarily small margin, and observations confirm this prediction. The flatness of the universe is one of the strongest pieces of evidence supporting the theory of cosmic inflation. A flat universe is also, in principle, infinite in extent. If space is flat and does not curve back on itself, then it extends forever in all directions. There is no edge, no boundary. No center. The observable universe is finite, limited by the cosmic horizon, but the universe as a whole may be infinite. Somewhere beyond the cosmic horizon, far beyond the reach of our most powerful telescopes, space may continue forever, filled with galaxies and stars and worlds that we will never see. Fact 13: stars are born in clouds of gas and dust called nebulae. Stars are not eternal. They are born, they live, and they die, and their births occur in some of the most beautiful structures in the universe. Nebulae, vast clouds of gas and dust scattered throughout galaxies. A nebula is a cloud of gas, primarily hydrogen and helium, mixed with tiny grains of dust, spread across regions of space that can be hundreds of light years across. Most of the time, the gas in a nebula is stable, held in equilibrium by the balance between gravity pulling it inward and thermal pressure pushing it outward. But when something disturbs this balance, the shockwave from a nearby supernova, the collision of 2 gas clouds, the gravitational influence of a passing galaxy, the cloud can begin to collapse. As a region of the cloud collapses under its own gravity, it fragments into smaller clumps, each clump collapsing further. The center of each clump becomes denser and hotter as gravitational potential energy is converted to thermal energy. If a clump has enough mass, at least about 8% of the mass of the Sun, the temperature and pressure at its core eventually become high enough to ignite nuclear fusion, the process by which hydrogen nuclei combine to form helium, releasing enormous amounts of energy. When fusion begins, a star is born. The process of star formation takes millions of years for a star like the Sun, but it can happen much faster for more massive stars. The most massive stars, those with dozens of times the mass of the Sun, form in only a few 100,000 years, burning bright and hot and dying in spectacular supernova explosions within a few million years of their birth. Smaller stars, like red dwarfs, take tens of millions of years to form and can burn for trillions of years, far longer than the current age of the universe. Some of the most famous nebulae are stellar nurseries, where star formation is actively occurring. The Orion Nebula, located approximately 1,340 light-years from Earth, is one of the closest and most intensely studied star-forming regions. It is visible to the naked eye as a fuzzy patch in the constellation Orion, and through a telescope reveals itself as a glowing cloud of gas, illuminated by the intense ultraviolet radiation from young, hot stars at its center. The pillars of creation, photographed by the Hubble Space Telescope in the Eagle Nebula, are towering columns of gas and dust several light-years tall where new stars are forming, their shapes sculpted by the intense radiation from nearby massive stars. Stars are the universe's way of turning simple hydrogen into complex elements. Every atom of carbon, oxygen, nitrogen, iron, every element heavier than hydrogen and helium, was created inside a star or in the explosion of a star. We are made of stardust in the most literal sense. The atoms in our bodies were forged in the nuclear furnaces of stars billions of years ago, ejected into space when those stars died, incorporated into new clouds of gas and dust, and eventually condensed to form the sun, the earth, and everything on it. We are the universe made conscious stardust contemplating itself. Fact 14: the sun will become a red giant and engulf the earth. The sun, the star that has sustained life on Earth for billions of years, is not eternal. It is approximately 4.6 billion years old, roughly halfway through its expected lifetime, and in approximately 5 billion years it will undergo dramatic changes that will transform the solar system and ultimately destroy the Earth. The sun is powered by nuclear fusion in its core, where hydrogen nuclei combine to form helium, releasing energy in the process. This energy radiates outward, providing the heat and light that make life on Earth possible. But the sun's hydrogen fuel is finite, and it is slowly being consumed. Over billions of years, helium accumulates in the sun's core while the hydrogen fusion continues in a shell around the core. In approximately 5 billion years, the hydrogen in the core will be exhausted. With no fusion to generate outward pressure, the core will begin to contract under its own gravity, becoming hotter and denser. The shell of hydrogen around the core will heat up and begin fusing more rapidly, releasing enormous amounts of energy. This energy will cause the outer layers of the sun to expand dramatically. The sun will swell into a red giant, increasing in radius until it is hundreds of times its current size. As a red giant, the sun will be large enough to engulf the orbits of Mercury and Venus, and possibly Earth as well. Even if Earth's orbit is not directly engulfed, the intense heat from the nearby red giant sun will vaporize the oceans, strip away the atmosphere, and render the planet a lifeless, scorched rock. The Earth as we know it, the blue planet, the living world, the cradle of humanity, will be destroyed. The sun will remain a red giant for approximately 1 billion years. During this time, the helium that has accumulated in the core will eventually become hot and dense enough to ignite in a process called helium flash, a runaway fusion reaction that converts helium into carbon and oxygen. After the helium in the core is exhausted, the sun will expel its outer layers in a series of pulses, creating a planetary nebula, a glowing shell of gas expanding into space, illuminated by the hot core of the dying star. What remains will be a white dwarf, a dense, Earth-sized remnant composed mostly of carbon and oxygen, slowly cooling over trillions of years until it fades to a black dwarf, a cold, dark ember of the star that once powered life on Earth. Humanity will not be here to witness the death of the sun. Long before the sun becomes a red giant, increasing solar luminosity will make Earth uninhabitable. The oceans will evaporate, the greenhouse effect will run away, and the surface temperature will rise until Earth resembles Venus. This will occur in approximately 1 to 2 billion years. If humanity survives that long, we will need to leave Earth and find a new home among the stars. The sun that gave us life will ultimately be the death of our world, but by then, if we have done our job well, we will be long gone, scattered across the galaxy, children of the sun who have grown up and moved out into the universe. Fact 15: neutron stars are the densest objects in the universe, except black holes. When a massive star, one with an initial mass between about 10 and 25 times the mass of the sun, reaches the end of its life and exhausts its nuclear fuel, its core collapses in a catastrophic implosion. If the core has a mass between about 1.4 and 3 times the mass of the sun, the collapse is halted not by nuclear fusion, but by a quantum mechanical effect called neutron degeneracy pressure. The result is an object so dense, so extreme, so alien to everyday experience that it strains the limits of physics and the imagination: a neutron star. A neutron star is the collapsed core of a dead star, composed almost entirely of neutrons packed together at nuclear density. A typical neutron star has a mass between 1.4 and 2 times the mass of the Sun, more mass than the entire Sun, compressed into a sphere only about 20 kilometers in diameter, roughly the size of a city. The density is approximately 1017 kilograms per cubic meter, comparable to the density of an atomic nucleus. A teaspoon of neutron star material, if it could somehow be brought to Earth, would weigh approximately 10 million tons, as much as a large mountain compressed into the volume of a sugar cube. The surface gravity of a neutron star is approximately 2 times 1011 times stronger than Earth's gravity. An object falling onto the surface of a neutron star would hit the surface at approximately half the speed of light, releasing more energy than a nuclear bomb. The gravitational field is so strong that it noticeably warps spacetime. Light rays are bent as they pass near the neutron star, allowing an observer to see the backside of the star around the edges, as if looking at a funhouse mirror. The escape velocity from the surface of a neutron star is approximately 100,000 kilometers per second, about 1/3 the speed of light. Neutron stars also have extraordinarily strong magnetic fields, up to 1 billion times stronger than the strongest magnetic fields created in laboratories on Earth. These magnetic fields, combined with the neutron star's rapid rotation, can accelerate particles to nearly the speed of light and generate beams of electromagnetic radiation that sweep across space like the beam from a lighthouse. If one of these beams points toward Earth, we observe it as a pulsar, a neutron star that emits regular pulses of radio waves, sometimes hundreds of times per second. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and initially nicknamed LGM-1 for Little Green Men because the regular pulses seemed almost artificial, like a signal from an alien civilization. It turned out to be something even stranger, the lighthouse beacon of a rotating neutron star, a collapsed stellar core spinning hundreds of times per second, sending pulses across the galaxy with the regularity of an atomic clock. Neutron stars are laboratories for extreme physics. They allow us to study matter under conditions that cannot be reproduced on Earth, matter compressed to nuclear density, magnetic fields of incomprehensible strength, gravitational fields strong enough to noticeably warp spacetime. They are among the strangest objects in the universe, and they are proof that the universe is far stranger than our everyday experience suggests. Fact 16. Galaxies collide and merge over hundreds of millions of years. Galaxies are not static islands floating in empty space. They move, they interact, they collide, and when they collide, the results are spectacular. Galactic collisions occur relatively frequently on cosmic timescales. Most large galaxies, including the Milky Way, have grown through mergers with smaller galaxies, cannibalizing dwarf galaxies and incorporating their stars into the larger structure. The Milky Way is currently in the process of absorbing several small satellite galaxies, including the Sagittarius dwarf elliptical galaxy, whose stars are being stretched into long streams as tidal forces from the Milky Way tear the smaller galaxy apart. When two large galaxies collide, the process takes hundreds of millions to billions of years. Despite the enormous number of stars in each galaxy, individual stars almost never collide. The distances between stars are so vast that they simply pass by each other like ships in the night. But the gravitational interactions between the galaxies distort their shapes, pulling out long tidal tails of stars, triggering bursts of star formation as gas clouds are compressed, and ultimately merging the two galaxies into a single larger galaxy. The Milky Way is currently on a collision course with the Andromeda Galaxy. The two galaxies are approaching each other at approximately 110 kilometers per second and are expected to collide in approximately 4.5 billion years. When the collision occurs, the spiral structures of both galaxies will be disrupted, their gas clouds compressed, triggering an intense burst of star formation. Over the following billions of years, the two galaxies will pass through each other, swing back under their mutual gravitational attraction, and eventually merge into a single giant elliptical galaxy. A galaxy with no spiral structure, no gas or dust, and little ongoing star formation, composed of the combined stars of the Milky Way and Andromeda orbiting in random directions around the common center. Our solar system will likely survive the collision. The Sun and its planets will be carried along with the other stars, orbiting in the merged galaxy in a different location and on a different orbit than we occupy today. The night sky will look completely different. The familiar constellations will be scrambled, new stars will be nearby, and the merged galaxy's structure will be visible from Earth, if Earth still exists, as a diffuse glow of stars in all directions rather than the narrow band of the Milky Way we see today. Galactic collisions are one of the primary mechanisms by which galaxies evolve. The universe is full of galaxies in various stages of interaction and merger, galaxies with distorted shapes, with long tidal tails of stars, with dual cores where the nuclei of two merging galaxies orbit each other, waiting for the final coalescence that will unite them into a single structure. The universe is not static. It is dynamic, violent, constantly changing, and galactic collisions are one of the most dramatic demonstrations of this dynamism. Fact 17. Supernovae are the most powerful explosions in the universe, except gamma-ray bursts. When a massive star reaches the end of its life, it dies in one of the most violent events in the universe, a supernova explosion, an event so energetic that for a brief time, a few weeks to a few months, a single dying star can outshine an entire galaxy of hundreds of billions of stars. There are two main types of supernovae. Type Ia supernovae occur in binary star systems where a white dwarf, the dense remnant of a sun-like star, accretes matter from a companion star until it reaches a critical mass of approximately 1.4 times the mass of the Sun. At this threshold, the white dwarf can no longer support itself against gravity, and carbon fusion ignites throughout the star in a runaway thermonuclear explosion that obliterates the white dwarf entirely, leaving no remnant. Type Ia supernovae are remarkably uniform in their peak brightness, making them valuable as standard candles for measuring cosmic distances. Type II supernovae, along with types Ib and Ike, occur when massive stars, typically more than 8 to 10 times the mass of the Sun, exhaust their nuclear fuel. Throughout their lives, these stars have been fusing lighter elements into heavier ones, first hydrogen into helium, then helium into carbon and oxygen, then carbon and oxygen into neon, magnesium and silicon, and finally silicon into iron. But iron is the end of the line. Fusing iron into heavier elements requires energy rather than releasing it. It is energetically unfavorable. When the core of a massive star is converted to iron, fusion stops. With no outward pressure from fusion to balance gravity, the core collapses in less than a second, compressing a mass greater than the Sun into a sphere only a few dozen kilometers across. The collapse happens so rapidly that the outer layers of the star have no time to react. They are still falling inward when the core reaches nuclear density and rebounds, sending a shockwave outward through the star. This shockwave, reinforced by an intense burst of neutrinos from the collapsing core, blows the outer layers of the star apart in an explosion that releases approximately 1044 joules of energy, more energy than the Sun will produce in its entire 10 billion year lifetime, released in a matter of seconds. A supernova can briefly outshine its entire host galaxy. The light is visible from billions of light years away. The explosion disperses the outer layers of the star into space at speeds of thousands to tens of thousands of kilometers per second, creating an expanding shell of gas called a supernova remnant. This ejected material is enriched with heavy elements created during the star's life and in the explosion itself: carbon, oxygen, silicon, iron, gold, uranium, and every other element heavier than helium. These elements are scattered into the interstellar medium, where they mix with clouds of gas and dust, and are eventually incorporated into new stars, planets, and on at least one planet we know of living beings. We are made of supernova debris. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were created in the cores of massive stars and scattered across space when those stars exploded. Supernovae are not just the death of stars. They are the forges where the elements that make up the universe are created, and without them, planets like Earth and life like us could not exist. Fact 18. The largest known star is 1,700 times larger than the Sun. The Sun is large, approximately 1.4 million kilometers in diameter, 109 times the diameter of Earth, large enough that over 1 million Earths could fit inside it. But the Sun is a relatively small star. There are stars in the universe so enormous that they dwarf the Sun the way the Sun dwarfs Earth, stars so large that if placed at the center of the solar system, they would extend beyond the orbit of Jupiter. The largest known star is UY Scuti, a red supergiant located approximately 9,500 light-years from Earth in the constellation Scutum. UY Scuti has a radius approximately 1,700 times that of the Sun, roughly 1.2 billion kilometers. If UY Scuti were placed at the center of the solar system, its surface would extend to approximately the orbit of Saturn. The Earth, orbiting inside the star, would be vaporized. Jupiter, orbiting near the star's surface, would be engulfed. Red supergiants like UY Scuti are rare and short-lived. They are evolved massive stars nearing the end of their lives, having exhausted the hydrogen in their cores, and now fusing helium and heavier elements in their interiors. The energy released by fusion in the core causes the outer layers to expand dramatically, creating a star of enormous size, but relatively low density. The outer atmosphere of a red supergiant is so tenuous that it is essentially a vacuum by Earth standards. Despite the star's enormous mass, most of the volume is nearly empty space. Red supergiants are also unstable. They pulsate, varying in brightness and size over periods of months to years. They lose mass continuously, shedding their outer layers into space in powerful stellar winds, and they are doomed to end their lives in spectacular supernova explosions. When Scuti exhausts its nuclear fuel, it will explode with a violence that will briefly outshine the entire galaxy, leaving behind either a neutron star or a black hole. The universe contains stars of extraordinary diversity. The smallest stars, red dwarfs, have masses only about 8% that of the Sun and radii smaller than Jupiter, burn their fuel so slowly that they can live for trillions of years, far longer than the current age of the universe. The largest stars, hypergiants like Scuti, have hundreds of times the mass of the Sun, burn their fuel so rapidly that they live only a few million years, and die in explosions that can be seen across the universe. Between these extremes lies a vast range of stellar types, each with its own characteristics, its own lifespan, its own ultimate fate. The universe is a laboratory of stellar evolution, and every star tells a different story. Fact 19. Space is not empty. It is filled with the interstellar medium. Space is often described as a vacuum, an empty void between the stars, but space is not truly empty. It is filled with an extraordinarily tenuous medium called the interstellar medium, ISM, a mixture of gas and dust that permeates the space between stars and galaxies. The interstellar medium is thin, far thinner than any vacuum we can create on Earth. In the densest regions of the ISM, the density is approximately 1 million atoms per cubic meter, roughly equivalent to 1 atom per sugar cube-sized volume of space. In the least dense regions, the density drops to 1 atom per cubic meter or less. For comparison, air at sea level on Earth contains approximately 1025 molecules per cubic meter. The interstellar medium is 20 orders of magnitude less dense. Despite its thinness, the interstellar medium is not negligible. It contains approximately 10 to 15% of the visible mass of a typical galaxy. It is the reservoir from which new stars form, the medium into which dying stars expel their enriched material, and the connection between generations of stars. The interstellar medium is constantly being cycled. Stars form from dense clouds of ISM, live their lives, and return their material to the ISM when they die, enriching it with heavy elements that are incorporated into the next generation of stars. The interstellar medium is also diverse. It includes cold molecular clouds, dense, dark regions where temperatures are only 10 to 20 Kelvin, and where molecules like hydrogen, carbon monoxide, and water can form, which are the sites of star formation. It includes warm neutral hydrogen, regions where temperatures are a few thousand Kelvin and hydrogen exists as neutral atoms. It includes hot ionized gas, regions heated to hundreds of thousands or millions of Kelvin by supernova shockwaves and stellar winds, which emits X-rays and fills large volumes of space. And it includes dust, tiny solid grains, typically less than a micrometer in size, composed of carbon, silicon, and other elements, which absorb and scatter starlight and play a critical role in the chemistry of space. Without the interstellar medium, galaxies would be sterile, stars would form once, live their lives and die, and no new stars could ever form. The universe would grow old and dark, filled with the remnants of the first generation of stars and nothing more. But because the interstellar medium exists, because it is constantly replenished by dying stars and constantly depleted by star formation, the cycle of stellar birth and death can continue for billions of years. The universe is not static. It is alive with the continuous recycling of matter, the transformation of gas into stars and stars into gas, the gradual enrichment of the cosmos with the heavy elements that make planets and life possible. Fact 20. We are made of atoms that are 13.8 billion years old. Every atom in your body is ancient. The hydrogen atoms, which make up about 10% of your body by mass, were created in the Big Bang, approximately 13.8 billion years ago, in the first few minutes after the universe began. These atoms are as old as the universe itself, and they have existed in one form or another since the beginning of time. The heavier atoms, carbon, oxygen, nitrogen, calcium, iron, and all the others that make up the remaining 90% of your body are younger but still extraordinarily old. They were created in the cores of massive stars that lived and died billions of years ago, long before the Sun and Earth existed. These stars fused hydrogen into helium, helium into carbon and oxygen, and continued fusing heavier and heavier elements until their cores were filled with iron. Then they exploded in supernovae, scattering their enriched material across space, where it mixed with the interstellar medium and was eventually incorporated into new clouds of gas and dust. Approximately 4.6 billion years ago, one of these clouds, enriched with the debris of countless previous generations of stars, began to collapse under its own gravity. The center of the cloud formed the Sun. The remaining material flattened into a disk and gradually coalesced into planets, moons, asteroids, and comets. The third planet from the Sun, Earth, formed from this material, inheriting the atoms that had been created in stars billions of years earlier. And eventually on Earth, some of those atoms were incorporated into living organisms. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, the iron in your blood, all were created in stars, ejected into space when those stars died, incorporated into the cloud that formed the solar system, condensed into the Earth, and finally assembled into the complex structures that make up your body. You are not separate from the universe. You are part of it. You are made of it. You are the universe looking at itself, stardust that has organized itself into a pattern complex enough to contemplate its own origin. Every breath you take, every thought you think, every emotion you feel, all are the universe experiencing itself through you. We are the cosmos made conscious, and that is one of the most profound and beautiful truths science has ever revealed. 20 facts, and the universe reveals itself as larger, older, stranger, and more magnificent than most people imagine. We have learned that the universe is 13.8 billion years old and 93 billion light years across. We have learned that it began with the Big Bang and is expanding faster and faster, driven by a mysterious dark energy we do not understand. We have learned that most of the universe is invisible, dark matter and dark energy that we can detect only through their effects on the things we can see. We have explored black holes where time stops, neutron stars compressed to the density of atomic nuclei, and supernovae that outshine entire galaxies. We have seen galaxies colliding over hundreds of millions of years and stars being born in clouds of gas and dust. We have learned that the sun will one day become a red giant and engulf the Earth, and that the atoms in our bodies were created in stars billions of years ago. And we have learned that we are made of the universe, literally, physically, made of atoms that are as old as time itself, forged in the cores of stars, scattered across space, and assembled into the extraordinary patterns that make up living beings. This is only the beginning. We have 80 more facts to explore. Now we will dive deeper into the nature of stars, galaxies, and cosmic structures. We will explore exoplanets and the search for life beyond Earth. And we will continue our journey through the greatest story ever told, the story of the universe itself. The cosmos awaits. So far, we explored the basics of the universe, its age, its size, its origin in the Big Bang. We learned that the universe is expanding and that most of it is invisible, composed of dark matter and dark energy we do not understand. We met black holes where time stops, neutron stars compressed to impossible densities, and supernovae that forge the elements we are made of. Now we go deeper. We explore the diversity of stars and the exotic worlds that orbit them. We search for life beyond Earth and confront the profound question of whether we are alone in the universe. We witness the death of stars in catastrophic explosions and the birth of new worlds from the debris. And we begin to understand the cosmic structures, galaxy clusters, superclusters, and vast cosmic voids that form the largest patterns in the universe. The universe is not just vast. It is impossibly diverse, filled with phenomena that challenge our understanding and worlds that stretch our imagination. Close your eyes, and let's continue our journey through the cosmos. Fact 21. There are more stars in the universe than grains of sand on Earth. Here is a number that captures the scale of the universe in a way that the human mind can almost grasp. There are more stars in the observable universe than there are grains of sand on all the beaches and deserts on Earth. The number of grains of sand on Earth is difficult to estimate precisely, but scientists have made reasonable approximations. If we count all the beaches, all the deserts, all the riverbeds and ocean floors where sand accumulates, the total number of grains of sand on Earth is estimated to be approximately 7.5 times 1018, 7 quintillion 500 quadrillion grains. The number of stars in the observable universe is approximately 1024, 1 septillion stars, or 1 trillion trillion. This number is derived from the estimate of 2 trillion galaxies in the observable universe, with each galaxy containing an average of 100 billion to several hundred billion stars. 1 septillion stars, more than 100,000 times more stars than grains of sand on Earth. Every grain of sand on every beach you have ever walked on every desert stretching across every continent, at the bottom of every ocean, multiply that by 100,000, and you approach the number of stars in the universe. And each of those stars is a sun, a massive ball of plasma, fusing hydrogen into helium, releasing energy that lights up space for light years in every direction. Many of those stars have planets. Some of those planets may be Earth-like, some may harbor life, and some, perhaps many, perhaps few, may be home to civilizations, to beings looking up at their own night sky, wondering if they are alone, counting the stars just as we do. The universe is not just large. It is incomprehensibly, overwhelmingly, magnificently large, and the stars are the visible proof of that enormity, scattered across space in numbers that exceed our ability to truly comprehend. Fact 22. Exoplanets are common. Thousands have been discovered. For most of human history, the only planets we knew were the ones in our own solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. The question of whether planets orbited other stars was a matter of speculation, not observation. We assumed they existed, but we had no proof. That changed in 1992, when astronomers discovered the first confirmed exoplanets, planets orbiting a pulsar, a rapidly rotating neutron star. The discovery was surprising because pulsars are the remnants of supernova explosions, and it seemed unlikely that planets could survive such a violent event. But the data were clear. 2 planets, and possibly a third, were orbiting the pulsar PSR B1257+12, detected through the tiny variations in the pulsar's radio signal caused by the planet's gravitational influence. The first exoplanet orbiting a Sun-like star was discovered in 1995, 51 Pegasi b, a gas giant planet roughly half the mass of Jupiter, orbiting its star every 4.2 days. The discovery was revolutionary, and it opened the floodgates. Over the following decades, thousands of exoplanets were discovered using a variety of detection methods. The radial velocity method, which detects the wobble of a star caused by an orbiting planet; the transit method, which detects the tiny dimming of a star when a planet passes in front of it; and direct imaging, which captures actual photographs of planets orbiting distant stars. The Kepler Space Telescope, launched in 2009, revolutionized exoplanet science. By continuously monitoring the brightness of over 150,000 stars, Kepler discovered over 2,600 confirmed exoplanets and identified thousands more candidates awaiting confirmation. The Transiting Exoplanet Survey Satellite, TESS, launched in 2018, has continued this work, discovering thousands of additional exoplanets closer to Earth and more accessible for detailed study. As of the mid-2020s, over 5,000 exoplanets have been confirmed, with thousands more candidates awaiting verification. These planets exhibit extraordinary diversity. Some are gas giants larger than Jupiter, orbiting their stars in a matter of days, so-called hot Jupiters that are tidally locked, with one side perpetually facing their star and baked to temperatures exceeding 1,000 degrees Celsius. Some are rocky planets similar in size to Earth, orbiting in their star's habitable zone, the region where temperatures allow liquid water to exist on the surface. Some are super-Earths, rocky planets larger than Earth but smaller than Neptune. And some are unlike anything in our solar system, planets with exotic compositions, unusual orbits, or conditions we never imagined. The discovery of exoplanets has answered one profound question. Planets are common. Most stars have planets. The galaxy is full of worlds: rocky worlds, gas giants, ice giants, lava worlds, water worlds, planets orbiting binary stars, planets orbiting dead stars, planets in systems so different from our own that they challenge our understanding of how planets form. The universe is not a barren void. It is filled with worlds beyond counting, and the implications for the existence of life beyond Earth are staggering. Fact 23. The habitable zone is where life as we know it could exist. Not all planets are suitable for life, at least not for life as we know it. Life on Earth requires liquid water, and liquid water can exist only within a certain range of temperatures and pressures. Too close to the star, and water boils away into vapor. Too far from the star, and water freezes into ice. The region around a star where temperatures are just right for liquid water to exist on a planet's surface is called the habitable zone, or the Goldilocks zone. Not too hot, not too cold, but just right. The habitable zone depends on the star's temperature and brightness. A hot, bright star like a blue giant has a habitable zone far from the star, spanning a wide range of distances. A cool, dim star like a red dwarf has a habitable zone much closer to the star, spanning a narrow range. For a Sun-like star, the habitable zone extends from approximately 0.95 to 1.4 astronomical units, AU, from the star, roughly from the orbit of Venus to just beyond the orbit of Earth. Earth orbits at 1 AU, placing it comfortably within the habitable zone. Mars orbits at 1.5 AU, just outside the habitable zone, and Venus orbits at 0.72 AU, too close to the Sun for liquid water to exist on its surface today. But the habitable zone is not a guarantee of habitability. Venus is closer to the Sun than the habitable zone allows, and its surface temperature is approximately 465 degrees Celsius, hot enough to melt lead, due to a runaway greenhouse effect. Mars is just outside the habitable zone and is too cold for liquid water to exist on its surface today, though evidence suggests it once had rivers, lakes, and possibly oceans billions of years ago when its atmosphere was thicker. Earth is in the habitable zone and has abundant liquid water, but it also has a protective magnetic field, a stable climate, and an atmosphere that regulates temperature, factors that are critical for habitability, but not guaranteed by orbital distance alone. Despite these caveats, the habitable zone is a useful concept for identifying exoplanets that might support life. Astronomers have discovered dozens of exoplanets orbiting within the habitable zones of their stars, worlds like Proxima Centauri b, a rocky planet orbiting the nearest star to the Sun, Kepler 452b, a planet slightly larger than Earth orbiting a Sun-like star in the habitable zone, and TRAPPIST-1e, F, and G, 3 of 7 planets orbiting a cool red dwarf star, all of which are roughly Earth-sized and located in or near the habitable zone. These planets are not necessarily habitable. We do not yet know if they have atmospheres, liquid water, or conditions suitable for life, but they are candidates, worlds where life as we know it could potentially exist, waiting to be studied in greater detail by the next generation of telescopes. The search for habitable exoplanets is one of the most exciting frontiers in astronomy, and the discoveries of the past 2 decades have shown that habitable zone planets are not rare. They are out there orbiting stars across the galaxy, waiting for us to find them. Fact 24, the Drake equation, estimates the number of communicative civilizations in the galaxy. In 1961, astronomer Frank Drake formulated an equation to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. The Drake equation is not a precise scientific formula. It is more of a framework for thinking about the problem of alien life, organizing our ignorance into a series of factors that we can try to estimate. The equation is n equals r times fp times n times fl times phi times fc times l, where n equals the number of civilizations in the Milky Way with which we might be able to communicate. R equals the rate of star formation in the galaxy. Fp equals the fraction of stars that have planetary systems. N equals the number of planets per solar system that could support life. Fl equals the fraction of those planets where life actually develops. Phi equals the fraction of life-bearing planets where intelligent life evolves. Fc equals the fraction of intelligent civilizations that develop technology capable of interstellar communication. L equals the length of time such civilizations release detectable signals into space. Some of these factors are now reasonably well understood. The rate of star formation in the Milky Way is approximately 1 to 3 new stars per year. The fraction of stars with planetary systems is high. Kepler data suggest that most stars have planets. The number of planets per system in the habitable zone is estimated at 0.4 to several, depending on assumptions. But the remaining factors, the fraction of habitable planets where life develops, where intelligent life evolves, where technology develops, and the lifespan of communicative civilizations are completely unknown. We have only one data point, Earth. Life developed on Earth relatively quickly after the planet cooled and became habitable, suggesting that the origin of life might be common. But intelligent life took billions of years to evolve, suggesting it might be rare. Technological civilization on Earth is less than 200 years old and has already developed the capability to destroy itself, raising questions about how long such civilizations typically survive. Estimates of n, the number of communicative civilizations in the galaxy, range from less than 1, meaning we are alone, to millions, meaning the galaxy is teeming with life. We do not know which estimate is correct. We do not have enough information to solve the Drake equation with confidence. But the equation is valuable not because it gives us an answer, but because it frames the question. It tells us what we need to know to determine whether we are alone. And every discovery we make, every exoplanet we find, every biosignature we detect, every signal we search for, is a step towards solving the greatest mystery of all. Are we the only intelligence in the universe, or are we part of a vast community of civilizations scattered across the stars? Fact 25, we have sent messages into space, and we are listening for replies. Humanity has been broadcasting radio signals into space for over a century. Every radio transmission, every television broadcast, every radar pulse leaks into space and travels outward at the speed of light, creating an expanding bubble of electromagnetic radiation that announces our presence to the cosmos. By now, our earliest radio signals have traveled over 100 light-years from Earth, reaching thousands of nearby star systems. If any of those systems harbor intelligent life with radio technology, they could, in principle, detect our presence. But most of our radio leakage is unintentional and weak, difficult to detect at interstellar distances. So in 1974, humanity made the first deliberate attempt to send a message to potential extraterrestrial civilizations. The Arecibo message, transmitted from the Arecibo radio telescope in Puerto Rico, was a short radio signal containing encoded information about Earth, humanity, and our location in the galaxy. The message was broadcast toward the globular star cluster M13, approximately 25,000 light-years away, and will arrive in approximately 25,000 years. A reply, if any, would arrive 50,000 years from now. Other messages have followed. The Voyager Golden Records, attached to the Voyager 1 and Voyager 2 spacecraft launched in 1977, carry sounds and images selected to represent the diversity of life and culture on Earth, along with instructions for how to play the records encoded in symbols. The spacecraft are now beyond the edge of the solar system, traveling through interstellar space, carrying humanity's message to any civilization that might intercept them millions or billions of years from now. And we are listening. The search for extraterrestrial intelligence, SETI, is an ongoing effort to detect signals from alien civilizations by monitoring radio frequencies for patterns that could indicate artificial origin. SETI projects use large radio telescopes to scan the sky, looking for narrow bandwidth signals, repeating patterns, or other anomalies that natural sources do not produce. Despite decades of searching, no confirmed alien signal has been detected, but the search continues, expanding to new frequencies, new search strategies, and new technologies. Some scientists have raised concerns about broadcasting our presence to the cosmos. If hostile civilizations exist, revealing our location might be dangerous. Others argue that remaining silent is pointless, our radio leakage has already announced us, and that attempting contact is worth the risk. The debate is unresolved, but the fact remains. We have sent messages into space, and we are listening for replies. If anyone is out there, listening as we are listening, broadcasting as we are broadcasting, we may one day receive the signal that changes everything, proof that we are not alone. Fact 26. A gamma-ray burst could sterilize half the Earth. Gamma-ray bursts, GRBs, are the most energetic explosions in the universe, releasing more energy in a few seconds than the Sun will produce in its entire 10 billion-year lifetime. They are detected approximately once per day somewhere in the observable universe, brief flashes of gamma radiation that announce the death of massive stars or the merger of neutron stars billions of light-years away. There are two main types of gamma-ray bursts. Short-duration GRBs, lasting less than 2 seconds, are believed to be produced by the merger of two neutron stars or a neutron star and a black hole, events that also produce gravitational waves detectable by instruments like LIGO. Long-duration GRBs, lasting more than 2 seconds and sometimes for several minutes, are produced by the collapse of extremely massive stars more than 30 times the mass of the Sun, in a type of supernova called a hypernova or collapsar. When a gamma-ray burst occurs, it releases two narrow beams of intense gamma radiation along the star's rotation axis. If one of these beams points toward Earth, we detect the gamma-ray burst. If the beam points in another direction, we see nothing. The explosion is just as energetic, but the radiation is beamed away from us. This means that the gamma-ray bursts we detect are only a tiny fraction of all the gamma-ray bursts that occur. Most are invisible to us because their beams point elsewhere. But what if a gamma-ray burst occurred nearby, say, within 6,000 light-years of Earth, and one of its beams pointed directly at us? The consequences would be catastrophic. The intense gamma radiation would strip away Earth's ozone layer within seconds, exposing the surface to lethal levels of ultraviolet radiation from the Sun. Photochemical reactions in the atmosphere would produce nitrogen oxides that would further damage the ozone layer and create a brown haze that could persist for years, blocking sunlight and cooling the planet. Marine phytoplankton, the microscopic organisms that produce much of Earth's oxygen and form the base of the ocean food web, would die in massive numbers. The food chain would collapse. Mass extinction would follow. There is evidence that gamma-ray bursts may have contributed to past mass extinctions on Earth. The Ordovician extinction, approximately 450 million years ago, which killed approximately 85% of marine species, coincides with evidence of increased ultraviolet radiation and atmospheric disruption consistent with a nearby gamma-ray burst. Fortunately, gamma-ray bursts are rare, and nearby gamma-ray bursts are extremely rare. The beaming effect means that only a tiny fraction of gamma-ray bursts are visible to us, and the vast majority occur in distant galaxies billions of light-years away. The probability of a gamma-ray burst occurring close enough to Earth to cause significant damage and pointed in our direction is estimated to be very low, approximately one event every few 100 million years, but it is not zero. Somewhere in the galaxy, there are massive stars nearing the end of their lives, stars that will collapse into black holes and release beams of gamma radiation powerful enough to sterilize any planet in their path. We cannot predict when or where the next nearby gamma ray burst will occur. We can only hope that when it happens, its beam is pointed somewhere else. Fact 27. Light from the sun takes 8 minutes to reach Earth, but 100,000 years to escape the sun's core. The sun is approximately 150 million kilometers from Earth, a distance called 1 astronomical unit, AU. Light travels at approximately 300,000 kilometers per second, so light from the sun takes approximately 8 minutes and 20 seconds to reach Earth. When you look at the sun, please do not look directly at the sun. You are seeing it as it was 8 minutes ago. But the light that reaches Earth did not begin its journey 8 minutes ago. It began its journey approximately 100,000 to 200,000 years ago, deep in the core of the sun, where nuclear fusion produces the energy that powers the sun and lights up the solar system. In the sun's core, where temperatures reach 15 million degrees Celsius, and the pressure is 250 billion times Earth's atmospheric pressure, hydrogen nuclei collide with enough energy to overcome their electromagnetic repulsion and fuse into helium. This fusion releases energy in the form of gamma-ray photons, extremely high-energy particles of light. These photons carry the energy outward from the core, but they cannot travel in a straight line. The sun's interior is incredibly dense, filled with matter that absorbs and re-emits photons countless times. Each time a photon is absorbed by an atom and re-emitted, it emerges in a random direction with slightly less energy. The photon takes a random walk through the sun's interior, traveling only a tiny distance before being absorbed again. The path length between absorptions is called the mean free path, and in the sun's core it is only about 1 centimeter. A photon must take trillions upon trillions of tiny steps, each in a random direction, to work its way from the core to the surface, a journey of 696,000 kilometers, but traveled in a zigzag path that is vastly longer. The time it takes for a photon to diffuse from the core to the surface depends on the random walk process and is estimated to be approximately 100,000 to 200,000 years. By the time the photon reaches the surface, it has lost so much energy through repeated absorption and re-emission that it is no longer a gamma-ray photon. It has been downgraded to visible light, the yellow-white light we see when we look at the sun. So the sunlight warming your face, the light illuminating the day, the energy that powers photosynthesis and drives Earth's climate, that light was created in the sun's core approximately 100,000 years ago, when early humans were just beginning to migrate out of Africa, when the last ice age had not yet begun, when the world looked utterly different from today. The light took 100,000 years to escape the sun, and then 8 minutes to cross the void of space and reach Earth. The sun is ancient, but the light it produces is older still. Fact 28. The universe has no center and no edge. One of the most difficult concepts in cosmology is that the universe has no center and no edge. This seems impossible. Everything we experience in daily life has boundaries, has a center, has limits. How can the universe not? The key is to understand that the universe is not an object sitting in space. It is space itself. When we say the universe is expanding, we do not mean that galaxies are moving through space like dots on a balloon that is being inflated from the inside. We mean that space itself is expanding, carrying the galaxies with it. Imagine the surface of a balloon as it is inflated. Draw dots on the balloon to represent galaxies. As the balloon expands, the dots move apart, not because they are moving across the surface, but because the surface itself is stretching. Now ask, where is the center of the balloon's surface? The answer is that there is no center on the surface. Every point on the surface is equivalent. An ant walking on the balloon's surface would never find an edge or a center. It would just walk around and around, eventually returning to its starting point. The universe is similar, but in 3 dimensions instead of 2. Space is expanding in all directions, and every point in space sees every other point moving away from it. There is no center to the expansion. Every galaxy sees itself as the stationary reference point and sees all other galaxies moving away. And there is no edge to the universe. Space does not end somewhere, and if you traveled far enough, you would not hit a wall or a boundary. You might eventually return to your starting point if the universe is finite and curved back on itself, or you might travel forever if the universe is infinite. Current observations suggest that the universe is flat or very nearly flat, which implies that it is either infinite in extent or extraordinarily large, far larger than the observable universe. If the universe is infinite, then it has always been infinite, even at the moment of the Big Bang. The Big Bang was not an explosion that occurred at a single point in space. It was the beginning of space and time everywhere, simultaneously. Infinity does not grow from finiteness. An infinite universe was infinite even when it was hot and dense and young. This is difficult to visualize and our intuitions fail us, but the mathematics is clear and the observations support it. The universe has no center, it has no edge. It is either infinite or so large that we will never see its boundaries. And every point in the universe, including the point where you are sitting right now, is as much the center of the universe as any other point. We are not at a special location. We are not near the edge or the center. We are simply here in a universe that extends equally in all directions, without limit and without boundary. Fact 29, some stars are older than the universe, or so it seemed. In the 1990s, astronomers had a problem. They were measuring the ages of the oldest known stars, ancient red giants and white dwarfs in globular clusters, and finding ages of 14 to 16 billion years. But they were also measuring the age of the universe using the Hubble constant, the rate of cosmic expansion, and finding an age of approximately 9 to 12 billion years. The stars appeared to be older than the universe itself, which is impossible. Something was wrong with the measurements. The resolution came from multiple sources. Improved measurements of the Hubble constant using the Hubble Space Telescope reduced uncertainties in the expansion rate. Observations of distant supernovae revealed that the universe's expansion is accelerating due to dark energy, which changes the relationship between expansion rate and age. And observations of the cosmic microwave background by the WMAP and Planck satellites provided an independent, highly accurate measurement of the universe's age. The current best estimate is that the universe is 13.787 billion years old, with an uncertainty of only about 20 million years. The oldest stars, remeasured with improved distance estimates and stellar evolution models, are approximately 13 to 13.5 billion years old, comfortably younger than the universe, as they must be. But the episode illustrates an important point about science. When observations conflict, something is wrong with our understanding, and we must revise our models until the observations agree. For a few years, it appeared that stars might be older than the universe, a paradox that demanded resolution. The resolution came not from abandoning observations, but from improving them, from questioning assumptions, from measuring more carefully. And the result is a consistent picture of the universe's age and the ages of its oldest stars, all fitting together into a coherent timeline of cosmic history. Fact 30, Saturn's rings are temporary. They will disappear in 100 million years. Saturn is one of the most beautiful objects in the solar system, instantly recognizable by its magnificent ring system, a vast, flat disk of ice particles, rock fragments, and dust extending from 7,000 kilometers to over 280,000 kilometers from the planet's center. The rings are thin, only about 10 to 100 meters thick in most places, but they span a distance greater than the distance from Earth to the Moon. Saturn's rings are not solid. They are composed of countless individual particles, each ranging in size from microscopic dust grains to house-sized boulders, all orbiting Saturn independently. The particles are primarily water ice, with some contamination from rock and organic compounds that give the rings a slight yellowish tint in some regions. But Saturn's rings are not permanent. They are being destroyed by two processes: ring rain and gravitational interactions. Ring rain occurs when charged particles from Saturn's magnetic field interact with the ring particles, ionizing them and causing them to spiral inward along Saturn's magnetic field lines, eventually falling into the planet's atmosphere. Observations by the Cassini spacecraft, which orbited Saturn from 2004 to 2017, revealed that Saturn is losing ring material at a rate of approximately 10,000 kilograms per second, enough to fill an Olympic swimming pool in half an hour. At this rate, the rings could be entirely gone in approximately 100 million years. Gravitational interactions with Saturn's moons also contribute to the ring's loss. Some ring particles are ejected outward by gravitational resonances with moons like Enceladus and Titan, while others are pulled inward and collide with the planet. 100 million years seems like a long time, but on cosmic timescales it is brief. Dinosaurs roamed Earth 100 million years ago. If the rings are disappearing this quickly, they cannot be as old as Saturn itself, approximately 4.6 billion years. They must be much younger, perhaps only a few hundred million years old, formed relatively recently, in cosmic terms, by the breakup of a moon or comet that wandered too close to Saturn and was torn apart by tidal forces. We are lucky to live at a time when Saturn has rings. Future astronomers, hundreds of millions of years from now, will look at Saturn and see a ringless planet, perhaps with a faint dusty remnant, but nothing like the spectacular ring system we observe today. The rings are temporary, a fleeting phenomenon in the solar system's history, and we are witnessing them at their peak. Fact 31, Jupiter has protected Earth from asteroid impacts. Jupiter, the largest planet in the solar system, with a mass more than twice that of all the other planets combined, has played a critical role in shaping the history of life on Earth, not through any direct influence, but through its gravitational effects on asteroids and comets in the solar system. Jupiter orbits the Sun at approximately 5.2 astronomical units, far beyond the asteroid belt that lies between Mars and Jupiter. Its enormous mass creates a powerful gravitational field that influences the orbits of smaller objects throughout the solar system. When an asteroid or comet passes near Jupiter, its trajectory can be dramatically altered. Some objects are flung out of the solar system entirely, ejected into interstellar space, while others are deflected into new orbits. This gravitational influence has two effects. First, Jupiter acts as a shield, reducing the number of asteroids and comets that reach the inner solar system where Earth orbits. Objects that might otherwise have struck Earth are instead captured by Jupiter's gravity or ejected from the solar system. Second, Jupiter occasionally sends objects inward, increasing the impact rate on the inner planets. The net effect is complex, but most models suggest that Jupiter has reduced the long-term impact rate on Earth, making large impacts less frequent than they would otherwise be. Without Jupiter, Earth might have experienced far more asteroid and comet impacts throughout its history. Some of these impacts could have been catastrophic, sterilizing the surface or disrupting the climate severely enough to prevent the evolution of complex life. Jupiter's presence has not eliminated impacts. The Chicxulub impact 66 million years ago, which contributed to the extinction of the dinosaurs, is proof of that, but it has reduced their frequency, creating a more stable environment for life to evolve. Jupiter is sometimes called Earth's guardian, and while the metaphor is imperfect, there is truth to it. The giant planet has shaped the solar system's architecture, clearing out much of the debris left over from the solar system's formation and protecting the inner planets from at least some of the bombardment they would otherwise have experienced. Life on Earth owes its existence to many factors, and Jupiter's gravitational influence is one of them. Fact 32. There are rogue planets wandering the galaxy without stars. Not all planets orbit stars. Some planets have been ejected from their star systems by gravitational interactions, cast out into the darkness of interstellar space to wander the galaxy alone. These rogue planets, also called free-floating planets, drift through the void, untethered to any star, experiencing no day or night, no seasons, no warming sunlight, only the eternal cold of deep space. Rogue planets are difficult to detect because they emit no light of their own and do not pass in front of a star to create a detectable transit. But they can be detected through gravitational microlensing, a phenomenon predicted by Einstein's general relativity, where the gravity of a massive object bends the light from a background star, temporarily brightening it as the object passes in front. If the lensing object is a rogue planet, the brightening is brief and has a characteristic signature that allows astronomers to estimate the planet's mass. Observations using gravitational microlensing suggest that rogue planets may be common, possibly as common as stars. The Milky Way may contain billions or even trillions of rogue planets, outnumbering the planets that orbit stars. Most of these rogue planets are likely gas giants, ejected from their star systems during the chaotic early period of planetary formation, when gravitational interactions between planets were frequent and violent. But some may be rocky planets, Earth-sized or larger, wandering the galaxy without a sun. What would a rogue planet be like? Without a star to warm it, the surface would be frozen, with temperatures only a few degrees above absolute zero, far too cold for liquid water or life as we know it. But a massive rogue planet might have enough internal heat from radioactive decay or residual heat from its formation to maintain a subsurface ocean beneath a thick layer of ice, similar to the moons Europa and Enceladus in our own solar system. If such an ocean existed, it might, in principle, harbor life that has never seen sunlight, life that evolved in darkness, sustained by chemical energy from the planet's interior rather than by photosynthesis. Rogue planets are wanderers, drifting through the galaxy for billions of years, sometimes passing through star systems and being captured into new orbits, sometimes colliding with stars or other planets, sometimes simply moving through the void forever, alone in the darkness. They are a reminder that planets are not always bound to stars, and that the universe contains objects and environments far stranger than the familiar solar system we call home. Fact 33. Betelgeuse will explode as a supernova, possibly soon. Betelgeuse is one of the brightest stars in the night sky, a red supergiant located approximately 650 light-years from Earth in the constellation Orion. It is easily visible to the naked eye as the reddish star marking Orion's right shoulder from our perspective, and it is one of the few stars large enough that its surface has been directly imaged by telescopes. Betelgeuse is enormous, approximately 900 times the diameter of the Sun. If placed at the center of the solar system, its surface would extend beyond the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars entirely. It is a massive star, with an initial mass estimated at 15 to 20 times that of the Sun, and it is nearing the end of its life. Betelgeuse has exhausted the hydrogen in its core and is now fusing heavier elements, helium, carbon, oxygen, in a series of reactions that are gradually building up an iron core. When the iron core reaches a critical mass, it will collapse catastrophically, and Betelgeuse will explode as a type II supernova. When will this happen? We do not know. The supernova could occur tomorrow, or it could occur 100,000 years from now. The uncertainty is large because we do not fully understand the final stages of massive stellar evolution. But on cosmic timescales, Betelgeuse's explosion is imminent. The star is unstable, pulsating irregularly, and in late 2019 and early 2020, it underwent a dramatic dimming event, dropping to approximately 40% of its normal brightness before recovering. The dimming was caused by a large ejection of material from the star's surface, which cooled and condensed into dust that temporarily blocked our view of the star. For a few months, some astronomers wondered if the dimming might signal an impending supernova, but the star recovered, and it appears that the explosion has not yet begun. When Betelgeuse does explode, the event will be spectacular. The supernova will be bright enough to be visible during the day, comparable in brightness to the full moon, and it will remain visible to the naked eye for weeks or months before gradually fading. It will be the closest supernova observed in modern times and one of the brightest in recorded history. Astronomers will study it intensely, gathering data that will improve our understanding of supernova mechanisms and stellar evolution. And for people around the world, it will be a reminder that the universe is dynamic and violent, that stars are born and die, and that the night sky we think of as unchanging is in fact constantly evolving. Betelgeuse's supernova will not threaten Earth. At 650 light-years distance, the explosion is far enough away that the radiation will be harmless, a beautiful show in the sky with no danger to life on our planet. But it will be a moment to remember, a moment when a star that has shone in the sky for all of human history suddenly ends its life in a blaze of light that will be visible across the galaxy. Fact 34. There is a giant void in space called the Boötes void. The universe is not uniformly filled with galaxies. Galaxies are distributed in a cosmic web, a large-scale structure of filaments, walls, and clusters, separated by vast regions of nearly empty space called cosmic voids. The largest of these voids is the Boötes void, a region of space approximately 330 million light-years in diameter, located in the direction of the constellation Boötes. The Boötes void was discovered in 1981 by astronomer Robert Kirshner and his colleagues during a survey of galaxy redshifts. In most regions of space, galaxies are distributed relatively evenly, with typical separations of a few million light-years. But when Kirshner's team surveyed the Boötes region, they found almost nothing, a vast spherical volume of space containing far fewer galaxies than expected, as if something had scooped out a huge cavity in the universe. The Boötes void contains approximately 60 known galaxies within a volume that, if filled at the average density of the universe, should contain approximately 2,000 galaxies. It is not completely empty, it is simply far less dense than typical regions of space. The galaxies that do exist in the void are mostly small, dim dwarf galaxies, and they are distributed in a thin shell near the void's edge rather than throughout its interior. Cosmic voids are a natural consequence of the large-scale structure of the universe. In the early universe, tiny density fluctuations, regions that were slightly denser or slightly less dense than average, were amplified by gravity over billions of years. Denser regions attracted more matter, growing into filaments and clusters of galaxies. Less dense regions became voids, as matter drained out of them and into the surrounding denser regions. The result is the cosmic web we observe today, a foam-like structure with galaxies clustered along filaments and walls, separated by vast empty voids. The Boötes void is sometimes called the Great Void or the Great Nothing, and it is a humbling reminder of the scale of cosmic structures. A void 330 million light-years across, a region so large that light takes 330 million years to cross it, a volume so vast that it could contain tens of thousands of galaxies, but instead contains only a few dozen. The universe is not just large. It is structured on scales that dwarf individual galaxies, scales where the building blocks are not stars but galaxy clusters, and the empty spaces are voids larger than anything the human mind can easily grasp. Fact 35. Gravity waves ripple through spacetime. On September 14, 2015, at 09:50:45 UTC, detectors at the Laser Interferometer Gravitational Wave Observatory, LIGO in Louisiana and Washington recorded a signal that had traveled 1.3 billion years to reach Earth. The signal lasted only a fraction of a second, a rapid increase in frequency and amplitude, ending in a sudden cutoff, but it represented one of the most important scientific discoveries of the century. LIGO had detected gravitational waves, ripples in the fabric of spacetime itself, produced by the merger of two black holes approximately 1.3 billion light-years away. The black holes, with masses of approximately 36 and 29 times the mass of the Sun, had spiraled inward over millions or billions of years, their orbits decaying as they radiated energy in the form of gravitational waves. In the final moments before the merger, they circled each other hundreds of times per second, warping spacetime so violently that they generated gravitational waves powerful enough to be detected across the universe. When they merged, approximately 3 solar masses of energy, the equivalent of 3 entire suns, was converted into gravitational wave energy and radiated into space in less than a second. Gravitational waves are a prediction of Einstein's general theory of relativity. According to relativity, mass and energy warp the geometry of spacetime, and accelerating masses produce ripples in this geometry that propagate at the speed of light. For a century after Einstein's prediction, gravitational waves remained undetected, not because they do not exist, but because they are extraordinarily weak. Even the most violent events in the universe, supernovae, colliding black holes, merging neutron stars, produce gravitational waves that distort spacetime by only a tiny fraction when they reach Earth. LIGO detects gravitational waves using laser interferometry. Each LIGO detector consists of 2 4-kilometer-long arms arranged in an L shape. A laser beam is split and sent down both arms, reflected by mirrors at the ends, and recombined. If a gravitational wave passes through, it stretches space in one direction and compresses it in the perpendicular direction, changing the lengths of the arms by a minuscule amount, approximately 1/10,000th the diameter of a proton. This tiny change shifts the phase of the laser beams, creating an interference pattern that the detectors can measure. Since the first detection in 2015, LIGO and its partner detector Virgo in Italy have detected dozens of gravitational wave events, including mergers of black holes, mergers of neutron stars, and at least one event consistent with the merger of a neutron star and a black hole. The detection of gravitational waves from neutron star mergers has been particularly significant because neutron star collisions also produce electromagnetic radiation, light, allowing astronomers to observe the same event using both gravitational waves and traditional telescopes, a new field called multi-messenger astronomy. Gravitational wave astronomy is opening a new window on the universe, allowing us to observe events and objects that are invisible or nearly invisible to traditional telescopes. Black hole mergers produce no light, but they produce gravitational waves that can be detected across the universe. Neutron star mergers produce both gravitational waves and light, allowing us to study them in unprecedented detail. And in the future, space-based gravitational wave detectors like LISA will detect lower-frequency gravitational waves from even more exotic sources, supermassive black hole mergers, the background hum of gravitational waves from the early universe, and perhaps signals from events we have not yet imagined. The universe is speaking to us in a new language, and we have only just learned to listen. Fact 36. Voyager 1 has left the solar system and entered interstellar space. On August 25, 2012, a spacecraft launched from Earth 35 years earlier crossed an invisible boundary and entered a region of space where no human-made object had ever traveled. Voyager 1, a robotic probe the size of a small car, passed through the heliopause, the boundary where the solar wind from the Sun gives way to the interstellar medium, and became the first human artifact to leave the solar system and enter interstellar space. Voyager 1 was launched on September 5, 1977, as part of a dual mission with its twin, Voyager 2, to explore the outer planets. The spacecraft flew by Jupiter in 1979 and Saturn in 1980, returning stunning images and data that revolutionized our understanding of these giant worlds and their moons. After completing its primary mission, Voyager 1 continued outward, its trajectory taking it out of the plane of the solar system and toward the heliopause. The heliopause is the boundary where the solar wind, a stream of charged particles flowing outward from the Sun at approximately 400 kilometers per second, is stopped by the pressure of the interstellar medium, the tenuous gas that fills the space between stars. Inside the heliopause, the environment is dominated by particles from the Sun. Outside the heliopause, the environment is dominated by particles from interstellar space. Crossing the heliopause is not like crossing a border on Earth. There is no sign, no gate, no visible change. But instruments on Voyager 1 detected the transition. The density of solar wind particles dropped dramatically, and the density of cosmic rays from interstellar space increased. Voyager 1 is now approximately 24 billion kilometers from Earth, over 160 times the distance from Earth to the Sun, and moving away at approximately 17 kilometers per second. Radio signals from the spacecraft, traveling at the speed of light, take over 22 hours to reach Earth. The spacecraft is powered by 3 radioisotope thermoelectric generators, RTGs, which convert heat from the decay of plutonium-238 into electricity. The RTGs are slowly losing power as the plutonium decays, and by the mid-2020s, Voyager 1 will no longer have enough power to operate any of its scientific instruments. Eventually, the spacecraft will go silent, drifting through interstellar space, carrying with it the golden record, a message from humanity to any civilization that might one day find it. Voyager 1 will continue its journey for millions or billions of years, long after the human civilization that built it has ceased to exist. In approximately 40,000 years, it will pass within 1.6 light-years of the star Gliese 445. In hundreds of millions of years, it may pass through other star systems, silent and dark but still carrying humanity's message. Voyager 1 is not just a spacecraft. It is an emissary, a time capsule, a monument to the species that built it and sent it on an endless journey to the stars. Fact 37. The Hubble Deep Field revealed thousands of galaxies in a patch of empty sky. In 1995, astronomers made a decision that seemed at first almost reckless. They pointed the Hubble Space Telescope at a tiny patch of apparently empty sky in the constellation Ursa Major, a region no larger than a grain of sand held at arm's length, and exposed the camera for 10 days, collecting every photon of light from that tiny region. The region was chosen specifically because it appeared empty. There were no bright stars, no known galaxies, nothing obvious to observe. The goal was to see what might be revealed if you looked long enough and deep enough into the darkness. What Hubble found was extraordinary. The resulting image, called the Hubble Deep Field, revealed approximately 3,000 galaxies in that tiny patch of sky. Galaxies of every type and shape, from spirals to ellipticals to irregular blobs. Galaxies so distant that their light had been traveling for billions of years. Galaxies showing us the universe as it was when it was young. Some of the galaxies were so faint that they could not be seen in any previous observation. The light from the most distant galaxies in the image had been traveling for over 12 billion years, showing us those galaxies as they were less than 2 billion years after the Big Bang. The Hubble Deep Field demonstrated that what appears to be empty space is actually filled with galaxies, faint, distant, invisible to the naked eye and to most telescopes, but they're nonetheless. If you take any random patch of apparently empty sky and look long enough, you will find thousands or tens of thousands of galaxies. The universe is not a mostly empty void with a few scattered galaxies. It is densely packed with galaxies, and the only reason we do not see them everywhere we look is that most are too faint and too distant to be visible without powerful telescopes and long exposures. Since the original Hubble Deep Field, astronomers have created deeper images, the Hubble Ultra Deep Field, the Hubble Extreme Deep Field, revealing progressively fainter and more distant galaxies. The current record is the James Webb Space Telescope's Deep Field images, which have detected galaxies formed only a few 100 million years after the Big Bang. Galaxies that are now so distant that their light has been stretched by cosmic expansion into the infrared, invisible to optical telescopes, but detectable by Webb's infrared instruments. The Deep Field images are among the most important images in the history of astronomy. They have shown us that the universe is vast beyond imagining, filled with galaxies beyond counting, and that every point in the sky, even the darkest, most apparently empty regions, contains wonders waiting to be revealed. Fact 38. Antimatter exists, but almost all of it has disappeared. For every particle of matter in the universe, every electron, every proton, every neutron, there exists an antimatter counterpart with the same mass but opposite charge. The antiparticle of the electron is the positron, with the same mass but positive charge instead of negative. The antiparticle of the proton is the antiproton, with the same mass but negative charge instead of positive. And when a particle meets its antiparticle, they annihilate each other, converting their mass entirely into energy, according to Einstein's equation E equals mc2. Antimatter is not theoretical. It exists and can be created in laboratories on Earth. Particle accelerators routinely produce antimatter particles by colliding high-energy particles together, and positrons are used in medical imaging techniques like PET scans, but antimatter is extraordinarily rare in the universe. The observable universe is made almost entirely of matter, with only tiny amounts of antimatter produced by high-energy processes like cosmic ray collisions or radioactive decay. This raises one of the greatest mysteries in physics. Why is there so much matter and so little antimatter? According to the standard model of particle physics and our understanding of the Big Bang, matter and antimatter should have been created in exactly equal amounts in the early universe. In the first moments after the Big Bang, temperatures were so high that particles and antiparticles were constantly being created from pure energy and annihilating back into energy. As the universe expanded and cooled, the creation stopped, and the particles and antiparticles should have annihilated each other completely, leaving a universe filled with energy but no matter. But that is not what happened. Somehow there was a tiny imbalance. For every billion antimatter particles, there were 1,000,000,001 matter particles. When the matter and antimatter annihilated, that tiny excess of matter survived, and it is that excess that makes up everything we see today, all the galaxies, stars, planets, and people. Why was there an imbalance? We do not know. The current best hypothesis is that some process in the early universe violated the symmetry between matter and antimatter, producing slightly more matter than antimatter. This process, called baryogenesis, is not fully understood, and it remains one of the great unsolved problems in physics. The absence of antimatter in the universe is fortunate for us. If matter and antimatter had been created in exactly equal amounts, they would have annihilated completely, and the universe would contain only radiation, no atoms, no stars, no life. We exist because of an asymmetry we do not fully understand, a tiny imbalance in the earliest moments of the universe that allowed matter to survive. The universe is stranger than we know, and the greatest mysteries are often hidden in the questions we have not yet learned to answer. Fact 39. There may be a ninth planet beyond Neptune. For over a decade, astronomers have been accumulating evidence for something strange in the outer reaches of the solar system. Several small icy objects orbiting far beyond Neptune, objects in the Kuiper belt, the region of icy debris beyond the orbit of the eighth planet, have orbits that are unexpectedly clustered. Their orbits are oriented in similar directions and tilted at similar angles, a pattern that is statistically unlikely to occur by chance. In 2016, astronomers Konstantin Batygin and Michael Brown proposed an explanation. The orbits are being influenced by the gravity of an as yet undiscovered planet, a world with a mass approximately 5 to 10 times that of Earth, orbiting the Sun at a distance of 400 to 800 astronomical units, 10 to 20 times farther from the Sun than Neptune. This hypothetical world has been nicknamed Planet 9. If Planet 9 exists, it would be a super-Earth, a planet larger than Earth but smaller than Neptune, a type of planet that is common around other stars but absent from our own solar system. It would orbit the Sun once every 10,000 to 20,000 years, far too slowly for its motion to be detected in the sky over human lifetimes. And it would be extraordinarily faint. At such a great distance from the Sun, it would reflect very little sunlight and would be barely detectable, even by the most powerful telescopes. Despite extensive searches, Planet 9 has not been found. Telescopes have surveyed large areas of the sky where the planet might be, but the outer solar system is vast, and a faint, slow-moving object is easy to miss. The evidence for Planet 9 is indirect: the clustering of orbits, the existence of objects with extreme orbits that are difficult to explain without an additional planet, but it is not conclusive. Some astronomers argue that the clustering could be a statistical fluke, or the result of observational bias. Others propose alternative explanations, such as a disk of small objects whose collective gravity mimics the influence of a single large planet. The search continues. Future telescopes, including the Vera Rubin Observatory, will survey the entire visible sky repeatedly, creating a time-lapse movie of the heavens that will reveal moving objects far too faint to detect with current instruments. If Planet 9 exists, it will be found. If it does not exist, the evidence will eventually point to an alternative explanation for the orbital clustering. The solar system may have 9 planets after all, or it may not. Either way. The search for Planet 9 is a reminder that even our own cosmic backyard contains mysteries waiting to be solved. Fact 40. The universe's fate depends on dark energy. The ultimate fate of the universe, how it will end, what will happen to all the galaxies and stars and planets in the incomprehensibly distant future, depends on a single question: what is dark energy, and how will it behave over time? If dark energy is a cosmological constant, a property of space itself that does not change with time, then the universe will continue expanding forever, and the expansion will continue to accelerate. Galaxies that are not gravitationally bound to our own will recede beyond the cosmic horizon, their light redshifted into invisibility. Star formation will gradually cease as the supply of gas is exhausted. Existing stars will burn out, one by one, over trillions of years. The universe will grow dark and cold, filled with the remnants of dead stars, white dwarfs, neutron stars, black holes, drifting through an ever-expanding void. Eventually, even the black holes will evaporate through Hawking radiation, a quantum process that causes black holes to slowly lose mass and eventually disappear. The universe will reach a state of maximum entropy, a condition called the heat death, where no energy is available to do work and nothing can ever happen again. If dark energy increases with time, the expansion will accelerate more and more rapidly, eventually becoming so fast that it tears apart structures that are currently held together by gravity. First, galaxy clusters will be torn apart as the expansion overpowers the gravity holding them together. Then galaxies themselves will be disrupted, their stars scattered into the expanding void. Then solar systems will be torn apart, planets ripped away from their stars. Finally, atoms themselves will be torn apart as space expands faster than the forces holding them together. This scenario is called the Big Rip, and it would occur approximately 22 billion years from now if dark energy behaves in this way. If dark energy decreases with time or reverses sign, the expansion could slow and eventually stop, and gravity could take over, pulling all the matter in the universe back together in a big crunch, the opposite of the Big Bang, a collapse to infinite density and temperature, possibly followed by a new Big Bang and a new cycle of expansion. We do not know which scenario is correct because we do not know what dark energy is or how it will behave. Current observations suggest that dark energy is consistent with a cosmological constant, which implies an eternally accelerating expansion and eventual heat death. But the uncertainty is large, and future observations may reveal that dark energy is something else entirely. The fate of the universe is not yet written. It will be determined by the nature of dark energy, and we are only beginning to understand what that nature might be. The universe will end, all things end, but how it will end, and when, and what, if anything, comes after, remain among the deepest mysteries in all of science. 40 facts, and the universe reveals itself as even more extraordinary than we imagined. We have learned that there are more stars than grains of sand on Earth, that exoplanets are common, and some orbit in habitable zones where life might exist. We have explored gamma-ray bursts powerful enough to sterilize planets, antimatter that should have annihilated all matter, but left a tiny excess that became everything we see, and gravitational waves that ripple through spacetime from colliding black holes billions of light years away. We have watched Saturn's rings disappearing, seen Voyager 1 leave the solar system, and glimpsed thousands of galaxies in patches of sky that appeared empty. We have learned that Jupiter has protected Earth from impacts, that some stars are older than we once thought the universe was, and that the ultimate fate of everything depends on the mysterious dark energy we do not yet understand. Now we will explore more cosmic mysteries, the nature of time, the quantum fabric of reality, the possibility of other universes. The journey continues. The universe is calling, and we have only just begun to answer. So far, we explored the basics, the universe's age, its size, the Big Bang that began it all. We learned that most of the universe is invisible, composed of dark matter and dark energy we cannot see or touch. Then we discovered exoplanets orbiting distant stars, searched for signs of extraterrestrial intelligence, and witnessed the violent deaths of stars in supernovae and gamma-ray bursts. We learned that Saturn's rings are temporary, that Jupiter has protected Earth, and that Voyager 1 has crossed into interstellar space. Now we venture into the truly strange. We explore the nature of time itself, the quantum realm where particles exist in multiple states simultaneously, and the possibility that our universe is not the only one. We confront the paradoxes of black holes, the mysteries of dark matter, and the question of what came before the Big Bang. And we begin to understand that the universe is not just stranger than we imagine, it is stranger than we can imagine. Close your eyes, prepare for the descent into the deepest mysteries, and let's continue. Fact 41. Time runs slower on Earth's surface than in orbit. Time is not absolute. It does not flow at the same rate everywhere in the universe. According to Einstein's theory of general relativity, time passes more slowly in stronger gravitational fields, and this effect, called gravitational time dilation, is not a theoretical curiosity, but a measured, confirmed phenomenon with practical consequences. On Earth's surface, where the gravitational field is relatively strong, time passes more slowly than it does in orbit, where the gravitational field is weaker. The difference is tiny, approximately 45 microseconds per day, but it is real and measurable. The Global Positioning System, GPS, must account for this time dilation to function accurately. GPS satellites orbit at an altitude of approximately 20,000 kilometers, where Earth's gravitational field is weaker than at the surface. The atomic clocks on the satellites therefore run faster than identical clocks on the ground by about 45 microseconds per day due to gravitational time dilation. There is also a special relativistic effect due to the satellite's motion that causes their clocks to run slower by about 7 microseconds per day, but the net effect is that satellite clocks run fast. If this time dilation were not corrected, GPS systems would accumulate errors of several kilometers per day, making them useless for navigation. The fact that GPS works, that you can use your phone to navigate to an address with meter-level accuracy, is practical proof that time dilation is real. The effect becomes more extreme near more massive objects. Near a neutron star, time runs noticeably slower than far from the star. Near a black hole, time slows dramatically. At the event horizon of a black hole, time from the perspective of a distant observer appears to stop entirely. An astronaut falling into a black hole would appear to an outside observer to slow down as they approach the event horizon, their image freezing at the boundary, their light redshifted to invisibility. But for the astronaut, time would pass normally. They would cross the event horizon in a finite time and fall toward the singularity. Time is not a river that flows at a constant rate. It is flexible, variable, dependent on gravity and motion. And that flexibility, that strangeness, is woven into the very fabric of the universe. Fact 42, quantum mechanics says particles can be in 2 places at once. At the smallest scales, the scales of atoms and subatomic particles, the universe behaves in ways that defy common sense and challenge our intuitions about what is real. This is the domain of quantum mechanics, the theory that describes the behavior of matter and energy at the atomic and subatomic level, and it is one of the strangest and most successful theories in all of science. One of the core principles of quantum mechanics is superposition, the idea that a quantum particle can exist in multiple states simultaneously until it is observed or measured. A particle can be in 2 places at once. It can be spinning both clockwise and counterclockwise at the same time. It can be both a particle and a wave until something forces it to choose. This is not a metaphor or a philosophical interpretation. It is what the mathematics of quantum mechanics predicts, and it is what experiments confirm. In the famous double-slit experiment, particles such as electrons are fired one at a time toward a barrier with 2 slits. If you do not observe which slit the particle passes through, it behaves as if it passes through both slits simultaneously, creating an interference pattern on a screen behind the barrier, a pattern that can only be explained if each particle interferes with itself, existing in a superposition of passing through both slits. But if you observe which slit the particle passes through, the interference pattern disappears, and the particle behaves as if it passed through only one slit. The act of observation collapses the superposition, forcing the particle to choose a definite state. Quantum superposition is not limited to simple particles. Larger systems can also exist in superposition states, though maintaining superposition becomes more difficult as systems become larger and more complex. Experiments have demonstrated superposition in molecules containing dozens of atoms, and in principle, the laws of quantum mechanics allow even macroscopic objects to exist in superposition, though no one has yet succeeded in observing a cat that is simultaneously alive and dead, as in Schrödinger's famous thought experiment. Quantum mechanics works. It makes predictions that have been confirmed to extraordinary precision. The entire modern technology of semiconductors, lasers, and quantum computers depends on quantum mechanical effects. But understanding what quantum mechanics means, what it tells us about the nature of reality, remains one of the deepest philosophical challenges in science. Does a particle really exist in multiple states at once, or is superposition just a mathematical description of our ignorance? What causes the collapse of the wave function when a measurement is made? Is there a boundary between the quantum world and the classical world, or is everything, even us, fundamentally quantum? These questions have no agreed-upon answers. The universe, at its smallest scales, is stranger than we can fully comprehend. Fact 43, the Heisenberg uncertainty principle, sets fundamental limits on knowledge. One of the most profound and unsettling principles in quantum mechanics is the Heisenberg uncertainty principle, which states that there are fundamental limits to how precisely we can know certain pairs of properties of a particle. The more precisely you know a particle's position, the less precisely you can know its momentum, mass times velocity, and vice versa. This is not a limitation of our measuring instruments or our technology. It is a fundamental property of nature. The uncertainty principle is often written as deltax times delta greater or equal to letter 210f/2, where deltax is the uncertainty in position, delta is the uncertainty in momentum, and letter 210f h-bar is the reduced Planck constant, a fundamental constant of nature. The product of the uncertainties has a minimum value. You cannot simultaneously know both position and momentum with infinite precision. If you measure position exactly, momentum becomes completely uncertain, and vice versa. This principle applies to other pairs of properties as well, energy and time, for example. The more precisely you know the energy of a system, the less precisely you can know when that energy was measured. This has strange consequences. For extremely short periods of time, the uncertainty in energy becomes large, allowing the creation of particle-antiparticle pairs from the vacuum. Virtual particles that pop into existence, exist for a tiny fraction of a second, and then annihilate back into nothingness. This process is happening constantly, everywhere in space, even in what we call a vacuum. Empty space is not truly empty. It is a seething foam of virtual particles appearing and disappearing, a quantum fuzz that underlies all of reality. The uncertainty principle tells us that the universe is fundamentally fuzzy at the smallest scales. There is no such thing as a particle with a perfectly defined position and momentum. Particles are described by wave functions, mathematical objects that give the probability of finding the particle in different locations with different momenta, and these wave functions spread out over space and time. The universe at the quantum level is not deterministic and clockwork-like, as classical physics assumed. It is probabilistic, uncertain, governed by chance as much as by law. This has philosophical implications that are still debated. If the future is not determined by the present, if quantum events are truly random, then does free will exist? Or are we, like everything else, subject to the probabilistic laws of quantum mechanics? The answers remain unclear, but the uncertainty principle itself is not in doubt. It has been confirmed by countless experiments, and it is a cornerstone of our understanding of the quantum world. Fact 44, entanglement, allows particles to affect each other instantly across any distance. One of the strangest predictions of quantum mechanics, and one that Einstein himself refused to accept, calling it spooky action at a distance, is quantum entanglement. When two particles are entangled, measuring the state of one particle instantaneously affects the state of the other, no matter how far apart they are. The particles are correlated in a way that cannot be explained by any local hidden variable theory. They behave as if they are part of a single system, even when separated by light years of space. Here is a simplified example. Imagine two particles are created in an entangled state such that their spins are always opposite. If one is spinning up, the other is spinning down. Before measurement, each particle is in a superposition, spinning both up and down simultaneously. But the moment you measure one particle and find it spinning up, the other particle's spin immediately becomes down, not because any signal traveled between them, but because they are entangled. The measurement of one particle collapses the wave function of both particles, instantly determining the state of the distant particle. This seems to violate the principle that information cannot travel faster than light, a cornerstone of Einstein's theory of special relativity, but entanglement does not allow faster-than-light communication. You cannot use entanglement to send a message, because the result of the measurement on the first particle is random. You cannot control whether you get spin up or spin down. The person measuring the second particle sees a random result as well. Only when you compare the results later, using conventional, slower-than-light communication, do you discover that the results were correlated. No information is transmitted instantaneously, only the correlation exists. Entanglement has been experimentally confirmed in countless tests, including experiments where entangled particles were separated by hundreds of kilometers. In 2022, the Nobel Prize in Physics was awarded to Elaine Aspect, John Clauser, and Anton Zeilinger for experiments that definitively ruled out local hidden variable theories and confirmed the reality of quantum entanglement. Entanglement is not just a laboratory curiosity. It is being used to develop new technologies, including quantum cryptography, which uses entangled particles to create theoretically unbreakable codes, and quantum computers, which use entanglement to perform calculations that would be impossible for classical computers. The universe is entangled at the deepest level. Particles separated by vast distances can be part of a single quantum system, influencing each other in ways that defy our classical intuitions about space and time. Fact 45, black holes may not destroy information. It may be encoded on the event horizon. One of the most profound puzzles in theoretical physics is the black hole information paradox. According to quantum mechanics, information cannot be destroyed. If you know the complete state of a system at one time, you can, in principle, calculate its state at any other time. But black holes seem to destroy information. When matter falls into a black hole, it disappears beyond the event horizon, and all the information about its state, its quantum properties, its history, appears to be lost forever. This creates a paradox. If black holes destroy information, quantum mechanics is violated. But if information is not destroyed, where does it go? It cannot escape from inside the event horizon, because nothing can escape from a black hole. The solution, proposed by physicists including Leonard Susskind, Gerard T. Hooft, and Stephen Hawking, who reversed his earlier position on the issue, is the holographic principle. The holographic principle states that all the information about the three-dimensional volume inside a black hole is encoded on the two-dimensional surface of the event horizon, much like a hologram encodes a three-dimensional image on a two-dimensional surface. When matter falls into a black hole, its information is not lost, it is imprinted on the event horizon. The event horizon acts like a vast information storage device. With each bit of information encoded in an area approximately the size of a Planck length squared, the Planck length is the smallest distance that has any meaning in physics, approximately 1035 meters. As the black hole evaporates through Hawking radiation, a quantum process in which black holes emit particles and slowly lose mass, the information is gradually released back into the universe in the form of the radiation. The holographic principle has deep implications beyond black holes. Some physicists believe it applies to the universe as a whole, that all the information in the three-dimensional universe we observe is encoded on a two-dimensional boundary at the edge of space. The universe we experience, with its 3 dimensions of space, might be a holographic projection from a low-dimensional reality. This idea is speculative and far from proven, but it has become a major area of research in theoretical physics, connecting quantum mechanics, general relativity, and string theory in unexpected ways. Black holes are not just exotic objects at the edge of physics. They are laboratories for testing our deepest theories about the nature of reality, information, and the structure of spacetime itself. Fact 46: dark matter makes up 27% of the universe, but we have never directly detected it. We have known for nearly a century that most of the matter in the universe is invisible. The evidence is overwhelming. Galaxies rotate too fast to be held together by the gravity of their visible matter alone. Galaxy clusters contain far more mass than can be accounted for by stars and gas. The gravitational lensing of light from distant objects reveals the presence of mass that emits no light. All of this points to the existence of dark matter, matter that does not interact with electromagnetic radiation, light, but does exert gravitational force. Dark matter makes up approximately 27% of the total mass-energy content of the universe, more than 5 times as much as the ordinary matter, protons, neutrons, electrons, that makes up stars, planets, gas clouds, and living beings. Without dark matter, galaxies would not have formed. The gravity of ordinary matter alone is insufficient to pull matter together fast enough to form the galaxies we observe. Dark matter provides the gravitational scaffolding around which galaxies form. It clumps together first, creating gravitational wells into which ordinary matter falls, eventually collapsing to form stars and galaxies. But despite decades of searching, we have never directly detected a dark matter particle. We do not know what dark matter is made of. The leading candidates are WIMPs, weakly interacting massive particles, hypothetical particles that interact with ordinary matter only through gravity and possibly through the weak nuclear force. Experiments in deep underground laboratories are searching for these particles by trying to detect the rare collisions that might occur when a dark matter particle strikes an atomic nucleus. So far, no confirmed detection has been made. Other candidates for dark matter include axions, hypothetical particles predicted by some extensions of particle physics, primordial black holes formed in the early universe, not from the collapse of stars, and more exotic possibilities like dark photons or sterile neutrinos. Some physicists have proposed alternative theories of gravity that might eliminate the need for dark matter, but these theories have difficulty explaining all the observations that dark matter explains so naturally. Dark matter is one of the greatest mysteries in physics. We know it exists, the evidence is undeniable. We know how much of it there is, approximately 5 times as much as ordinary matter. We know where it is surrounding galaxies, filling the space between galaxy clusters, forming the large-scale structure of the universe, but we do not know what it is. And until we detect it directly or develop a better theory that explains the same observations without it, dark matter will remain one of the universe's deepest secrets. Fact 47: the multiverse theory suggests our universe is one of many. The concept of the multiverse, the idea that our universe is not the only one, but one of many or even infinitely many universes, has moved from the realm of science fiction to serious scientific consideration over the past few decades. Several independent lines of reasoning in physics suggest that multiple universes might exist, though the evidence is indirect and the concept remains controversial. One version of the multiverse arises from cosmic inflation, the theory that the universe underwent exponential expansion in the first fraction of a second after the Big Bang. According to eternal inflation models, inflation does not happen just once, it happens continuously in different regions of space. Our universe is a region where inflation stopped and normal expansion took over, but beyond our cosmic horizon, inflation continues, creating new bubble universes constantly. Each bubble universe might have different physical laws, different fundamental constants, different properties, forming a vast multiverse of diverse universes, most of which would be unobservable from our own. Another version arises from quantum mechanics. The many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957, suggests that every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. When you measure a particle's spin and find it spinning up, there is another branch of the universe where you found it spinning down. Every quantum event creates new universes, and the multiverse contains all possible histories, all possible outcomes, all possible versions of reality. A third version arises from string theory, which proposes that the fundamental constituents of reality are not particles, but tiny vibrating strings of energy. String theory requires extra dimensions of space beyond the three we observe, and the way these extra dimensions are compactified, curled up to sizes too small to detect, determines the properties of particles and forces in that universe. The number of possible compactifications is enormous, estimated at 10^500 or more, leading to the string theory landscape, a vast collection of possible universes with different physical laws. The multiverse is not directly testable. By definition, other universes are beyond our cosmic horizon and cannot be observed. But some versions of the multiverse make indirect predictions that might be testable. For example, if our universe collided with another bubble universe in the distant past, the collision might have left an imprint on the cosmic microwave background that we could detect. Searches for such imprints have been conducted, but have found nothing conclusive. The multiverse remains speculative. Some physicists embrace it as a natural consequence of our best theories. Others reject it as untestable metaphysics, not science. But the idea refuses to go away, and it raises profound questions. If the multiverse exists, is our universe special, or are we just one of countless universes, most of which might be lifeless and empty? And if infinite universes exist, does that mean everything that can happen does happen somewhere? Fact 48: Hawking radiation means black holes eventually evaporate. In 1974, Stephen Hawking made one of the most surprising discoveries in theoretical physics. Black holes are not entirely black. They emit radiation, now called Hawking radiation, and over incomprehensibly long timescales, this radiation causes black holes to evaporate completely. Hawking radiation arises from quantum effects near the event horizon. According to quantum mechanics, the vacuum is not truly empty. It is filled with virtual particle-antiparticle pairs that constantly pop into existence and annihilate back into nothingness. Normally, these virtual particles exist for such a short time that they have no observable effect. But near the event horizon of a black hole, something strange happens. One particle of a virtual pair can fall into the black hole while the other escapes. To an outside observer, this appears as if the black hole has emitted a particle Hawking radiation. The energy for this radiation comes from the black hole's mass. Each emitted particle slightly reduces the black hole's mass, causing it to shrink. The rate of emission is extraordinarily slow for large black holes. A black hole with the mass of the Sun would emit Hawking radiation at a temperature of only about 10 Kelvin, far colder than the cosmic microwave background, and would take approximately 1067 years to evaporate. But smaller black holes emit more radiation. The smaller the black hole, the hotter it gets and the faster it evaporates. A black hole with the mass of a mountain would evaporate in a fraction of a second, releasing as much energy as billions of nuclear bombs. As a black hole evaporates, it gets smaller and hotter, and the rate of evaporation accelerates. In the final moments, the black hole radiates enormous amounts of energy and then disappears in a final burst of radiation. What remains is unclear. Some theories suggest that a tiny remnant might be left behind, while others predict complete evaporation. Hawking radiation has never been directly observed. The effect is far too weak for any existing black hole to be detected. But it is a firm prediction of quantum field theory in curved spacetime, and most physicists accept it as real. It has profound implications. It means that black holes are not eternal. They will eventually evaporate, returning their mass energy to the universe. And it connects quantum mechanics and general relativity in a way that hints at a deeper theory, a theory of quantum gravity that would unify the two great pillars of modern physics. Fact 49: We are made of star material, literally. This is not a poetic metaphor. It is a literal, physical fact. Every atom in your body heavier than hydrogen and helium was created inside a star or in the explosion of a star. Hydrogen and helium, the two lightest elements, were created in the Big Bang in the first few minutes after the universe began. But everything else, carbon, oxygen, nitrogen, iron, calcium, phosphorus, every element that makes up your body was created later, through nuclear fusion in the cores of stars or in the violent explosions of supernovae. During a star's life, nuclear fusion in its core converts hydrogen into helium, then helium into carbon and oxygen, and in massive stars, the fusion continues, creating neon, magnesium, silicon, and eventually iron. Elements heavier than iron cannot be created by fusion in stellar cores. Creating them requires more energy than the fusion releases. These heavier elements, including gold, platinum, uranium, and others, are created in supernova explosions or in the mergers of neutron stars, where the extreme temperatures and pressures allow nuclear reactions that would be impossible in normal stellar cores. When a massive star explodes as a supernova, it scatters these newly created elements across space. The gas and dust enriched with heavy elements mix with the interstellar medium, forming new clouds of gas that will eventually collapse to form new stars and planets. The Sun and its planets, including Earth, formed from such a cloud approximately 4.6 billion years ago, a cloud that had been enriched by the deaths of previous generations of stars. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, the iron in your blood, all were forged in the nuclear furnaces of stars that lived and died billions of years ago. You are made of atoms that were once part of distant stars, atoms that traveled across space for billions of years before coming together to form you. This connection is profound. We are not separate from the universe. We are part of it. We are the way the universe looks at itself. Every breath you take contains atoms that were once inside stars. Every thought you think is the product of billions of atoms working together, atoms that began their journey in the hearts of dying stars and that will, one day, return to the cosmos when you die. We are stardust, and that fact is one of the most beautiful truths science has ever revealed. Fact 50, the cosmic microwave background has a temperature of 2.7 Kelvin. The cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, has a temperature of approximately 2.725 Kelvin, or about minus 270 degrees Celsius. This is only 2.7 degrees above absolute zero, the coldest temperature theoretically possible. When the CMB was released, approximately 380,000 years after the Big Bang, it had a temperature of about 3,000 Kelvin, hot enough to glow visibly, like the surface of a cool star. But as the universe expanded, the wavelength of the CMB photons was stretched by the expansion of space, shifting the radiation from visible light to infrared to microwaves. Today, the CMB is invisible to the naked eye. It is microwave radiation, with wavelengths of approximately 1 to 2 millimeters, far too long for our eyes to detect. The CMB is extraordinarily uniform. Its temperature is the same in all directions to within 1 part in 100,000. This uniformity tells us that the early universe was remarkably smooth and homogeneous, consistent with the predictions of cosmic inflation. But the CMB is not perfectly uniform. Tiny temperature fluctuations, variations of only a few millionths of a degree, are visible in detailed maps of the CMB. These fluctuations represent regions of the early universe that were slightly denser or slightly less dense than average, and they are the seeds from which all the structure in the universe today, galaxies, galaxy clusters, cosmic voids, eventually grew. The temperature of the CMB will continue to decrease as the universe expands. In the far future, trillions of years from now, the CMB will have cooled to a fraction of a degree above absolute zero, and eventually it will become so faint that it will be undetectable. The universe will grow darker and colder, and the afterglow of the Big Bang will fade into silence. Fact 51, neutron stars are so dense a teaspoon weighs a billion tons. We have mentioned neutron stars before, but their density deserves emphasis because it is so extreme that it defies comprehension. A neutron star is the collapsed core of a massive star, compressed by gravity to densities comparable to the density of an atomic nucleus. To understand this, consider that atoms are mostly empty space. The nucleus of an atom, containing protons and neutrons, occupies only about 10 of the atom's volume. The rest is empty space occupied by electrons. In a neutron star, this empty space has been crushed out. The electrons have been forced to combine with protons, forming neutrons, and these neutrons are packed together as tightly as the particles in an atomic nucleus. The density of a neutron star is approximately 4 times 1017 kilograms per cubic meter. A teaspoon of neutron star material, approximately 5 milliliters, would have a mass of approximately 2 times 1012 kilograms, or about 2 billion tons. This is roughly the mass of 3,000 Empire State Buildings, compressed into a volume the size of a teaspoon. If you could somehow transport a teaspoon of neutron star material to Earth, it would fall through the Earth like a stone through water, punching a hole clean through the planet, and oscillating back and forth through the Earth's core until friction slowed it down and it settled at the center. The gravitational pull of such a dense object would be immense. Anything nearby would be pulled toward it with tremendous force. Neutron stars are laboratories for extreme physics. The density, the pressure, the gravitational field, all are far beyond anything we can recreate on Earth or study in any other astrophysical context, except black holes. The matter inside a neutron star is in a state called neutron degenerate matter, held up against further collapse not by thermal pressure or electromagnetic forces, but by neutron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, which forbids identical fermions, like neutrons, from occupying the same quantum state. At the very center of the most massive neutron stars, the density may be so high that neutrons themselves break down, forming exotic states of matter like quark matter, where quarks, the fundamental particles that make up protons and neutrons, exist freely rather than being bound inside nucleons. We do not know for certain what happens at these densities. The physics is at the edge of what we understand. Neutron stars are the universe's way of showing us what matter does under the most extreme conditions imaginable. Fact 52, the Sun loses 4 million tons of mass every second. The Sun is powered by nuclear fusion, the conversion of hydrogen into helium in its core, releasing energy in the process. Every second, approximately 600 million tons of hydrogen are fused into approximately 596 million tons of helium. The missing 4 million tons are converted into energy, according to Einstein's famous equation E = mc2. 4 million tons of mass converted to energy every second. This is an enormous amount, equivalent to the energy of approximately 90 billion nuclear bombs. This energy radiates outward from the Sun's core, takes approximately 100,000 years to diffuse through the Sun's interior, and then streams into space as sunlight. Despite losing 4 million tons per second, the Sun is so massive that this mass loss is negligible on human timescales. The Sun's total mass is approximately 2 times 1030 kilograms, 2,000 trillion kilograms. At a loss rate of 4 million tons per second, the Sun would need to burn for approximately 150 trillion years to lose just 1% of its mass. Since the Sun is only about 4.6 billion years old, and will burn for another 5 billion years or so before running out of hydrogen, the total mass loss over the Sun's lifetime is only a tiny fraction of its total mass. But the mass loss is enough to have measurable effects. As the Sun loses mass, its gravitational pull on the planets weakens slightly, causing their orbits to expand slowly over time. Earth's orbit is increasing by approximately 1.5 centimeters per year, a tiny amount, but measurable with precise astronomical observations. The Sun's mass loss also affects the solar wind, the stream of charged particles flowing outward from the Sun at speeds of approximately 400 kilometers per second. As the Sun loses mass, the solar wind carries some of this mass into space, along with energy and magnetic fields. The solar wind shapes the heliosphere, the bubble of space surrounding the solar system, beyond which lies interstellar space. Every second, the Sun is consuming itself, converting its substance into light and heat and radiation that streams across the solar system and beyond. We live on the energy of a dying star, a star that burns itself away slowly, steadily, inexorably, until one day it will exhaust its fuel and begin the transformation that will end the world we know. Fact 53, space is not empty, it is filled with the quantum vacuum. Empty space, the vacuum of the universe, is not truly empty. According to quantum mechanics, the vacuum is filled with fluctuating electromagnetic fields, virtual particles that pop into existence and disappear, and a background energy that permeates all of space. This quantum vacuum is one of the strangest predictions of quantum field theory, and it has observable consequences. One consequence is the Casimir effect. If you place two uncharged metal plates very close together in a vacuum, they will experience a tiny attractive force pulling them together. This force arises because the space between the plates can support only certain wavelengths of virtual photons, while the space outside the plates can support all wavelengths. The difference in the number of virtual photons creates a pressure imbalance, pushing the plates together. The Casimir effect has been measured in laboratories and confirms the reality of the quantum vacuum. Another consequence is vacuum energy, a background energy density associated with empty space. In quantum field theory, the vacuum is not at zero energy. It has a baseline energy level that cannot be removed. The exact value of this vacuum energy is uncertain, but if it exists, it would contribute to the total energy density of the universe. Some physicists believe that dark energy, the mysterious force driving the accelerated expansion of the universe, may be vacuum energy, though the theoretical predictions for vacuum energy are many orders of magnitude larger than the observed value of dark energy, creating a major unsolved problem in physics. The quantum vacuum is also responsible for spontaneous emission, the phenomenon where an excited atom can emit a photon and drop to a lower energy state even in the absence of any external radiation. According to quantum field theory, the atom interacts with the fluctuating electromagnetic fields of the vacuum, and this interaction triggers the emission. The vacuum is not passive, it is active, dynamic, influencing the behavior of matter and energy. Space at the quantum level is seething with activity. What we call a vacuum is not nothingness. It is a complex, fluctuating quantum field, filled with virtual particles and energy and possibilities. The universe is not built on a foundation of emptiness. It is built on a foundation of quantum noise, a fuzz of possibility that underlies all of reality. Fact 54: light takes longer to travel through empty space than we think. Light travels at approximately 300,000 kilometers per second in a vacuum. This is the fastest speed anything can travel, a fundamental constant of nature, or so we are taught. But this is not quite true. Light travels at 300,000 kilometers per second only in a perfect vacuum, completely empty space with no matter, no electromagnetic fields, no gravitational fields. In reality, no such perfect vacuum exists. Space is filled with the quantum vacuum, with stray atoms and molecules, with magnetic fields, with gravitational fields from distant objects. All of these affect the speed of light, slowing it down by tiny amounts. In the interstellar medium, the space between stars, the density of matter is so low that the slowing is negligible, perhaps a few parts in a trillion. But over cosmic distances, even these tiny effects can add up. Light traveling from a distant galaxy may take slightly longer to reach us than we would calculate assuming a perfect vacuum. Gravitational fields also affect the speed of light. Light passing near a massive object like the Sun is slowed and bent by the Sun's gravity. The bending, gravitational lensing, has been observed and is one of the classic tests of general relativity. But the slowing, gravitational time dilation, means that light takes longer to travel a given distance in a gravitational field than it would in flat, empty space. On Earth, light also slows dramatically when passing through transparent materials. Light travels at approximately 300,000 kilometers per second in a vacuum, but only about 225,000 kilometers per second in water and about 200,000 kilometers per second in glass. This slowing is due to light interacting with the atoms in the material, being absorbed and re-emitted countless times, which delays its passage. Speed of light in a vacuum, 299,792,458 meters per second, is a fundamental constant. But the effective speed at which light travels through space, real, messy, imperfect space, is slightly less. The universe is not an ideal laboratory. It is full of matter, energy, and fields that complicate everything. The light we see from distant stars has been slowed, bent, scattered, and redshifted on its journey to us. The universe is more complex than the simplified models we use to describe it. Fact 55: the observable universe is only a tiny fraction of the total universe. The observable universe, the region of space from which light has had time to reach us since the Big Bang, is vast. It has a radius of approximately 46.5 billion light-years and contains approximately 2 trillion galaxies. But the observable universe is not the entire universe. It is just the portion we can see. Beyond the cosmic horizon lies the unobservable universe, regions of space whose light has not yet reached us and may never reach us. How large is the unobservable universe? We do not know. It could be only slightly larger than the observable universe, or it could be vastly larger, perhaps infinite. If the universe is infinite, and current measurements of its flatness suggest it might be, then the observable universe is an infinitesimal fraction of the whole, a tiny bubble of space embedded in an infinite expanse that we can never observe. Even if the universe is finite, it could be far larger than the observable universe. Some models suggest the universe could be hundreds or thousands of times larger than what we can observe. Imagine the observable universe as a sphere with a radius of 46.5 billion light-years. Now imagine that this sphere is embedded in a larger space that extends far beyond in all directions. A space filled with more galaxies, more stars, more worlds, all forever beyond our reach. There is no way to observe the unobservable universe. Its light has not reached us, and if the expansion of space continues to accelerate, never will. We can make inferences based on our theories and measurements. If the universe is flat, as observations suggest, then it is either infinite or extraordinarily large. But direct observation is impossible. The unobservable universe is, by definition, unobservable. This has profound implications. Everything we study, everything we observe, everything we know about the universe is based on the tiny fraction of it that falls within our cosmic horizon. The rest, possibly infinite, possibly just very large, remains forever hidden. We are like observers on a small island in an infinite ocean, able to see only as far as the horizon, forever ignorant of what lies beyond. The universe is larger than we can see, possibly larger than we can imagine. And we will never know how much we are missing. Fact 56. Time may have begun with the Big Bang, or it may be eternal. What happened before the Big Bang? This is one of the most common questions people ask about the universe, and it is also one of the most difficult to answer, because it may not have a meaningful answer. According to general relativity and the standard Big Bang model, time itself began with the Big Bang. The Big Bang was not an event in time, it was the beginning of time. Asking what happened before the Big Bang is like asking what is north of the North Pole. The question does not make sense because there is no before, when time itself did not exist. But this answer is unsatisfying to many people, and some physicists have proposed alternatives. One possibility is that the universe is cyclical. It undergoes an infinite series of expansions and contractions, with each big crunch, the collapse of the universe to a singularity, followed by a new Big Bang that begins a new cycle. In this model, time is eternal, extending infinitely into the past and future, with no ultimate beginning or end. Another possibility is that the Big Bang was not the beginning but a transition, a phase change in a pre-existing universe. Some models suggest that the universe before the Big Bang was in a different state, perhaps a contracting universe that bounced at a minimum size and began expanding again, or perhaps a parent universe that gave birth to our universe through a process analogous to quantum tunneling. String theory and quantum gravity theories suggest even stranger possibilities. Some versions of string theory propose that our universe is a three-dimensional membrane, a brain, floating in a higher dimensional space, and the Big Bang was the result of a collision between our brain and another brain. In this model, time might exist in the higher dimensional space, even if it began in our universe. We do not know what happened before the Big Bang, or even if the question makes sense. The moment of the Big Bang itself is hidden from us by a barrier of ignorance. The physics of the first 10 seconds, Planck time, is beyond our current understanding. At those energies and densities, quantum effects dominate, and we do not yet have a theory of quantum gravity that can describe what happens. The origin of time, the origin of the universe, the question of what came before, these remain among the deepest mysteries in all of science. Fact 57. The universe is mostly empty space. Despite containing approximately 2 trillion galaxies, each with hundreds of billions of stars, the universe is overwhelmingly empty. The density of matter in the universe, averaged over the largest scales, is astonishingly low, approximately 5 protons per cubic meter. To put this in perspective, a cubic meter of air at sea level on Earth contains approximately 1025 molecules. The average density of the universe is 24 orders of magnitude less dense than air. Most of the volume of the universe is intergalactic space, the vast voids between galaxy clusters, where the density of matter is even lower, sometimes approaching just 1 atom per cubic meter or less. Even within galaxies, most of the volume is empty space. The distance between stars is enormous compared to the size of the stars themselves. In our region of the Milky Way, the nearest star to the Sun is Proxima Centauri, approximately 4.24 light-years away, about 40 trillion kilometers. If the Sun were the size of a basketball, Proxima Centauri would be another basketball about 6,000 kilometers away. The space between them would be almost completely empty. Even atoms themselves are mostly empty space. The nucleus of an atom occupies only about 10 of the atom's volume. If an atom were the size of a football stadium, the nucleus would be the size of a marble at the center, and the electrons would be tiny specks orbiting somewhere in the stands. The rest is empty. But as we have discussed, even empty space is not truly empty. It is filled with the quantum vacuum, with virtual particles, with electromagnetic fields, with the cosmic microwave background radiation, with neutrinos streaming through from the Sun and other stars, with gravitational waves from distant astrophysical events. Space is empty of matter, but it is not empty of everything. It is a complex, dynamic medium, filled with fields and particles, and energy that we are only beginning to understand. The universe is vast, and most of it is space, incomprehensible expanses of near-nothingness, interrupted occasionally by islands of matter, stars, planets, galaxies that are themselves mostly empty. We live on one such island, a tiny condensation of matter in an ocean of void, looking out at a universe that is defined more by its emptiness than by its substance. Fact 58. Proxima Centauri is the closest star to the Sun, but still 4.24 light-years away. The nearest star to the Sun is Proxima Centauri, a small red dwarf star in the Alpha Centauri system, located approximately 4.24 light-years from Earth. This is the closest star to us other than the Sun, our nearest stellar neighbor in a galaxy of hundreds of billions of stars. 4.24 light-years, approximately 40 trillion kilometers. If you could travel at the speed of the fastest spacecraft humans have ever built, the Parker Solar Probe, which reached speeds of approximately 163 kilometers per second relative to the Sun, it would still take approximately 7,700 years to reach Proxima Centauri. At the speed of a commercial airliner, approximately 900 kilometers per hour, the journey would take approximately 5 million years. Proxima Centauri is a red dwarf, a type of star far smaller and dimmer than the Sun. It has a mass of approximately 12% that of the Sun and a luminosity only about 0.17% that of the Sun. It is so dim that it cannot be seen with the naked eye from Earth despite being our closest stellar neighbor. The star is orbited by at least 2 known planets, including Proxima Centauri b, a planet with a mass slightly larger than Earth's, orbiting in the star's habitable zone, where liquid water could potentially exist on the surface. The Alpha Centauri system, which includes Proxima Centauri as well as 2 larger Sun-like stars, Alpha Centauri A and Alpha Centauri b, orbiting each other, is the target of some of the most ambitious proposals for interstellar travel. The Breakthrough Starshot project, announced in 2016, aims to send tiny spacecraft equipped with light sails to Alpha Centauri, accelerated to approximately 20% of the speed of light by ground-based lasers. At this speed, the spacecraft would reach Alpha Centauri in approximately 20 years, sending back images and data from the closest star system to our own. Proxima Centauri is close by the standards of the galaxy. Most stars are tens, hundreds, or thousands of light-years away. But even this close star is so distant that the light we see from it left the star over 4 years ago. The stars are separated by distances so vast that they might as well be islands in an infinite ocean, each one isolated from all the others, connected only by the faint light that travels between them across the void. Fact 59: galaxies are moving away from us faster than light. One of the strangest consequences of the expansion of the universe is that distant galaxies are moving away from us faster than the speed of light. This seems to violate the principle that nothing can travel faster than light, but it does not, because the galaxies are not moving through space. Space itself is expanding, carrying the galaxies with it. Imagine a rubber sheet with dots drawn on it to represent galaxies. If you stretch the sheet, the dots move apart, not because they are moving across the sheet, but because the sheet itself is expanding. The expansion of space works the same way. Galaxies are not flying through space at high speeds. Space itself is stretching, increasing the distance between galaxies. The rate of expansion is described by the Hubble constant, which relates the recession velocity of a galaxy to its distance. The current best estimate of the Hubble constant is approximately 70 kilometers per second per megaparsec. This means that a galaxy 1 megaparsec away, approximately 3.26 million light-years, is receding at approximately 70 kilometers per second. A galaxy 2 megaparsecs away is receding at 140 kilometers per second. And so on. At a distance of approximately 4,200 megaparsecs, about 14 billion light-years, a galaxy would be receding at the speed of light. Beyond that distance, beyond the cosmic horizon, galaxies are receding faster than light, and their light can never reach us. These galaxies are forever beyond our observation, moving away from us so rapidly that their light is stretched and redshifted infinitely, disappearing into unobservability. The expansion of space is not bound by the speed limit that governs objects moving through space. The universe can expand at any rate, carrying distant galaxies to recession velocities greater than light speed, without violating relativity. We can never travel to these distant galaxies. They are beyond the cosmic horizon. Beyond the reach of any spacecraft or signal we could send. They are part of the unobservable universe, forever hidden from us by the expansion of space itself. Fact 60: the universe is 13.8 billion years old, but some stars could be nearly that old. The universe is 13.787 billion years old. The oldest stars we have observed are approximately 13.2 to 13.5 billion years old, formed only a few hundred million years after the Big Bang, when the universe was still in its infancy. These ancient stars, called population III stars, are believed to be the first generation of stars to form in the universe. They condensed from clouds of gas composed almost entirely of hydrogen and helium, the only elements created in the Big Bang. Because they contain no heavy elements, population III stars were able to grow much larger than modern stars. Some may have reached masses of hundreds of times the mass of the Sun. They burned hot and fast, exhausting their fuel in only a few million years and exploding as supernovae, scattering the first heavy elements into the interstellar medium and seeding the formation of the next generation of stars. None of the original population III stars still exist, they all died billions of years ago. But their remnants, the heavy elements they created and dispersed, are incorporated into later generations of stars, including the Sun. Every atom of carbon, oxygen, and iron in your body was created by a star that died billions of years ago, possibly a population III star that formed when the universe was young. The stars we observe today that are 13 billion years old are mostly red dwarfs and white dwarfs, long-lived stars that have survived since the early universe. Red dwarfs can burn for trillions of years, far longer than the current age of the universe, so the oldest red dwarfs are still in their prime. White dwarfs are the remnants of sun-like stars that exhausted their fuel and shed their outer layers, leaving behind a dense core that cools slowly over billions of years. The oldest known star in the Milky Way is Methuselah, HD 140,283, a subgiant star located approximately 190 light-years from Earth. Its age has been estimated at approximately 14.5 billion years, older than the universe itself, which created a paradox when the measurement was first reported. Subsequent analysis and improved measurements of the star's distance and composition revised the age estimate to approximately 13.7 billion years, comfortably younger than the universe but still extraordinarily ancient, a star that formed when the cosmos was barely 100 million years old. These ancient stars are time machines, relics from the early universe, witnesses to cosmic history that stretches back almost to the beginning. They are reminders that the universe is old, but not infinitely old. It had a beginning, and everything in it, no matter how ancient, is younger than that beginning. 60 facts, and the universe becomes stranger with every one. We have explored the nature of time, the quantum realm where particles exist in superposition, and the possibility that our universe is one of many in a vast multiverse. We have learned that black holes emit radiation and eventually evaporate, that dark matter holds galaxies together but has never been directly detected, and that empty space is filled with the quantum vacuum. We have confronted the limits of knowledge imposed by the uncertainty principle, the spooky action at a distance of quantum entanglement, and the holographic principle that suggests information is encoded on surfaces rather than in volumes. We have learned that we are made of stardust, that the sun loses 4 million tons of mass every second, and that the observable universe is only a tiny fraction of the total universe. Now we will explore more cosmic extremes, the most energetic events, the strangest objects, the deepest paradoxes. The journey through the universe continues, and the strangest revelations are yet to come. The cosmos awaits. At beginning, we learn the fundamentals, the universe's age, its size, the Big Bang that began it all. We discovered that most of the universe is invisible, composed of dark matter and dark energy. Then we explored exoplanets and the search for alien life, witnessed the violent deaths of massive stars, and learned that Jupiter has protected Earth from countless impacts. After it, we ventured into quantum strangeness, superposition, entanglement, the uncertainty principle. We explored the nature of time, the possibility of a multiverse, and the holographic principle that suggests our three-dimensional reality might be encoded on a two-dimensional surface. Now we confront the universe's most extreme phenomena. We explore the most powerful explosions, the fastest spinning objects, the coldest places, and the hottest temperatures. We witness cosmic collisions that reshape galaxies, discover planets where it rains glass sideways, and learn about the mysterious fast radio bursts that flash across the cosmos. And we begin to understand that the universe is not just vast and old. It is actively violent, constantly transforming, filled with events of incomprehensible power. Close your eyes, prepare for the extremes, and let's continue. Fact 61. Magnetars have the strongest magnetic fields in the universe. Among the strangest and most extreme objects in the universe are magnetars, neutron stars with magnetic fields so powerful they distort the very fabric of space and would be lethal to any matter that came near them. A typical neutron star has a magnetic field approximately 100 billion times stronger than Earth's magnetic field. This is already extraordinarily powerful, strong enough to erase the magnetic stripe on a credit card from thousands of kilometers away. But magnetars have magnetic fields that are 1,000 times stronger still, up to 1015 Gauss, or a quadrillion times Earth's magnetic field. To understand how extreme this is, if you were within 1,000 kilometers of a magnetar, the magnetic field would be strong enough to disrupt the molecular bonds in your body, effectively dissolving you at the atomic level. The magnetic field would align all the atoms in your body, pull apart molecules, and interfere with the electrical signals in your nervous system. Death would be instantaneous and absolute. Magnetars are created in supernova explosions of massive stars, when rapid rotation and powerful convection in the newborn neutron star amplify the magnetic field to extreme levels. These fields are not stable, they decay over time, releasing energy in the form of X-rays and gamma rays. When a magnetar undergoes a starquake, a sudden cracking and rearrangement of its solid crust due to magnetic stresses, it releases an enormous burst of energy. In 2004, a magnetar named SGR 180620, located approximately 50,000 light-years from Earth, released a burst of gamma rays and X-rays so powerful that it measurably affected Earth's atmosphere, ionizing the upper atmosphere and disrupting radio communications, despite being on the opposite side of the galaxy. Magnetars are rare, only about 30 have been identified in the Milky Way, out of an estimated population of perhaps 30 million neutron stars. They are also short-lived by astronomical standards, with magnetic field decay timescales of thousands to tens of thousands of years. But they are among the most extreme objects in the universe, and they demonstrate that nature can create magnetic fields far more powerful than anything we can produce or even imagine. Fact 62: pulsars spin hundreds of times per second with incredible precision. Pulsars are neutron stars that emit beams of electromagnetic radiation from their magnetic poles, and as the star rotates, these beams sweep across space like the beam from a lighthouse. If one of the beams points toward Earth, we detect it as a regular pulse of radio waves, hence the name pulsar. The fastest known pulsar, PSRJ 17482446 AD, spins at approximately 716 rotations per second. This means that a neutron star approximately 20 kilometers in diameter, roughly the size of a city, is rotating 716 times every second. The surface of this pulsar is moving at approximately 24% of the speed of light. If it spun any faster, the centrifugal force would tear it apart. What makes pulsars even more remarkable is the precision of their rotation. The most stable pulsars, called millisecond pulsars, are among the most precise clocks in the universe, rivaling atomic clocks in their stability. Some pulsars maintain their rotation rate with such precision that they lose or gain only a few microseconds per year. Astronomers use arrays of pulsars as cosmic clocks to detect gravitational waves and measure subtle variations in the fabric of spacetime. Pulsars slow down over time as they lose rotational energy through electromagnetic radiation and particle emission. Young pulsars, freshly formed in supernova explosions, typically rotate tens of times per second and slow by approximately 1 rotation per century. Old pulsars, billions of years old, have slowed to rotation periods of seconds or even minutes. But millisecond pulsars, the fastest pulsars, are believed to be old neutron stars that have been spun up by accreting matter from a companion star, gaining angular momentum and speeding up their rotation. The discovery of pulsars in 1967 by Jocelyn Bell Burnell was one of the most important astronomical discoveries of the 20th century. When the first pulsar was detected, its incredibly regular pulses, arriving every 1.337 seconds with extraordinary precision, seemed almost artificial, and it was briefly nicknamed LGM-1 for Little Green Men, on the hypothesis that it might be a signal from an extraterrestrial civilization. But subsequent discoveries of more pulsars with different periods confirmed that they were natural objects, neutron stars, spinning with the precision of cosmic clockwork, broadcasting their presence across the galaxy. Fact 63: the coldest known place in the universe is the Boomerang Nebula. The coldest known natural place in the universe is the Boomerang Nebula, a planetary nebula located approximately 5,000 light-years from Earth in the constellation Centaurus. The temperature at the center of this nebula is approximately 1 Kelvin, only 1 degree above absolute zero, the coldest temperature theoretically possible. The Boomerang Nebula is the expanding cloud of gas ejected from a dying sun-like star. As the star exhausted its nuclear fuel and entered the late stages of its evolution, it began to shed its outer layers in powerful stellar winds, ejecting gas at speeds of approximately 164 kilometers per second. This rapid expansion causes the gas to cool dramatically through a process similar to the way a compressed gas cools when allowed to expand, the same principle used in refrigerators. The expansion of the Boomerang Nebula is so rapid, and the cooling so efficient, that the temperature has dropped to approximately 1 Kelvin, colder than the cosmic microwave background radiation, which has a temperature of 2.7 Kelvin. This makes the Boomerang Nebula the only known object in the universe that is colder than the CMB. Everywhere else, the CMB provides a minimum temperature floor. Objects can radiate heat into space and cool, but they cannot cool below the temperature of the CMB because they are constantly absorbing energy from it. The Boomerang Nebula is cooling so quickly that it has temporarily dropped below this floor. The coldest temperatures ever achieved in laboratories on Earth are far colder than the Boomerang Nebula. Physicists have cooled atoms to temperatures of a few billionths of a Kelvin, far colder than anything in nature. But these ultra-cold temperatures are achieved only in carefully controlled experiments and persist for only brief periods. The Boomerang Nebula is the coldest natural environment in the universe, a place where the gas is so cold that most molecules have frozen onto dust grains, leaving only a tenuous vapor of helium and hydrogen atoms. In the far future, as the universe expands and the cosmic microwave background continues to cool, the entire universe will eventually become colder than the Boomerang Nebula is today. Trillions of years from now, the CMB will have cooled to a tiny fraction of a Kelvin, and the universe will approach absolute zero. But for now, the Boomerang Nebula holds the record, the coldest place we know, a frigid remnant of a dying star. Fact 64, the hottest temperature ever recorded was in a particle collider on Earth. The hottest temperature ever recorded anywhere in the universe, as far as we know, was achieved not in the core of a star or in a supernova explosion, but in a laboratory on Earth. In 2012, physicists at the Large Hadron Collider, LHC, at CERN in Switzerland, collided lead ions at nearly the speed of light, creating a state of matter called quark-gluon plasma at a temperature of approximately 5.5 trillion degrees Celsius, about 100,000 times hotter than the core of the Sun. Quark-gluon plasma is believed to be the state of matter that existed in the first microseconds after the Big Bang, when the universe was so hot and dense that protons and neutrons could not form. At these temperatures, the quarks and gluons that normally make up protons and neutrons are no longer confined inside particles. They exist freely in a hot, dense soup. As the universe expanded and cooled, the quark-gluon plasma condensed into protons and neutrons, which eventually combined to form atomic nuclei. By recreating these conditions in particle colliders, physicists can study the properties of matter under conditions that existed only in the earliest moments of the universe. The hottest natural temperatures in the universe today are found in supernova explosions and in the accretion disks around black holes and neutron stars, where infalling matter is heated to billions of degrees by friction and compression. The cores of massive stars during their final moments before collapse can reach temperatures of several billion degrees. Gamma-ray bursts, the most energetic explosions in the universe, may briefly reach even higher temperatures, possibly approaching the temperatures achieved at the LHC. But even these extreme natural phenomena are cooler than the Big Bang itself. In the first fraction of a second after the universe began, temperatures were incomprehensibly high. At 10:43 seconds Planck time, the temperature is estimated to have been approximately 1032 Kelvin, 100 million trillion degrees. At these temperatures, the laws of physics as we know them break down, and we have no theory that can describe what happens. The earliest moments of the universe remain beyond our understanding, a realm where temperature and energy were so extreme that matter, space, and time themselves existed in forms we cannot yet describe. Fact 65, there are planets where it rains molten glass sideways. Among the thousands of exoplanets discovered orbiting other stars, some are so alien, so extreme, so utterly unlike anything in our solar system that they challenge our understanding of what a planet can be. One of the strangest is HD 189733b, a hot Jupiter, located approximately 64 light-years from Earth. HD 189733b is a gas giant slightly larger than Jupiter, but it orbits its star at a distance of only 4.5 million kilometers, less than 2% of the distance from Earth to the Sun. At this proximity, the planet is tidally locked, with one side permanently facing the star and baked to temperatures exceeding 1000 degrees Celsius, while the other side, facing away from the star, is cooler but still far too hot for any known form of life. But the temperature is not the strangest thing about HD 189733b. Observations, using the Hubble Space Telescope, have revealed that the planet has a deep blue color, not because it has oceans like Earth, but because its atmosphere contains silicate particles that scatter blue light. And the weather on HD 189733b is nightmarish. Winds reach speeds of up to 8,700 kilometers per hour, over 5,000 miles per hour, or 7 times the speed of sound on Earth. These supersonic winds are driven by the extreme temperature difference between the day side and night side of the planet. And in this howling atmosphere, it rains glass. The high temperatures vaporize silicate minerals, and as atmospheric circulation carries this vapor to cooler regions, it condenses into tiny droplets of molten glass, essentially liquid sand, which fall as rain. But because of the extreme winds, this glass rain does not fall vertically. It is blown sideways at thousands of kilometers per hour, creating horizontal streams of molten silicate droplets whipping across the planet's atmosphere. HD 189733b is not unique. Other hot Jupiters have been found with equally extreme conditions: planets where the day side is hot enough to vaporize iron, planets where clouds are made of corundum, the mineral that forms rubies and sapphires, planets where it rains molten iron or titanium oxide. These worlds are nothing like Earth. They are furnaces, their atmospheres hostile beyond imagination, their surfaces, if they have solid surfaces at all, uninhabitable and deadly. They are reminders that the universe is creative in ways we never expected, producing planets in configurations that no theory predicted and conditions that no science fiction writer imagined. Fact 66. Fast radio bursts are one of the universe's greatest mysteries. In 2007, astronomers analyzing archived data from the Parkes Radio Telescope in Australia made a strange discovery. A brief burst of radio waves, lasting only a few milliseconds, had been detected coming from somewhere far outside our galaxy. The burst was extraordinarily bright, releasing as much energy in a few milliseconds as the Sun releases in several days, and it appeared to have originated from a source billions of light years away. This was the first detection of what is now called a fast radio burst, FRB. Since then, hundreds of FRBs have been detected by radio telescopes around the world. They are one of the most mysterious phenomena in astronomy. We do not know what causes them, though we have many theories. FRBs are characterized by their brevity, typically lasting only a few milliseconds, their brightness extremely energetic, and their distance, most originate from outside our galaxy, billions of light years away. The signal shows dispersion, lower frequencies arrive slightly after higher frequencies, a pattern consistent with the signal passing through ionized gas in intergalactic space, confirming the extragalactic origin. What could produce such an energetic, brief burst of radio waves? Proposed explanations include magnetoflares, eruptions from the extraordinarily strong magnetic fields of magnetars; colliding neutron stars or black holes, the merger events that produce gravitational waves; supernova explosions of exotic types; evaporating primordial black holes; pulsars with extreme properties; and inevitably, signals from extraterrestrial civilizations, though this is considered the least likely explanation. Most FRBs appear to be one-time events, detected once and never repeating. But a few FRBs are repeaters. They flash multiple times from the same location, allowing astronomers to study them in more detail. In 2020, the first FRB was detected from within our own galaxy, a burst from a known magnetar called SGR 1935+2154. This was a breakthrough discovery, providing the first direct evidence linking FRBs to magnetars, and suggesting that at least some FRBs are produced by these extreme neutron stars. But many FRBs remain unexplained. Their extreme energies, their brevity, their locations scattered across the cosmos, all suggest that they are produced by violent, catastrophic events, but we do not yet know what those events are. FRBs are the universe speaking to us in a language we do not yet understand, sending messages across billions of light years that arrive at Earth as fleeting millisecond flashes, then fall silent again. Fact 67. The Great Attractor is pulling our galaxy toward it. In the 1970s, astronomers studying the motion of galaxies made a disturbing discovery. The Milky Way, along with thousands of other galaxies in our region of the universe, is moving at approximately 600 kilometers per second in a direction toward the constellation Centaurus. This motion is far too fast to be explained by the gravitational attraction of the Virgo cluster, the nearest large cluster of galaxies to us. Something much larger and more massive must be pulling us. This something is called the Great Attractor. It is a gravitational anomaly located approximately 150 to 250 million light-years from Earth, in the direction of the constellation Hydra Centaurus. The Great Attractor appears to be the focal point of the motion of galaxy clusters in our region of the universe. Not just the Milky Way, but thousands of galaxies, stretching across hundreds of millions of light-years, are being pulled toward it. Observing the Great Attractor directly is difficult because it lies in the zone of avoidance, a region of the sky obscured by the dust and stars of our own Milky Way galaxy. Light from objects in this direction is absorbed and scattered by the intervening material, making it nearly impossible to see what lies beyond. But radio and infrared observations, which can penetrate the dust, have revealed that the Great Attractor is not a single object, but a complex region containing multiple galaxy clusters and superclusters. Further observations have shown that the Great Attractor itself is being pulled by an even larger structure, the Shapley supercluster, a massive concentration of galaxy clusters located approximately 650 million light-years from Earth, containing tens of thousands of galaxies with a total mass equivalent to tens of thousands of Milky Way galaxies. The Shapley supercluster is one of the largest structures in the local universe, and its gravitational influence extends across hundreds of millions of light-years. The Milky Way is not just orbiting the center of the local group, not just moving with the local group toward the Virgo cluster, not just being pulled by the Great Attractor. It is part of a vast cosmic flow, a river of galaxies streaming toward the densest concentrations of matter in our region of the universe. And we are moving with this flow at hundreds of kilometers per second, our galaxy and all its stars carried along by the gravitational pull of structures so vast that the Milky Way is just a tiny speck in their domain. Fact 68. The Sun orbits the Milky Way every 225 million years. The Sun is not stationary. It orbits the center of the Milky Way galaxy, completing one full orbit approximately every 225 to 250 million years, a period called a galactic year or cosmic year. Since the Sun formed approximately 4.6 billion years ago, it has completed approximately 20 to 21 orbits around the galaxy. The Sun orbits at a distance of approximately 26,000 light-years from the galactic center, moving at a speed of approximately 220 kilometers per second, about 800,000 kilometers per hour. Despite this tremendous speed, the orbit is so large that it takes over 200 million years to complete. The last time the Sun was at its current position in the galaxy, dinosaurs had not yet evolved. The continents were arranged differently. The Earth looked completely alien compared to today, and the next time the Sun completes an orbit and returns to this position, Earth will have changed beyond recognition once again. As the Sun orbits, it bobs up and down through the galactic plane, the thin disk of stars and gas that makes up the visible Milky Way. The Sun completes approximately 2.7 oscillations through the plane per orbit, crossing the plane approximately every 35 million years. Some researchers have proposed that these crossings might correlate with mass extinction events on Earth, suggesting that passage through the denser regions of the galactic plane might increase the likelihood of comet impacts or exposure to cosmic radiation. The evidence for this correlation is weak, and the hypothesis remains controversial. The entire local group of galaxies, including the Milky Way, Andromeda, and their satellite galaxies, is also moving through space, falling toward the Virgo cluster at approximately 400 kilometers per second. And the Virgo cluster itself, along with neighboring clusters, is moving toward the Great Attractor. The motion is nested. The Earth orbits the Sun orbits the Milky Way moves toward Virgo moves toward the Great Attractor, and at every scale the universe is in motion. We are not standing still. We are orbiting, falling, streaming through space at hundreds or thousands of kilometers per second, part of a vast cosmic dance that has been going on for billions of years and will continue for billions more. Fact 69. Voyager's golden record contains sounds and images of Earth. When Voyager 1 and Voyager 2 were launched in 1977, they carried with them a message intended not for humans, but for any extraterrestrial civilization that might one day encounter the spacecraft drifting through interstellar space. This message, the Voyager Golden Record, is a 12-inch gold-plated copper disc containing sounds and images selected to represent the diversity of life and culture on Earth. The Golden Record contains 116 images, including photographs of Earth, the solar system, human anatomy, landscapes, plants, animals, and scenes from human life and culture. It contains 90 minutes of music from cultures around the world, ranging from Bach and Beethoven to traditional songs from Japan, India, Africa, and South America. It contains spoken greetings in 55 languages, from ancient Sumerian to modern Mandarin. And it contains natural sounds: surf, wind, thunder, birdsong, whale song, and the sounds of human activity including footsteps, heartbeats, laughter, and the cry of a newborn baby. The record also contains a message from President Jimmy Carter. This is a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. The Golden Record is enclosed in an aluminum case with instructions for playing it, encoded in symbols that are intended to be understandable to any scientifically literate species. The case shows the location of the Sun relative to 14 pulsars, rapidly rotating neutron stars, whose precise rotation rates can be used to triangulate Earth's position in the galaxy. It shows the hydrogen hyperfine transition, a fundamental physical constant that defines a unit of time and length, and it shows the basic structure of the record player needed to retrieve the images and sounds. Voyager 1 is now over 24 billion kilometers from Earth, traveling at approximately 17 kilometers per second through interstellar space. It will not approach another star for approximately 40,000 years, when it will pass within 1.6 light-years of the star Gliese 445. By that time, humanity may have ceased to exist. The civilization that built Voyager may be long gone. But the golden record will remain, drifting through the galaxy, carrying humanity's message to the stars, a time capsule, a greeting, a monument to the species that built it and sent it on an endless journey. Fact 70: the universe is mostly hydrogen and helium. By mass, approximately 73% of the ordinary matter in the universe is hydrogen, and approximately 25% is helium. The remaining 2% consists of all the heavier elements, carbon, oxygen, nitrogen, iron, and everything else, that we tend to think of as important because they make up planets and living beings. This distribution was set in the first few minutes after the Big Bang, during a period called Big Bang nucleosynthesis, lasting from approximately 10 seconds to 20 minutes after the beginning. The universe was hot enough and dense enough for nuclear fusion to occur throughout space, converting protons into helium nuclei and small amounts of lithium. When the universe cooled below the temperature needed for fusion, the process stopped, leaving the universe with approximately 75% hydrogen by mass and 25% helium, with trace amounts of lithium and beryllium. For hundreds of millions of years after the Big Bang, the universe contained only these light elements. The heavier elements did not exist. They were created later, inside the first generation of stars, which fused hydrogen into helium and then helium into carbon, oxygen, and heavier elements. When these stars died in supernova explosions, they scattered the newly created heavy elements into the interstellar medium, enriching it and allowing the formation of second-generation stars with planetary systems that could include rocky planets. The Sun and Solar System formed from gas that had been enriched by multiple generations of stars. Approximately 1.5 to 2% of the Sun's mass consists of elements heavier than helium, what astronomers call metals, even though this category includes non-metals like carbon and oxygen. Earth, being a rocky planet, is made almost entirely of these heavy elements: iron, oxygen, silicon, magnesium, with very little hydrogen or helium. But Earth is the exception, not the rule. The universe as a whole is overwhelmingly hydrogen and helium, and it always will be. Stars create heavier elements, but they create them in small amounts, and most of the universe's mass will forever be the simple, light elements created in the Big Bang. We live on a planet made of rare elements, orbiting a star made mostly of the common ones, in a galaxy that is predominantly hydrogen and helium gas. We are the exception, built from the periodic table's minority constituents, complex structures assembled from the universe's rarest building blocks. Fact 71: the Andromeda Galaxy will collide with the Milky Way in 4.5 billion years. The Andromeda Galaxy, M31, and the Milky Way are on a collision course. The two galaxies are approaching each other at approximately 110 kilometers per second, and in approximately 4.5 billion years, they will collide. The collision will be one of the most spectacular events in the history of the local universe. As the galaxies approach, their gravitational interaction will distort their shapes, pulling out long tidal tails of stars. The gas clouds in the two galaxies will collide and compress, triggering enormous bursts of star formation, creating brilliant blue-white regions filled with massive, short-lived stars. The supermassive black holes at the centers of both galaxies, Sagittarius A in the Milky Way, approximately 4 million solar masses, and the black hole at the center of Andromeda, approximately 100 million solar masses, will spiral toward each other and eventually merge, releasing gravitational waves that will ripple across the universe. Despite the violence of the collision on a galactic scale, individual stars will almost never collide. The distances between stars are so vast that even when two galaxies merge, their stars simply pass by each other like ships in the night. The Sun and its planets will likely survive the collision intact, though our solar system's position in the merged galaxy will be completely different. We might be flung into the outer halo, or we might end up closer to the galactic center, or we might be ejected from the galaxy entirely, becoming part of the intergalactic void. The collision will take billions of years to complete. The galaxies will pass through each other, then swing back under their mutual gravitational attraction, and pass through again. Over hundreds of millions of years, they will merge, their stars and gas and dark matter mixing together, their spiral structures disrupted and replaced by a more chaotic, elliptical shape. Astronomers have already given this future merged galaxy a name: Milkomeda. By the time Milkomeda forms, the Sun will have evolved into a red giant and likely destroyed Earth. Life on Earth, if it still exists, will have migrated to other planets or moons or left the solar system entirely. The sky will look completely different, the familiar constellations scrambled, Andromeda no longer a distant fuzzy patch but a vast swirl of stars filling half the sky. The Milky Way band dissolved into a three-dimensional cloud of stars surrounding us in all directions. The collision of the Milky Way and Andromeda will be the end of both galaxies as we know them, and the beginning of a new, larger galaxy that will dominate the local group for billions of years to come. Fact 72. The universe doubles in size every 10 billion years. The expansion of the universe is accelerating, driven by dark energy, and this acceleration means that the size of the observable universe is increasing at a rate that is itself increasing. Based on current measurements of the expansion rate, the Hubble constant, and the amount of dark energy, cosmologists estimate that the universe roughly doubles in size approximately every 10 billion years. This doubling is not uniform. Nearby objects that are gravitationally bound, like our solar system, or the local group of galaxies, do not expand. The expansion affects only the largest scales, the distances between galaxy clusters that are not bound together by gravity. These clusters are moving apart, and the space between them is expanding, carrying them farther and farther apart as time goes on. 10 billion years from now, the observable universe will be roughly twice as large as it is today, and the cosmic horizon will have receded, allowing us to see galaxies that are currently beyond our view. But paradoxically, we will also see fewer galaxies, because many galaxies that are currently within the observable universe will have been carried beyond the cosmic horizon by the accelerating expansion, their light stretched and redshifted into invisibility. The expansion of the universe has profound implications for the future. As the universe continues to expand and accelerate, galaxies outside the local group will move beyond the cosmic horizon, disappearing from view. Star formation will gradually cease as the supply of gas is exhausted. The universe will grow darker, colder, and emptier. In the far future, trillions of years from now, an observer in the Milkomeda galaxy, the merger of the Milky Way and Andromeda, would see only the local group. All other galaxies would have receded beyond the horizon, their light so redshifted that they would be undetectable. The observable universe would consist of a single galaxy surrounded by darkness, and future astronomers, if they exist, would have no evidence that other galaxies ever existed. We live in a special time, a time when the universe is old enough to have developed complex structures and intelligent observers, but young enough that the observable universe still contains galaxies, that the cosmic microwave background is still detectable, that the expansion has not yet carried everything beyond our reach. In the deep future, the universe will be profoundly different, emptier, darker, lonelier. We are witnessing the universe in its youth, before it fades into the long darkness. Fact 73. There are more possible chess games than atoms in the observable universe. Here is a fact that illustrates the extraordinary power of combinatorics, the mathematics of combinations and permutations. The number of possible chess games that could be played is so large that it exceeds the number of atoms in the observable universe. The number of atoms in the observable universe is estimated at approximately 1080, a 1 followed by 80 zeros. This is an incomprehensibly large number, but the number of possible chess games, calculated by considering every legal move at every position, and every possible sequence of moves, is estimated to exceed 10,120. This number, called the Shannon number after Claude Shannon who first calculated it, is far larger than the number of atoms in the universe. This fact seems unrelated to cosmology, but it illustrates something profound about the nature of complexity. The universe may be vast, containing octillions of atoms, but the space of possibilities, the number of different configurations, different patterns, different outcomes that simple rules can generate, is far vaster still. The universe is not just large in terms of space and matter, it is large in terms of possibility space. This principle applies to many systems. The number of possible protein configurations, the number of possible genomes, the number of possible arrangements of matter in a room, the number of possible histories that could unfold from any given starting point. All of these numbers are staggeringly large, often far larger than the number of atoms in the universe. The universe we observe is one realization out of an inconceivably vast space of possibilities, and the fact that we exist at all, that this particular configuration of matter has assembled itself into galaxies and stars and planets and life, is an extraordinary statistical event. The universe is not just vast, it is complex beyond measure, exploring a tiny corner of an unimaginably large space of possible states. Every moment, every configuration, every thought you think is unique, one of countless possibilities that could have been but aren't, selected from a space so large that the entire observable universe cannot contain it. Fact 74. Some exoplanets orbit two stars like Tatooine. In the Star Wars universe, Luke Skywalker's home planet of Tatooine orbits two stars, which rise and set in its sky as a beautiful binary pair. For decades, this was thought to be pure fiction. Planets orbiting binary stars were considered unlikely because the complex gravitational interactions would make stable orbits difficult. Then in 2011, NASA's Kepler Space Telescope discovered Kepler 16b, a planet approximately 200 light-years from Earth that orbits two stars, a binary system where a smaller red dwarf orbits a larger Sun-like star. Kepler 16b is a gas giant, similar in size to Saturn, and it orbits both stars at a distance of approximately 100 million kilometers, taking 229 days to complete one orbit. If you could stand on a moon of Kepler 16b, you would see two suns in the sky, one orange, one red, rising and setting together, casting double shadows. Since the discovery of Kepler 16b, dozens more circumbinary planets have been found, planets that orbit two stars. Some of these planets are in the habitable zone, where temperatures might allow liquid water to exist on a rocky moon or on the planet's surface if it has one. The binary sunsets imagined by science fiction are real, and they occur on worlds scattered across the galaxy. Circumbinary planets face unique challenges. The gravitational interactions between the two stars create complex orbital dynamics, and planets can only exist in stable orbits if they are either very close to both stars, orbiting inside the binary system, or far enough away that the two stars can be treated as a single gravitational source. The habitable zones around binary stars are more complex than around single stars, depending on the masses of the stars, their orbital separation, and their eccentricity. But the discovery of circumbinary planets has shown that planetary systems are more diverse than we imagined. Planets can form and survive in binary systems, in triple star systems, around white dwarfs and pulsars, in orbits that would have seemed impossible just a few decades ago. The galaxy is full of worlds in configurations that challenge our theories and expand our understanding of what a planet can be. Fact 75. Quasars are the brightest objects in the universe. Quasars, short for quasi-stellar radio sources, are the extraordinarily bright cores of distant galaxies, powered by supermassive black holes actively consuming matter. They are the brightest continuously emitting objects in the universe, outshining entire galaxies despite being located at the very centers of those galaxies, in regions only light hours across. A typical quasar emits more energy than 100 normal galaxies, more than 1 trillion times the energy output of the Sun, from a region smaller than the solar system. This energy comes from the accretion disk surrounding the supermassive black hole, where matter spiraling inward is heated to millions of degrees by friction and tidal forces, emitting enormous amounts of radiation across the entire electromagnetic spectrum, from radio waves to X-rays. Quasars are among the most distant objects we can observe. The most distant known quasars are more than 13 billion light-years away, showing us the universe as it was less than 1 billion years after the Big Bang. These distant quasars are powered by supermassive black holes, with masses of billions of times the mass of the Sun, black holes that somehow formed and grew to enormous sizes in the early universe, a process that cosmologists are still trying to understand. Quasars were more common in the early universe than they are today. In the distant past, when galaxies were younger and gas was more abundant, supermassive black holes had more fuel to consume, and active galactic nuclei, quasars and other types, were far more numerous. Today, most supermassive black holes are quiescent. They have consumed most of the readily available gas in their vicinity and are no longer actively accreting material. The Milky Way's supermassive black hole, Sagittarius A, is not a quasar. It is relatively quiet, accreting matter at a low rate, and emitting only a fraction of the energy it could if it had more fuel. But quasars are not extinct. Some galaxies still have active quasars, and collisions between galaxies can funnel gas toward the central black hole, reigniting quasar activity. When the Milky Way and Andromeda collide in approximately 4.5 billion years, the disruption may send gas streaming toward the merged black holes, potentially creating a quasar at the center of Milkomeda, a brilliant beacon of light powered by the death of two galaxies. Fact 76. The universe was opaque for the first 380,000 years. For the first 380,000 years after the Big Bang, the universe was opaque to light. You could not see through it. It was filled with a hot, dense plasma of protons, electrons, and photons, and the photons were constantly being scattered by the free electrons, unable to travel more than a tiny distance before being absorbed and re-emitted. The universe was like the inside of a glowing fog. Light existed everywhere, but it could not travel far. This period is called the photon epoch, or the epoch of recombination, a misleading term, since electrons and protons were combining for the first time, not recombining. During this time, the universe was cooling as it expanded, and the temperature was dropping from millions of degrees to thousands of degrees. But it was still too hot for neutral atoms to form. Any electron that combined with a proton to form a hydrogen atom would be quickly ionized again by high-energy photons. At approximately 380,000 years after the Big Bang, the temperature dropped below about 3,000 Kelvin, cool enough that electrons and protons could combine to form neutral hydrogen and helium atoms, and cool enough that the photons no longer had enough energy to ionize them again. This moment is called recombination, and it transformed the universe. When recombination occurred, the photons were no longer scattered by free electrons. They could travel freely through space. The universe became transparent. The light released at the moment of recombination is the cosmic microwave background, the oldest light in the universe, the afterglow of the Big Bang, the first light that could travel freely through space. Before recombination, there is no light we can observe. The universe was opaque, and any light from before that time has been scattered and lost. The cosmic microwave background is our earliest view of the universe, a snapshot taken when the cosmos was only 380,000 years old. Before recombination, the universe had no stars, no galaxies, no complex structures, just a hot, uniform plasma gradually cooling and expanding. The cosmic microwave background shows us that universe smooth, homogeneous, with only tiny fluctuations in temperature that would, over hundreds of millions of years, grow into the galaxies and galaxy clusters we observe today. The universe was dark before recombination, and then when the plasma cleared, it was filled with light, not the light of stars, which did not yet exist, but the diffuse glow of the cooling Big Bang itself. Fact 77, cosmic rays are not rays, they are particles traveling near the speed of light. Cosmic rays are not electromagnetic radiation like light or X-rays. Despite the name, they are particles, primarily protons and atomic nuclei, traveling through space at speeds approaching the speed of light. They bombard Earth constantly, approximately 100 particles per second per square meter, passing through the atmosphere and in some cases, reaching the ground. Most cosmic rays are relatively low energy and are stopped by Earth's atmosphere or magnetic field. But some cosmic rays are extraordinarily energetic. Ultra-high energy cosmic rays, UHECRs, can have energies exceeding 10-20 electron volts, far higher than any particle accelerator on Earth can produce. A single UHECR can carry as much kinetic energy as a baseball thrown at 100 kilometers per hour, all concentrated in a single atomic nucleus. The origin of cosmic rays varies with their energy. Low-energy cosmic rays are produced by the Sun and by supernova explosions in the Milky Way. Medium-energy cosmic rays likely come from supernova remnants, where particles are accelerated to high speeds by the expanding shock waves. But the origin of ultra-high-energy cosmic rays is still a mystery. They are so energetic that they should not be able to reach us from very far away. They should lose energy by interacting with the cosmic microwave background, a process called the GZK cutoff after the physicists who predicted it. The fact that we detect UHECRs at all suggests that their sources are relatively nearby, within a few hundred million light-years, but no sources have been definitively identified. Cosmic rays have practical effects. When they strike the upper atmosphere, they create showers of secondary particles, muons, pions, electrons, that cascade down through the atmosphere. Some of these particles reach the ground, and some pass through our bodies. At any given moment, several cosmic ray muons are passing through your body every second. They are harmless at these low rates, but astronauts in space, unprotected by Earth's atmosphere and magnetic field, receive much higher doses of cosmic rays, which can damage DNA and increase cancer risk. Cosmic rays are also a concern for electronics. High-energy particles can flip bits in computer memory, causing errors, a phenomenon called a single-event upset. Cosmic rays are messengers from the most violent events in the universe, supernova explosions, active galactic nuclei, possibly colliding galaxies or other exotic sources. They are the only particles from distant parts of the universe that reach us directly. Photons and neutrinos also reach us, but cosmic rays are the only massive particles. By studying cosmic rays, we can learn about the acceleration mechanisms, the magnetic fields, and the extreme environments that produce them, a form of astronomy that uses particles instead of light. Fact 78. There is enough energy in empty space to power the universe. One of the deepest mysteries in physics is the vacuum energy problem, also called the cosmological constant problem. According to quantum field theory, empty space, the vacuum, has a non-zero energy density due to quantum fluctuations. Virtual particles constantly pop in and out of existence, and this activity gives the vacuum a baseline energy level. If you calculate the vacuum energy using quantum field theory, you get an absurdly large number, approximately 10^113 joules per cubic meter. This is 100 orders of magnitude larger than the observed energy density of the universe, which is approximately 10^9 joules per cubic meter, mostly in the form of dark energy. This discrepancy, a factor of 10^122, is the largest mismatch between theory and observation in all of physics. If the vacuum energy were as large as quantum field theory predicts, the universe would be expanding so rapidly that galaxies, stars, and atoms could not form. The fact that we exist at all tells us that the vacuum energy must be much, much smaller than the theoretical prediction, but we do not know why. Either quantum field theory is wrong, or there is some mechanism, unknown to us, that cancels almost all of the vacuum energy, leaving only the tiny amount we observe as dark energy. This is not just an academic problem. The vacuum energy, if it exists, is dark energy, the mysterious force causing the accelerated expansion of the universe. Understanding why the vacuum energy is so small could explain dark energy, one of the most important unsolved problems in cosmology, but no one has succeeded in explaining it. The vacuum energy problem is a profound puzzle sitting at the intersection of quantum mechanics, general relativity, and cosmology, and solving it may require a revolution in physics comparable to the revolutions brought by quantum mechanics and relativity in the early 20th century. The universe is held together by mysteries. Dark matter, dark energy, the cosmological constant, the vacuum energy, all are names for things we know exist but do not understand. The universe works, galaxies form, stars shine, life evolves, but the fundamental reasons why the universe has the properties it does, why the constants of nature have the values they have, why the vacuum energy is not enormous, these remain among the deepest questions in science. Fact 79, the Milky Way will eventually run out of gas and stop forming stars. Star formation requires gas, cold, dense clouds of molecular hydrogen that can collapse under gravity to form new stars. The Milky Way currently contains enormous amounts of gas, and star formation continues at a rate of approximately 1 to 2 new solar masses per year, but this cannot continue forever. The gas supply in the Milky Way is being depleted by star formation and is being replenished by infall of gas from the intergalactic medium. Currently, the inflow roughly balances the outflow, and the star formation rate is relatively steady, but in the distant future, the inflow will decrease and the gas supply will be exhausted. The collision with Andromeda in approximately 4.5 billion years will trigger a final burst of intense star formation as the gas clouds in the two galaxies collide and compress. This starburst will consume much of the remaining gas, creating a generation of massive, short-lived stars that will quickly burn out and die. After the starburst ends, the merged Milkomeda galaxy will have very little gas left, and star formation will slow to a trickle and eventually cease. Approximately 100 billion years from now, if not sooner, the Milky Way or Milkomeda will have exhausted its gas supply. No new stars will form. The existing stars will continue to burn, but one by one they will exhaust their fuel and die. The most massive stars will have long since exploded as supernovae. The sun-like stars will swell into red giants and then shed their outer layers, leaving behind white dwarfs. The smallest stars, red dwarfs, will continue to burn for trillions of years, but eventually even they will run out of fuel. In the far future, trillions of years from now, the galaxy will be dark. The last star will have burned out. The only light will come from the faint glow of white dwarfs and neutron stars slowly cooling, and from the accretion disks around black holes consuming the occasional stray planet or stellar remnant. The era of stars will be over, and the universe will enter the degenerate era, a dark age where the only remnants of the stellar epoch are the slowly cooling corpses of dead stars, drifting through the darkness for eternity. Star formation is not eternal. It is a phase in the universe's history, a brief period by cosmic standards, when gas is abundant and stars can form. We live in that phase now in a universe filled with light and life and the elements created by dying stars, but the phase will end. The stars will die, the galaxies will darken, and the universe will fade into a cold, dark silence that will last far longer than the bright age we are privileged to witness. Fact 80, every point in space was once at the center of the universe. Here is a mind-bending truth about the Big Bang. Every point in space was once at the center of the universe. The Big Bang did not happen at a single point in space. It happened everywhere, simultaneously. Space itself expanded from a state of infinite density, and every point in the universe today was once part of that infinitely dense state. Imagine the universe at 1 second after the Big Bang. At that moment, the universe was far smaller than it is today, but it was already infinite in extent if it is infinite now. Every point that exists today existed then, but the distances between points were smaller. As the universe expanded, the distances grew, but no point was special. Every point experienced the same expansion, the same cooling, the same evolution. This means that the universe has no center in space. There is no point you can identify and say the Big Bang happened here. The Big Bang happened everywhere. The cosmic microwave background, the light from 380,000 years after the Big Bang, reaches us from every direction because we are surrounded by the sphere of space from which that light was emitted. and observers in other galaxies, billions of light years away, see the same thing. They are surrounded by the CMB, seeing light from their own cosmic horizon. The Big Bang was not an explosion in space, it was the expansion of space itself. And every point in the universe, every galaxy, every star, every atom is expanding away from every other point. We are not at the center of this expansion. There is no center. Every point is equivalent. Every observer sees themselves as stationary while everything else moves away. This is one of the most counterintuitive truths about the universe, and it challenges our deeply ingrained notions of space as a fixed container in which events occur. Space is not fixed. It is dynamic, expanding, carrying matter with it. And the universe we observe, the galaxies receding, the CMB surrounding us, the cosmic horizon limiting our view, is the view from one point among countless others, each seeing the same expansion, each occupying a universe with no center and no edge. 80 facts, and the universe reveals itself as more extreme, more violent, more strange than we could have imagined. We have witnessed magnetars with magnetic fields that would dissolve matter, pulsars spinning hundreds of times per second, temperatures hotter than anything in the cosmos, and planets where it rains molten glass sideways. We have discovered the mysteries of fast radio bursts, learned about the great attractor pulling our galaxy through space, and watched the Sun orbit the Milky Way on a journey that takes 225 million years. We have sent the Voyager Golden Record into interstellar space, discovered circumbinary planets orbiting two stars, and learned about quasars that outshine entire galaxies. We have explored the universe's first 380,000 years when it was opaque, learned about cosmic rays bombarding Earth, and confronted the vacuum energy problem that threatens to undermine physics. Now, the final part, we complete the journey. We explore the last 20 facts, from the ultimate fate of the universe to the deepest philosophical questions raised by cosmology. The end approaches, and the greatest mysteries await. The universe is calling, one final descent remains. Now, in this final part, we complete the journey. We explore the deepest questions. What is the universe's ultimate fate? Are we alone? What is the meaning of our existence in a cosmos so vast? We confront the anthropic principle, the fine-tuning of physical constants, and the possibility that we live in a simulation. And we end where we began, staring up at the stars, awed by the magnitude of what we have discovered and humbled by how much remains unknown. This is the final descent, the last 20 facts, the completion of our journey through everything that exists. Close your eyes one last time, and let's finish what we started. Fact 81, the fine structure constant, is one of nature's deepest mysteries. The fine structure constant, denoted by the Greek letter alpha, is a dimensionless number approximately equal to 1/137. It appears throughout physics, governing the strength of electromagnetic interactions between charged particles, and no one knows why it has the value it does. Unlike other physical constants that have dimensions, the speed of light, Planck's constant, the gravitational constant, the fine structure constant is pure number, it has no units, and its value would be the same in any system of measurement. This makes it particularly mysterious. You could imagine a universe with a different value for the fine structure constant, and the laws of physics would still be mathematically consistent, but such a universe would look very different from ours. If alpha were slightly larger, electron orbitals would be smaller and atoms would be different. Chemical bonds would have different energies. If alpha were much larger, say, greater than 0.1 instead of 1/137, atoms would not be stable. Electrons would fall into nuclei, and chemistry as we know it would be impossible. If alpha were smaller, atoms would be larger and more loosely bound. Stars would burn differently. The synthesis of heavy elements would be altered. A universe with alpha significantly different from 1/137 might not be able to support complex chemistry or life. The fact that alpha has the value it does close to 1/137, a value that allows stable atoms, complex chemistry, and ultimately life, is sometimes cited as evidence of fine-tuning in the universe. But we do not know if alpha could have been different, or if there is some deeper theory that predicts its value. String theory and other approaches to quantum gravity have attempted to derive the fine structure constant from first principles, but no one has succeeded. The physicist Richard Feynman called the fine structure constant one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. It appears in equations throughout physics, governing phenomena from the emission of light by atoms to the strength of forces in particle accelerators. But its origin remains unknown. It is a number carved into the structure of reality, and we do not know why it is what it is. Fact 82, the anthropic principle says the universe must allow observers. The anthropic principle is a philosophical observation about the relationship between the universe and the existence of conscious observers. In its weak form, it states, The universe must have properties that allow conscious observers to exist, because if it did not, we would not be here to observe it. This seems trivial. Of course, the universe must be compatible with our existence, because we exist. But the anthropic principle has deeper implications when combined with the observation that the fundamental constants of physics appear to be finely tuned for life. Consider just a few examples. If the strong nuclear force were 2% stronger, protons would bind so tightly that hydrogen could not exist, and stars could not burn through hydrogen fusion. If the electromagnetic force was slightly different, atoms would not be stable. If the cosmological constant, dark energy, were much larger, the universe would have expanded so rapidly that galaxies could not form. If the masses of the up and down quarks were slightly different, stable matter would not exist. The list goes on. Many of the fundamental constants of physics fall within narrow ranges that allow complex structures, atoms, molecules, stars, planets, life, to exist. Outside those ranges, the universe would be sterile. No atoms, no chemistry, no evolution, no observers. The anthropic principle offers one explanation. We observe a universe with these properties because only such a universe can produce observers. If the multiverse exists, if there are countless universes with different physical constants, then we necessarily find ourselves in one of the rare universes where the constants allow life. This is sometimes called observer selection bias. We cannot observe a universe that does not permit our existence, so the fact that we observe a life-permitting universe is not surprising. Critics argue that the anthropic principle is not predictive and cannot be tested. It explains why we observe what we observe, but it does not predict anything new. Proponents counter that in the absence of a deeper theory that predicts the values of physical constants, the anthropic principle is the best explanation we have for fine-tuning. The anthropic principle raises profound questions. Is the universe designed for life? Or are we simply lucky, existing in one of countless universes, most of which are barren? The answers remain unknown, but the fact remains. The universe we inhabit has properties that seem almost impossibly well-suited for the emergence of conscious beings who can ask these questions. Fact 83. We may live in a simulation. The simulation hypothesis proposes that our reality, everything we experience, including the entire universe, is a computer simulation created by a technologically advanced civilization. This idea, popularized by philosopher Nick Bostrom in a 2003 paper, has gained serious attention from scientists and philosophers. Bostrom's argument goes like this. If civilizations typically survive long enough to develop the technology to run detailed simulations of their ancestors, and if they have the motivation to run many such simulations, then the number of simulated consciousnesses would vastly outnumber real biological consciousnesses. In that case, by simple probability, we are more likely to be simulated beings than original biological ones. The simulation hypothesis makes a testable prediction. If reality is a simulation, there should be limits to computational resources, which might manifest as glitches or fundamental limits in nature, pixels in reality, so to speak. Some physicists have proposed that the Planck length, approximately 1035 meters, the smallest meaningful distance in physics, and the Planck time, approximately 1043 seconds, might be the resolution of the simulation, the smallest units of space and time that the simulation can represent. Others have suggested looking for anomalies in the cosmic microwave background or in the distribution of high-energy cosmic rays, patterns that might reveal the underlying computational grid on which reality runs. So far, no such evidence has been found. The simulation hypothesis is unfalsifiable in its strongest form. If the simulators are sufficiently advanced, they could make the simulation indistinguishable from base reality, and we would have no way to detect we are in a simulation. But it raises unsettling questions. If we are in a simulation, who created it? What is their purpose? Can the simulation be turned off? And perhaps most disturbing, if we develop the technology to run simulations ourselves, does that make us simulators creating new layers of simulated reality? The simulation hypothesis is speculative, and most scientists do not consider it a serious scientific theory because it makes few testable predictions. But it forces us to confront the limits of what we can know about reality. If we cannot distinguish simulation from reality, does the distinction matter? And if the universe operates according to mathematical laws, as physics suggests it does, then is there any meaningful difference between a universe that is real and one that is simulated? Fact 84. Neutrinos pass through your body by the trillions every second. Neutrinos are among the strangest and most abundant particles in the universe. They are electrically neutral, nearly massless, and interact with matter so weakly that they can pass through solid objects, including planets, stars, and your body, as if those objects were not there. Every second, approximately 100 trillion neutrinos from the Sun pass through your body. They stream out of the Sun's core, where nuclear fusion produces them in enormous numbers, and they travel outward at nearly the speed of light, passing through the Sun itself, through space, through Earth, and through you without slowing down or being absorbed. Of the 100 trillion neutrinos passing through you every second, only about 1 will interact with an atom in your body during your entire lifetime. Neutrinos are so difficult to detect that physicists must build enormous detectors deep underground to shield them from cosmic rays and other interference. The Super Kamiokan detector in Japan contains 50,000 tons of ultrapure water surrounded by thousands of light sensors. When a neutrino very occasionally interacts with a water molecule, it produces a charged particle that emits a faint flash of light Cherenkov radiation, which the sensors detect. Even with 50,000 tons of water, the detector captures only a handful of solar neutrinos per day. Neutrinos come from many sources. The Sun, supernovae, the Big Bang. There is a cosmic neutrino background analogous to the cosmic microwave background, though it has never been directly detected, nuclear reactors on Earth, and cosmic ray interactions in the atmosphere. The detection of neutrinos from the supernova SN 1987A, which occurred 168,000 light-years away in the Large Magellanic Cloud, was one of the great triumphs of neutrino astronomy. Several detectors around the world detected a burst of approximately 25 neutrinos, arriving about 3 hours before the light from the supernova reached Earth. This early arrival makes sense. The neutrinos were created in the core collapse and escaped immediately, while the light was created when the shockwave reached the star's surface hours later. Neutrinos are ghosts in the machine of the universe, particles that interact so weakly that they might as well not exist, yet they are produced in such enormous numbers that they carry energy and information across cosmic distances. They pass through us constantly, unseen and unfelt, connecting us to the Sun, to distant supernovae, to the Big Bang itself. Fact 85: the speed of light is not just a speed limit, it is the speed of causality. The speed of light, approximately 300,000 kilometers per second in a vacuum, is often described as the cosmic speed limit, the maximum speed at which anything can travel. But this description misses the deeper truth. The speed of light is the speed at which causality propagates through the universe. According to Einstein's theory of special relativity, cause and effect are fundamentally limited by the speed of light. If something happens here and now, its effects cannot reach a distant location faster than light can travel. This creates a light cone, a region of spacetime that can be causally connected to an event. Everything inside the future light cone can be influenced by the event. Everything outside cannot. This means that the universe has a fundamentally local structure. Distant events cannot affect you until enough time has passed for light, or any signal, to travel from there to here. When you look at the Sun, you see it as it was 8 minutes ago. When you look at the Andromeda Galaxy, you see it as it was 2.5 million years ago. You cannot see the current state of distant objects because that information has not reached you yet. It is traveling toward you at the speed of light. Interestingly, the speed of light appears to be the same in all reference frames, regardless of how fast you are moving. This is one of the most counterintuitive results of special relativity. If you are on a train moving at half the speed of light and you shine a flashlight forward, you might expect the light to travel at 1.5 times the speed of light, your speed plus the light's speed, but it doesn't. An outside observer measures the light traveling at exactly the speed of light, the same speed they would measure if the train were stationary. This constancy of the speed of light forces time dilation and length contraction. Time slows down, and space contracts for moving objects in exactly the way needed to keep the speed of light constant. The speed of light is built into the structure of spacetime. It is the conversion factor between space and time, the rate at which the universe allows information to propagate, the fundamental speed limit of reality. And it is not arbitrary, it is a consequence of the geometry of spacetime, a number carved into the fabric of the universe itself. Fact 86: most of the stars that will ever exist have already been born. Star formation in the universe has been declining for billions of years. The peak of star formation occurred approximately 10 billion years ago, when the universe was about 3 to 4 billion years old. Since then, the rate of star formation has decreased steadily, and it continues to decline. The reason is simple. Star formation requires gas, and the supply of gas in galaxies is being depleted. Gas is consumed by star formation, expelled from galaxies by supernova explosions and stellar winds, and locked up in long-lived stars that will burn for trillions of years. The infall of fresh gas from the intergalactic medium is slowing as the universe expands and gas becomes more dilute. Current estimates suggest that approximately 95% of all the stars that will ever exist have already been born. The era of peak star formation is behind us. The universe is in a long, slow decline, and the future will see fewer and fewer new stars. This has profound implications. Most of the stars that exist today, including the Sun, are relatively young compared to the total lifespan of star formation. But in the distant future, star formation will dwindle to a trickle and eventually cease entirely. The last stars will form trillions of years from now, in isolated pockets of gas that have somehow avoided being consumed or expelled. And after those last stars form, there will be no more. The universe's stellar epoch, the age of stars, the era when galaxies are filled with light and energy and the elements of life are forged in stellar cores, is finite. It began hundreds of millions of years after the Big Bang, peaked approximately 10 billion years ago, and will end trillions of years in the future. We live near the peak of this era in a universe still rich with star formation, still bright with the light of billions of galaxies, but it will not last forever. The stars will fade, one by one, until the universe is dark. Fact 87, the observable universe contains 1024 stars, but most are red dwarfs. We have mentioned the staggering number of stars in the observable universe, approximately 1024, or 1 septillion, but it is worth understanding what kinds of stars make up this population, because the universe is not filled with stars like the Sun. The most common type of star in the universe is the red dwarf, small, dim, cool stars with masses between about 0.08 and 0.5 solar masses. Red dwarfs make up approximately 70 to 80% of all stars in the Milky Way, and probably a similar fraction in other galaxies. They are so dim that none can be seen with the naked eye from Earth, despite their abundance. The nearest star to the Sun, Proxima Centauri, is a red dwarf, and it is invisible without a telescope. Red dwarfs burn hydrogen at such a slow rate that they can live for trillions of years, far longer than the current 13.8 billion year age of the universe. No red dwarf has ever died of old age. Every red dwarf that has ever formed is still burning today, and they will continue burning for trillions of years into the future, long after stars like the Sun have exhausted their fuel and died. Sun-like stars, stars with masses between about 0.8 and 1.2 solar masses, make up only about 10% of all stars. Massive stars, those with masses greater than 8 solar masses, make up less than 1% of all stars. These massive stars burn bright and die young, living only a few million to a few hundred million years before exploding as supernovae. The universe is not dominated by bright, massive stars or by sun-like stars. It is dominated by small, dim, long-lived red dwarfs. If you were to pick a random star in the universe, it would almost certainly be a red dwarf. And around many of these red dwarfs orbit planets, small rocky worlds, some in the habitable zone, some potentially harboring life. The universe may be teeming with life, but that life may exist on planets orbiting dim red stars that humans will never see without telescopes. Fact 88, time travel to the future is possible. We know how to do it. Time travel to the future is not science fiction. It is a confirmed prediction of Einstein's theory of relativity, and we know exactly how to do it: move very fast or spend time near a strong gravitational field. According to special relativity, time passes more slowly for objects moving at high speed relative to a stationary observer. This effect, called time dilation, is real and measurable. Atomic clocks flown on airplanes run slightly slower than identical clocks on the ground. GPS satellites must account for time dilation to maintain accurate positioning. And particles called muons, created in the upper atmosphere by cosmic rays, live longer when moving at high speeds than they do when at rest. They experience time dilation, allowing them to reach the ground before decaying. If you could travel at speeds close to the speed of light, time dilation becomes extreme. At 99% of the speed of light, time passes approximately 7 times more slowly for you than for someone at rest. If you traveled at this speed for what feels like 1 year to you, approximately 7 years would pass on Earth. At 99.9% of the speed of light, the factor increases to about 22. At 99.99%, it is about 71. The closer you get to the speed of light, the more extreme the time dilation becomes. In principle, you could travel to the future by accelerating to near-light speed, traveling for a few years by your clock, and then returning to Earth. You would have aged only a few years, but centuries or millennia might have passed on Earth. You would have traveled to the future, not by skipping time, but by experiencing time more slowly than everyone else. Time travel to the past is a different matter. General relativity allows solutions, like rotating black holes or wormholes, that permit closed time-like curves, paths through spacetime that loop back to the past. But these solutions require exotic matter with negative energy density, which may not exist, and they create causality paradoxes. What happens if you go back in time and prevent your own birth? Most physicists believe time travel to the past is either impossible or severely restricted by laws of physics we do not yet understand. But time travel to the future is real. It is a consequence of relativity, confirmed by countless experiments, and it is something we could do if we had the technology to accelerate spacecraft to relativistic speeds. The future is accessible. The past, as far as we know, is not. Fact 89: the last star will die in 100 trillion years. The universe will not last forever in its current state. Star formation is slowing, galaxies are running out of gas, and the era of stars, the bright, energetic epoch in which we live, will eventually end. But the process will take an incomprehensibly long time. The last stars to form will be red dwarfs, the smallest and longest-lived stars. These stars will continue burning for trillions of years after they form. The longest-lived red dwarfs, those with masses close to the minimum mass required for hydrogen fusion, about 0.08 solar masses, will burn for approximately 10 to 20 trillion years. This means that the last star in the universe will die approximately 100 trillion years from now. At that point, the stellar epoch will end. No more stars will shine. The universe will enter the degenerate era, filled with the remnants of dead stars, white dwarfs, neutron stars, and black holes, all slowly cooling in the darkness. But even this is not the end. White dwarfs will continue to cool over trillions of years, eventually becoming black dwarfs, cold, dark objects no longer emitting significant radiation. Protons, if they are unstable, as some theories suggest, will decay over timescales of 1035 years or more, causing even the remnants of stars to slowly disintegrate. Black holes will evaporate through Hawking radiation on timescales of 10–100 years or more, depending on their mass. In the unimaginably distant future, 10–100 years or beyond, even the black holes will be gone, evaporated into a faint haze of radiation. The universe will be cold, dark, and empty, filled with nothing but photons, neutrinos, and electrons scattered across an ever-expanding space. The temperature will be a tiny fraction of a degree above absolute zero. Entropy will have reached its maximum. Nothing will happen because there will be no energy available to make anything happen. This is the heat death of the universe, the ultimate fate predicted by thermodynamics if dark energy remains constant. The stars will die, the galaxies will fade, and the universe will settle into a state of eternal darkness and cold, with no possibility of recovery, no new structures forming, no light, no warmth, no life, forever. 100 trillion years. It is a long time, longer than the current age of the universe by a factor of 10,000, but it is finite. The stars will die, and when they do, the universe as we know it will end. Fact 90: if you could see all wavelengths, the sky would never be dark. The night sky appears dark because our eyes can only see visible light, and most of the universe does not emit visible light. But if you could see all wavelengths of electromagnetic radiation, from radio waves to gamma rays, the sky would never be dark. It would be filled with light. In the radio portion of the spectrum, you would see the cosmic microwave background, the afterglow of the Big Bang, filling the entire sky with faint microwave radiation. You would see radio emissions from the Sun, from Jupiter, from pulsars, and from active galactic nuclei. The sky would glow with radio light. In the infrared, you would see the heat radiation from every warm object, the Earth glowing brightly, the Sun blazing, distant galaxies shining with the light of their star formation hidden behind dust. The Milky Way would be a bright band of infrared light, and the cosmic infrared background, the accumulated light from all galaxies across cosmic history, would suffuse the sky. In the ultraviolet, you would see hot stars, supernova remnants, and the diffuse glow of ionized gas in the interstellar medium. The Sun would be intensely bright in UV, and the sky would be filled with the ultraviolet light of hot, young stars. In X-rays, you would see the extremely hot gas in galaxy clusters, the accretion disks around black holes and neutron stars, and the remnants of supernova explosions. The sky would be dotted with X-ray sources, neutron stars, black hole systems, active galactic nuclei. In gamma rays, you would see the most energetic phenomena in the universe: gamma ray bursts, pulsars, blazars, and the diffuse gamma ray background from cosmic ray interactions. The sky would flash with gamma ray bursts, brief but enormously energetic explosions occurring somewhere in the universe every day. The darkness of the night sky is an illusion created by the limitations of our eyes. The universe is filled with light at wavelengths we cannot see. If we could see them all, the sky would be a brilliant tapestry of radiation, a glowing dome of light in every direction, revealing the universe in all its energetic glory. We are surrounded by light, we just can't see most of it. Fact 91: the universe could be curved back on itself like a hypersphere. We have discussed that current observations suggest the universe is flat or very close to flat. But flat in cosmology does not mean two-dimensional. It means that the geometry of space follows the rules of Euclidean geometry on large scales. Parallel lines remain parallel, the angles of a triangle add up to 180 degrees, and the universe extends infinitely in all directions. But there are other possibilities. If the density of the universe were slightly higher than the critical density, space would be positively curved like the surface of a sphere, but in 3 dimensions instead of 2. Such a universe is called a closed universe, and it would have strange properties. In a closed universe, if you traveled in a straight line long enough, you would eventually return to your starting point, having circumnavigated the universe. Parallel lines would eventually converge. The universe would be finite in volume but have no edge, just as the surface of a sphere is finite in area but has no edge. You could travel forever without hitting a boundary, but you would eventually come back to where you started. A closed universe would also have a finite lifetime. After expanding for some time, the gravitational attraction of all the matter in the universe would eventually overcome the expansion, and the universe would begin to contract. Eventually, it would collapse back to a singularity in a big crunch, the opposite of the Big Bang. Current observations, particularly measurements of the cosmic microwave background by the Planck satellite, indicate that the universe is extremely close to flat, so close that we cannot detect any curvature. If the universe is curved, the radius of curvature is at least several times larger than the observable universe, meaning we would not be able to detect the curvature directly. But the universe could, in principle, be curved on scales larger than we can observe. We might live in a hypersphere, a 3-dimensional closed universe, and we would have no way to know unless we could map the universe on scales far larger than the observable universe. The geometry of the universe beyond our cosmic horizon is, by definition, unknowable. We can measure the local geometry, and we find it to be flat. But the global geometry, the shape of the entire universe, remains one of cosmology's great unsolved questions. Fact 92: the odds of your existence are astronomically small. Here is a humbling calculation. The probability of you existing, given all the contingencies that had to occur for you to be here, is so small that it is effectively zero. Consider the chain of events required. The universe had to have the right physical constants to allow stars, planets, and life. The solar system had to form in a stable region of the galaxy. Earth had to form at the right distance from the sun. The moon had to form, probably from a giant impact, to stabilize Earth's axial tilt and create tides. Life had to originate on Earth, an event we do not fully understand. Life had to survive multiple mass extinctions over billions of years. Your evolutionary lineage, an unbroken chain stretching back 3.5 billion years, had to survive, reproduce, and evolve. Your ancestors had to meet, fall in love, and reproduce at exactly the right times. The specific sperm and egg that created you had to unite, one chance in hundreds of millions for each conception. If any of these contingencies had gone differently, if your great-great-great-grandmother had married someone else, if the asteroid that killed the dinosaurs had missed Earth, if a supernova had sterilized Earth 2 billion years ago, you would not exist. The number of possible humans who could have existed but didn't vastly exceeds the number who did exist. You are one person out of an essentially infinite possibility space. The odds of you specifically existing are vanishingly small. And yet here you are, against all odds, through an unbroken chain of survivors and reproducers stretching back to the origin of life, you exist. You are reading these words, thinking these thoughts, experiencing this moment. This is sometimes called the anthropic selection effect applied to individuals. Of course you exist. If you didn't, you wouldn't be here to contemplate your existence. But that doesn't make existence any less improbable or any less miraculous. You are a statistical impossibility, and so is everyone else. Every human who has ever lived won an impossible lottery just by being born. The universe is not only stranger than we imagine, it is more generous than we deserve. Fact 93: we are made of quantum fluctuations from the early universe. The large-scale structure of the universe, the distribution of galaxies, the cosmic web of filaments and voids, the pattern of light and dark in the cosmic microwave background, all originated from quantum fluctuations in the first fraction of a second after the Big Bang. In the earliest moments of the universe, space was filled with a quantum field undergoing rapid expansion, cosmic inflation. This field was subject to quantum uncertainty, tiny random fluctuations that created regions slightly denser or slightly less dense than average. These fluctuations were microscopic, subatomic, governed by the Heisenberg uncertainty principle. Then inflation occurred. In less than 1032 seconds, the universe expanded by a factor of at least 1026, stretching these quantum fluctuations from subatomic scales to cosmic scales. The tiny quantum variations became the density variations we see in the cosmic microwave background, regions of space that were slightly hotter or colder, slightly denser or less dense. Over hundreds of millions of years, gravity amplified these variations. Denser regions attracted more matter, growing denser still, eventually collapsing to form the first stars and galaxies. Less dense regions became voids, expanding as matter drained out of them and into the denser regions. The cosmic web we observe today, the filaments of galaxies, the clusters, the voids, all grew from the quantum fluctuations of the early universe, stretched to cosmic proportions by inflation. You are made of atoms that were once part of that primordial density field. The matter in your body condensed out of regions that were slightly overdense due to quantum fluctuations 13.8 billion years ago. The pattern of galaxies in the sky, the structure of the Milky Way, the formation of the Sun and Earth, all trace back to quantum uncertainty in the first moments after the Big Bang. We are made of quantum fluctuations made real. The universe took random noise, quantum fuzz at the smallest scales, and amplified it through inflation and gravity until it became stars and planets and people. We are the children of uncertainty, the offspring of quantum randomness, patterns that emerged from chaos and became conscious. The universe is stranger than we can imagine, and we are part of that strangeness. Fact 94, there may be no absolute meaning, but we create our own. The universe, as far as we can tell, does not have inherent meaning or purpose. It is governed by physical laws, mathematics made manifest, and those laws do not care about meaning, purpose, or value. Stars form and die, galaxies collide, life evolves and goes extinct. The universe operates according to cause and effect, probability and entropy, with no apparent goal or intention. This can seem bleak. If the universe has no purpose, what is the purpose of our existence? If we are temporary patterns of matter, destined to dissolve back into the cosmos, what does anything matter? But this perspective misses something important. Meaning is not something we find, it is something we create. Humans are meaning-making creatures. We create art, tell stories, build civilizations, love each other, pursue knowledge, experience beauty and wonder and awe. These things are not written into the laws of physics. They are emergent properties of complex systems, products of evolution, neuroscience, culture, and consciousness. But they are real, they matter to us. And the fact that the universe does not hand us meaning on a cosmic platter does not make the meaning we create any less valid. You are a pattern of atoms that has organized itself into a configuration capable of experiencing the universe and reflecting on its own existence. You are the universe become conscious of itself, and the meaning of your life is not something dictated by the cosmos. It is something you write through your choices, your relationships, your actions, your values. The universe does not care whether you exist, but you can care. The people you love can care. The communities you build can care. And in a universe governed by indifferent physical laws, the caring matters precisely because it is rare, fragile, and created by us. We live in a universe without inherent meaning, and that is not a curse. It is a freedom, the freedom to decide for ourselves what matters, what we value, what we will dedicate our brief existence to pursuing. The universe gives us atoms and energy and the laws of physics. What we do with them, the meaning we create, the beauty we experience, the love we share, that is up to us. Fact 95, the observable universe is our prison, but also our home. The observable universe, the sphere of space, approximately 93 billion light-years across, from which light has had time to reach us, is all we can ever observe. Everything beyond the cosmic horizon is forever inaccessible, hidden by the expansion of space and the finite age of the universe. This is our cosmic prison. There are galaxies beyond the horizon, possibly infinitely many, that we can never see. There may be entire regions of space where the laws of physics are different, or where structures beyond our imagination exist. There may be civilizations, wonders, phenomena that we will never know about because their light will never reach us. The expansion of the universe is accelerating. Galaxies currently within the observable universe are being carried beyond the horizon, disappearing from view as the expansion carries them faster and faster away. In the distant future, an observer in our galaxy would see only the local group. All other galaxies would have receded beyond reach, their light stretched into undetectability. But the observable universe is also our home. It is vast, containing 2 trillion galaxies, 1024 stars, an incomprehensible diversity of planets, phenomena, and structures. It is old, 13.8 billion years of history, written in the light of distant galaxies and the faint glow of the cosmic microwave background, and it is ours to explore, to study, to marvel at. We may be confined to the observable universe, but we are not confined to ignorance. We have learned to read the history of the cosmos in starlight and gravitational waves. We have measured the universe's age, its size, its composition. We have traced its evolution from the Big Bang to the present. We have discovered its laws, its patterns, its deepest structure. The observable universe is our prison, yes, but it is a prison so vast that we could spend all of human history exploring it and never run out of wonders to discover. We are trapped, but we are trapped in an ocean of light and matter and space, filled with mysteries that will take generations to unravel. The cosmic horizon is a boundary we cannot cross, but it is also a reminder of how far we have come, from beings who thought the Earth was the center of everything to beings who can measure the size of the observable universe and contemplate what lies beyond. We are prisoners of the horizon, but we are also children of the cosmos, and the observable universe is our birthright. Fact 96. Every atom in your body will eventually return to the universe. You are made of atoms, approximately 7 times 10^27 of them, give or take, and every one of those atoms has a history stretching back to the beginning of the universe, and a future extending far beyond your lifetime. The hydrogen atoms in your body, about 60% of your atoms by count, were created in the Big Bang, 13.8 billion years ago. They have existed in one form or another since the universe was minutes old. They have been part of interstellar gas clouds, part of stars, part of planets, part of countless other organisms, and now they are part of you. In a few decades, they will be part of something else. The heavier atoms, carbon, oxygen, nitrogen, calcium, iron, were created in stars. They were forged in stellar cores over millions or billions of years, then scattered into space when those stars died. They drifted through the galaxy for millions of years before being incorporated into the cloud of gas that formed the sun and planets. They were part of the early Earth, part of ancient oceans and rocks, part of the first living organisms. And now they are part of you. When you die, those atoms will not disappear. They will return to the Earth through decay, through decomposition, through the cycles of biology and geology. Some will become part of plants, some will become part of other animals, some will evaporate into the atmosphere, some will wash into the ocean. Some will be buried and compressed and eventually subducted into the mantle, to be recycled through volcanism and returned to the surface billions of years from now. In the far future, trillions of years from now, even the Earth itself will be gone, consumed when the sun becomes a red giant. The atoms that were once you will be scattered into space, incorporated into new gas clouds, part of new stars and new planets, and perhaps new living beings in a future so distant that the universe will be unrecognizable. You are not permanent, but the atoms that make you are. They are older than the Earth, older than the sun, some as old as the universe itself. And they will exist long after you are gone, cycling through the cosmos, part of the great recycling of matter and energy that has continued since the Big Bang and will continue until the last stars die. You are a temporary pattern, but you are made of eternal substance. And in a very real sense, you are the universe experiencing itself, atoms that have organized themselves into a configuration capable of contemplating their own existence. You will dissolve, but the atoms will remain, and somewhere in some form they will continue the story. Fact 97. We have barely begun to explore the universe. Humanity has been studying the universe scientifically for only about 400 years, since Galileo first pointed a telescope at the sky in 1609. In that time, we have discovered that the Earth orbits the Sun, that the Sun is one star among billions in the Milky Way, that the Milky Way is one galaxy among trillions in the observable universe, and that the universe itself had a beginning and is expanding. We have measured the universe's age to within 20 million years. We have mapped the cosmic microwave background. We have detected gravitational waves from colliding black holes. We have discovered thousands of exoplanets. We have sent spacecraft beyond the solar system and landed robots on Mars. But we have only begun. We do not know what dark matter is. We do not know what dark energy is. We do not know if the universe is finite or infinite. We do not know if we are alone in the cosmos. We do not know if there are other universes. We do not know what happened before the Big Bang, or if that question even makes sense. We do not know the ultimate fate of the universe with certainty. We have not unified quantum mechanics and general relativity. We have not detected life beyond Earth. The universe is 13.8 billion years old. Human civilization is approximately 10,000 years old. Scientific astronomy is 400 years old. We have existed for an eye blink of cosmic time, and we have been studying the universe scientifically for a tiny fraction of that eye blink. We have learned an extraordinary amount in that time, but the ratio of what we know to what remains unknown is still vanishingly small. Every answer we find raises new questions. Every mystery we solve reveals deeper mysteries. The universe is not a puzzle with a finite number of pieces. It is an infinite frontier, always receding as we approach it, always offering new wonders, new challenges, new questions we have not yet learned to ask. We have barely begun, and that is cause for hope, for excitement, for awe. The universe is stranger and larger and more magnificent than we can imagine, and we have all of future history to explore it. Fact 98. The universe does not care about us, and that is liberating. The universe operates according to physical laws. It does not care about human beings, human suffering, human happiness, or human survival. Stars explode, galaxies collide, species go extinct, and the universe continues indifferent. This can seem terrifying. We want to matter, we want our existence to mean something, we want the universe to care. But the universe's indifference is also liberating. It means we are free. We are not actors in a cosmic play, assigned roles by a universe that has plans for us. We are not pawns in someone else's game. The universe has given us atoms and energy and the laws of physics, and what we do with them is up to us. We create our own meaning, we decide our own values, we build our own civilizations, we write our own story. And the universe does not judge us, does not punish us for mistakes, does not reward us for obedience. It simply is. And in a universe that does not care, the caring we do for each other, for knowledge, for beauty, for justice, is all the more precious because it is rare. The universe is vast and old, and will continue long after we are gone. We are temporary, fragile, finite. But in our brief moment of existence, we can create, explore, love, learn, build, and wonder. We can study the stars and discover their secrets. We can send messages to the cosmos and listen for replies. We can create art and music and stories that move us. We can love each other and care for each other and build communities that matter. The universe does not care, but we do, and that is enough. Fact 99. The universe is comprehensible, and that is the greatest mystery of all. Here is perhaps the deepest mystery of all. The universe is comprehensible. It operates according to mathematical laws that we can discover and understand. The same laws that govern the fall of an apple govern the motion of planets and galaxies. Quantum mechanics and general relativity, discovered through human reason and experimentation, describe the behavior of the universe from the smallest scales to the largest. Why should this be true? Why should the universe be governed by laws at all? Why should those laws be mathematical? Why should human brains, products of biological evolution on a single planet, be capable of understanding those laws? Einstein called this the eternal mystery of the world, its comprehensibility. The fact that the universe can be understood, that it follows rules, that those rules can be expressed in mathematics and tested by experiment, this is not something we should take for granted. We could have lived in a universe that was arbitrary, capricious, incomprehensible, where no regularities existed and no predictions were possible. But we don't. We live in a universe where understanding is possible. Some have argued that the comprehensibility of the universe is evidence for a designer, that the mathematical structure of reality suggests an intelligence behind it. Others argue that we are products of the universe, and it is not surprising that we have evolved brains capable of understanding the environment we live in. Still others suggest that the comprehensibility is an anthropic selection effect. We can only exist in a universe comprehensible enough to allow the evolution of intelligence. None of these explanations is entirely satisfying. The mystery remains. The universe is comprehensible. Mathematics works, science works, the laws we discover on Earth apply across the cosmos, and we do not fully understand why. But we can be grateful for it, because the comprehensibility of the universe means we are not condemned to ignorance. We can learn, we can discover, we can understand. We can look up at the stars and not just wonder, but know their composition, their age, their fate. We can trace the history of the universe from the Big Bang to the present and predict its future. We can explore the cosmos with our minds even when we cannot yet reach it with our bodies. The universe is comprehensible, and that is the greatest gift the cosmos has given us. Fact 100. We are the universe trying to understand itself. We end where we began, with the recognition that we are not separate from the universe. We are part of it, made of it, products of its laws, its history, its evolution. You are made of atoms forged in stars. You are made of quantum fluctuations from the early universe, stretched to cosmic proportions and then collapsed by gravity into galaxies, stars, planets, and life. You are made of the same substance as everything else, the rocks, the oceans, the stars. There is no fundamental difference between you and the cosmos. You are the cosmos, temporally organized into a pattern that can think and feel and wonder. And in wondering about the universe, you are the universe wondering about itself. When you look up at the stars and ask, what are they? And how did they form? And are we alone? That is the universe asking those questions. When scientists build telescopes and measure the cosmic microwave background and calculate the age of the universe, that is the universe studying itself. When you feel awe at the vastness of space, or the beauty of a nebula, or the strangeness of quantum mechanics, that is the universe experiencing awe at its own existence. We are the mechanism by which the universe becomes conscious of itself. We are matter arranged in such a way that it can contemplate matter. We are the universe's way of knowing that it exists. This is not poetry, it is physics. It is the logical conclusion of everything we have learned about our place in the cosmos. We are not observers from outside, looking in at the universe. We are the universe, looking at itself from the inside. And that perspective changes everything. It means that when we explore the universe, we are exploring ourselves. When we seek to understand the cosmos, we are seeking self-knowledge. When we wonder whether we are alone, we are asking whether the universe has become conscious in other places, in other forms. It means that our existence, however brief, however small, matters in a profound way. We are the universe's attempt to understand itself. We are its eyes and ears and mind. And every discovery we make, every question we ask, every moment of wonder we experience, all of it is the universe coming to know itself. 100 facts, and we have learned that the universe is vast beyond imagining, old beyond comprehension, stranger than we can conceive. We have learned that most of it is invisible, that its fate is uncertain, that we barely understand it. But we have also learned that we are not separate from it. We are made of stardust, governed by its laws, participants in its grand experiment. We are temporary, but while we exist, we are the universe's way of experiencing beauty, seeking truth, and asking the question that defines consciousness. What is this? What am I? What does it all mean? The answers are still incomplete. The mysteries remain, and that is as it should be. The universe is vast, and we have barely begun to explore it. But the fact that we can explore it, that we can understand it, that we can ask the questions and sometimes find the answers, that is the miracle. We are the universe, awake and aware, looking up at the stars and seeing not just points of light but distant suns, distant worlds, distant possibilities. We are the cosmos contemplating itself. And in that contemplation, we find meaning, wonder, and our place in the grand tapestry of existence. The universe is calling. We have only just begun to answer. And the journey continues, outward to the stars, inward to the quantum foam, forward into the unknown future, and backward to the beginning of time. Close your eyes, remember what you have learned, and when you open them again, look up at the stars and know that you are looking at home.